Welcome back to all the students interested in learning more about cloud computing concepts. This is Cloud Computing Concepts Part 2. This course, just like the first part of the cloud computing concepts, remains about the internals of cloud computing, which means distributed systems and distributed algorithms that underlie today's cloud computing technologies. What underlies the hood is what we are going to be focusing on in this second part as well. We'll discuss concepts and techniques and applications of these to industry systems as well as open source systems. This second part of C3, the Cloud Computing Concepts course, builds on the Part 1. C3 Part 1 is a prerequisite for Part 2. We will be reusing and relying on many of the concepts you have learned in Part 1 throughout Part 2 for the homeworks, for the material that we discuss, as well as for the optional programming assignment. So what are we going to cover in C3 Part 2? We'll continue our discussion where we left off in Part 1 and focus on more classical algorithms, including leader election, mutual exclusion, and scheduling, all of which are used in pretty much all the cloud computing systems today. We'll look at a discussion of scalability. How do you support millions of clients with concurrency control and hundreds of servers and replicas with replication control? We'll look at new trending areas such as real-time stream processing, distributed graph processing, and also wisdom and structure of networks, as well as new areas like sensor networks. And finally, we'll discuss areas related to cloud computing such as distributed file systems, distributed shared memory, security, and we'll see case studies of what happens when things go wrong in data centers. And we'll continue interviews with our friends in industry as well as academia. What we'll be relying on from C3 Part 1 includes classical precursors, information about the widely used algorithms and classical algorithms that underlie cloud computing systems, things that you've already learned in Part 1, as well as knowledge about MapReduce and key value stores that you've seen in Part 1. Just like Part 1, here in Part 2 as well, we're going to have homeworks. Here we'll have weekly homeworks. In addition, you'll be doing a programming assignment, and it's in C++. In this programming assignment, you're going to be implementing a fault-tolerant key value store inside an emulator that emulates a distributed system. This builds on the programming assignment from the Cloud Computing Concepts Part 1, so I highly encourage students who have not taken Part 1 yet to go and take a look and even try out the programming assignment from Part 1. And of course, at the end of the course, there's going to be one final exam. Cloud computing continues to be an exciting area, one that is dynamic and continuously changing. And I hope you will continue this journey with me as we complete our tour through the cloud computing concepts landscape. Welcome to this Cloud Computing Concepts course. In this lecture, we'll be covering several concepts that are assumed as a part of the topics that we'll be discussing in the Cloud Computing Concepts course. So we'll be covering several of the basics that are considered to be basics in computer science. Typically, some of these concepts are concepts that computer science students learn in their first couple of years in a computer science degree, undergraduate degree program. So for those of you who are already familiar with this material, this could be a refresher, or you could just skip it if you already know this stuff. In any case, you can always use this orientation lecture as a reference to keep coming back to if you encounter a term during the regular lectures that doesn't make sense to you or that you'd like to be reminded about. So we'll discuss a few topics. We'll discuss some basic data structures, what processes are. We'll discuss a little bit about computer architecture, and then a little bit of math with big O notation, basic probability, and a few other miscellaneous topics. So let's get started here. So basic data structures, we'll discuss two different data structures. The first one is a queue. A queue is essentially a first in, first out data structure. Elements of the queue could be any data types. In this example here, I have elements that are integers. So in this example right now, the queue has 5 elements, 3, 5, 8, 0, 7. This is an ordered list of elements. When you remove an element from the queue, you remove it from the head of the queue. In this case, the head is the element 3. When you insert a new element, you insert it at the tail of the queue, which means that if I insert a new element, say 1, it's going to get inserted right after 7 in this queue. So removal always comes from the head, while insertion always happens at the tail. So for instance, given this particular queue consisting of 5 elements, if you dequeue or remove an item, then that item will be 3. At that point of time, the queue will only consist of 5, 8, 0, and 7, with the head pointing to 5. The next item that you dequeue or remove will be 5. Okay? After that, the queue will consist of only 8, 0, and 7. Then the next item that you dequeue will be 8, and so on and so forth. Dequeues and or removals as well as insertions can occur concurrently, so you can remove an element but at the same time also insert an element at the tail. So that's a queue, which is a first in first out data structure. A different data structure is the stack, which is the first in last out data structure. Imagine a stack of dishes that you place on your table. The dish that you put at the top, that you add the last, will be the first one that you can remove, right? And that's essentially a stack. So remove, or also known as a pop, happens from the top, and insert or a push also happens at the top. Okay, so in this case, if you push a new element into this particular stack, say 9, then 9 will go above 3. After that, if you pop or remove an element, that's going to be the last element that you added, which is 9 in this case. The next pop after that will get 3 because 9 was just removed and 3 is now the top of the stack. After you've removed 3, the next pop or removal will get you 5. And so on and so forth. After that, you'll get 8 and then 0 and 7. Okay, so once again, the removal always returns you the last item that was added, and insertion or push adds an item right to the top of the stack. So these two data structures, queue and stack, are used very widely in computer science, and in fact, we'll be using the notion of a stack right away when we'll discuss processes soon in this particular orientation lecture itself. What is a process? A process is essentially a program in action. For instance, you might write a program in a language like C, C++, Java, or Python, or Ruby on Rails, whatever it is, it doesn't matter what the language is. And when you execute that program, say from the command line or from a GUI, that executing program is called a process. For instance, here I have a C-like program which has a function main, which in turn calls a method f1, which in turn calls a method f2. This is shown pictorially here, main calling f1, calling f2. When you instantiate this program and execute it, it becomes a process, which here in this case is labeled as p1. So this code part shown here is only the program itself. The process itself consists of multiple other components. The code typically doesn't change, but these other components might change. What are these other components? Let's look at them one by one. First of all, there is a program counter, which is an index into the code which says where the program is right now. What is the exact line number within the code where the program is executing right now. Next, you have a stack, which is used by the functions to pass arguments and return values. For instance, when the main function calls f1, any arguments that it needs to pass to f1 are passed via the stack by pushing an element on top of the stack. f1 can then pop that element off and obtain the arguments that are passed to it. Similarly, when f1 calls f2, it then pushes on top of the stack the arguments that it has for f2, and f2 can retrieve these arguments by popping the top of the stack. When f2 is done, it can return the return values to f1 also by pushing the return values on top of the stack, so that when f1 resumes, it can pop the top of the stack to obtain the return values from f2. Similarly, f1 returns its return values to main by pushing on top of the stack. Now, the functions themselves might declare variables. Some variables might be local variables, and local variables are also typically maintained on top of the stack. I'm not showing them here, and this is the reason why when a function or method is completed in its execution, any local variables it declared inside are then gone, because that part of the stack has been popped. In addition, functions might also create new memory by, for instance, calling malloc or new. In this case, I'm showing such a variable x, and such variables are stored in a separate data structure associated with the process known as the heap. Also associated with the heap are also registers, which typically refer to the recently accessed variables in the process itself. So, for instance, this variable x is present in the heap. Such malloc or newed variables also need to be explicitly freed in most cases. However, some programming languages have automatic garbage collection. Now, the reason we are discussing a process here is really the main reason is that when we talk of distributed systems, we're going to talk of multiple processes communicating with each other, and we'll mostly focus on process-to-process communication, although later on we'll also talk about how procedure calls or function calls can cross process boundaries. In addition, the other reason we are discussing a process here is that when you take a snapshot of a process, when I say a process takes its own snapshot, This essentially includes everything that I'm showing here on the slide and maybe a few more elements. It includes the code, the program counter, the current status of the stack, the current status of the heap and the registers, and then a few other elements. Essentially, this information is enough to resume this process from here onwards. Okay, speaking of computer architecture, let's discuss a simplified version of computer architecture. Computer architectures today can be very complicated, but typically when we think of how a process executes on a computer architecture, we can think of a simplified view. So there is a CPU which executes the actual instructions which are present in your code. There are also a bunch of registers that are co-located with the CPU. These are small pieces of memory that can be accessed very quickly by the CPU. Typically, there is only a small number of registers, typically not more than a few tens of registers. There is also a cache, which is a slightly larger memory than the collection of registers. And the larger a piece of memory is, the slower it is to access it. So accessing a cache is slower than accessing registers, but accessing a cache is still pretty fast. Then beyond the cache, there is the main memory, or the random access memory, or the RAM, which is even larger than the cache, and the memory itself therefore is slower than the cache, but still it's pretty fast. And then finally there's a hard disk, or if you would like, a solid state drive, a flash drive or whatever, which is a lot more memory than the main memory, but of course it's much slower. So as you go up from disk to memory to cache to registers, the speed increases, the total amount of storage space that you have decreases. So when you write a program such as C++ or Java or C and you compile it, it gets compiled to low-level machine instructions. These machine instructions might be specific to the architecture, the machine on which you are running, or it might be a virtual machine like a JVM kind of code. In any case, these low-level machine instructions are the executable version of your program, and this is stored in the file system on your disk. When your program starts executing, when it becomes a process, the CPU loads instructions in batches, or in the more simplified way, it loads instructions one by one. It loads them into memory and then into cache and into registers. Typically, the cache and the registers contain the last few accessed instructions, so they follow what is known as the least recently used principle. Now, as it executes each instruction, the CPU, which is executing the process, loads the data that is necessary for the instruction into the memory, and then if necessary into the cache and the registers. And if there are any necessary changes that happen to a variable like x, then these are stored into a memory, first into cache and then into memory. Once in a while, you may need to store something on disk so that you have a permanent storage. So in case the process goes offline, then you still have some data saved. For instance, the program might open a file and write something into the file. So in this case, you may want to write those updates to the file onto the disk. Now, of course, this is a very highly simplified picture. Computer architectures can be far more complex than this today, but for our practical purposes in this course, and as far as explaining how processes work, this will suffice. So next we move on to a few mathematical topics. The first mathematical topic is a big O notation. The big O notation is one of the most basic ways of analyzing algorithms. When I give you an algorithm and I say analyze the algorithm mathematically, essentially I expect you to come up with at the least a big O notation analysis of that algorithm. The big O notation describes an upper bound of the behavior of an algorithm as some variable is scaled or increased in value all the way till infinity. Typically, this variable is the size of the input, maybe the number of input elements. You'll see a few examples of this. So essentially, this big O analysis tells us how does the algorithm itself scale as the size of the input is increased. This analyzes the runtime, or typically another performance metric as well. Most of the time we analyze runtime. Sometimes, as you'll see in the course, we'll analyze things like number of messages, even bandwidth that is exchanged in the total network itself. The important thing about big O notation is that it captures worst case performance. Okay, so this is not expected performance or best case performance. Big O is worst case performance. Given this algorithm, what is the worst that it can do in terms of this performance metric that we are measuring? So essentially, when I say an algorithm A is order of foo, this means that algorithm A takes less than c times foo time to complete, assuming time is the metric we are measuring, for some constant c, a fixed constant c, beyond some input size n. Okay? Typically, this foo that is present in this definition is some function of the input size n. For instance, I could say that an algorithm is order n, which means that the algorithm A takes less than c times n time to complete for some constant c beyond some input size n. Similarly, the algorithm might be order n squared, which means that it is quadratic in time and it takes time less than c times n squared for some constant c. Once again, when we say order n squared or order n, notice that we do not include the constant c in the definition itself. This is because the constant is irrelevant. As long as there is a fixed constant, some fixed constant, that is good enough for us as far as big O notation is concerned. Okay, so we do not state the constants in big O notation. So let's see a couple of examples. So first, I give you an unsorted list of, say, integers, and I ask you to search for a specific element in the list. This essentially means that you have to iterate through the list one item at a time and search for the element by trying to match it with each element already present in the list. What is the worst case performance? That's what we need for big O notation, right? So the worst case performance happens when either the element is not there at all in the list, so you return a false, or the element is the very last one in the list, the very last one that you match against. Therefore, the worst case performance involves n operations, and the number of operations involved is less than c times n, where c equals 2, because the number of operations is n, where n is the size of the list. Okay, so the time as well as the number of operations, assuming each operation takes 1 unit of time, both the time taken for this algorithm, which iterates through the list, as well as the number of operations are both order n. That's why we say order n over here. Let's take a different example to see how big O notation works. This deals with insertion sorting of an unsorted list. So suppose I give you a list of elements, say integers, and this is unsorted, and I ask you to sort them, say, in increasing order of the elements. The insertion sort algorithm works as follows. First, you create a new list that is empty. Then you iterate through the elements in the unsorted original list. You remove one element at a time, and you insert that element in the new list at the appropriate position. Essentially, you sort through the new list linearly, searching for the right position where this element should be. So if you do this, the first element of course takes one operation to insert. That's one insert operation. The second element in the worst case takes two operations to insert. One operation for the comparison with the one element that's already present in the new sorted list, and one more operation to insert. Imagine the worst case where this second element is inserted right at the very end of the list. Similarly, the third element will take three operations to insert, where the first two elements compare it with the two already existing elements, and the third operation inserts it at the very end of the list. If you go on like this, then the ith element takes I operations to insert, and you can calculate that the total time required to insert all the n elements is 1 plus 2 plus 3, so on till n, and this is a well-known sum which comes to n times n plus 1 divided by 2, which is less than 1 times n squared. So with the value of c equals 1, this insertion sorting example is an algorithm that takes order n squared in time and also order n squared in number of operations. Next, we'll look at a little bit of basic probability. Before probability, we need to discuss a few definitions. The first definition is a set. A set is essentially a collection of things. So for instance, a set S might be the set of all humans who live in this world at this current moment. A subset is another set, which is a collection of things that is a part of the larger set. So I might describe a set S2, which says a set of all humans who live currently in Europe today. S2 is a subset of S because every element that is present in S2 is also present in S, but the reverse is not necessarily true. Okay, so now probability. Any event has a probability of happening. Okay, so let me give you an example. If you wake up at a random hour of the day, say you just wake up at some random hour of the day, say you're jet lagged or something, and I ask you what is the probability that the event at the time is between 10 a.m. and 11 a.m. Let's try to calculate this. Well, there are 24 hours in a day, so you have a set that consists of 24 elements, one for each hour, 12 a.m., 1 a.m., 2 a.m., all the way till 10 a.m., 11 a.m., 11 p.m. Okay, so when I say an element like 1 a.m., I mean the hour between 1 a.m. and 1:59 a.m. Similarly, 10 a.m. means 10 a.m. and 10:59 a.m. Out of this set of 24 elements, you pick one at random, and the probability that you're going to pick 10 a.m. is essentially 1 divided by 24, because you're picking one element at random, and there are 24 elements in the set, and the probability that you pick that one special element 10 a.m. is 1/24, because you want to be lucky of that to pick that 10. Okay, so the probability that if you wake up at a random hour of the day, the time is between 10 a.m. and 11 a.m., that probability is 1 over 24. Now, there might be multiple events and you might need to calculate the probability of conjunctions or disjunctions of these events. I'll describe what these are soon. So say E1 is one event and E2 is another event, and E1 and E2 are independent of each other. This means that E1 does not influence E2, E2 does not influence E1. Then the probability that E1 and E2 both happen is essentially the multiplication of these probabilities. So you take the probability of E1 multiplied by the probability of E2, and that gives you the probability that both E1 and E2 are true. Let's discuss an example of this. Suppose you have 3 shirts. They're colored blue, green, and red. And also you wake up at a random hour and blindly pick a shirt. You put your hand into your closet and you blindly pick out a shirt. What is the probability that you woke up between 10 a.m. and 11 a.m. and that you picked a green shirt to wear? Well, the first probability of the first event, that you woke up between 10 and 11, is essentially 1 over 24, like we calculated on the previous slide. The probability that you pick the green shirt is essentially 1 out of 3, because there are 3 colors of shirts. You have 3 shirts, and you want to pick the green one. You want to be lucky to pick the green one, so that's 1 over 3. And so the probability that both these events are true, that you woke up between 10 and 11 and that you wore the green shirt, is the multiplication of the probabilities of those events. So it's 1 over 24 times 1 over 3, and that gives you 1 over 72. One of the things that you have to be careful about here is that if E1 and E2 are not independent, meaning that they influence each other in some way, then you cannot multiply the probabilities with each other. Okay, so for instance, if the shirts that you have in your closet change from 1 hour to another because say someone in your house changes them around, then you can't necessarily multiply these probabilities as they are here. A different thing that you may need to do with 2 event probabilities is to OR them. So if I give you 2 events E1 and E2, and I ask you the probability that of either E1 or E2 happening, then you can say that the probability of E1 or E2 is the probability of E1 plus the probability of E2 minus the probability of E1 and E2. Okay, so this is the intersection probability here. If you do not know probability of E1 and E2, this last term over here, then you can write the inequality probability of E1 or E2 is less than or equal to the sum of the constituent probabilities. Okay. Sometimes we use these inequalities to upper bound the probabilities of the disjunctions, as we see here. DNS refers to a domain name system. It's essentially a named resolution system. It is run as a collection of servers throughout the world, and it helps you to translate URLs, actually domain names, into IP addresses. So the input to the DNS is a domain name such as Coursera.org, and this is a human readable string that uniquely identifies the object. So we humans can easily remember a name like Coursera.org. Actually, we really remember URLs like class.coursera.org/foo, and when you enter this into your browser extracts the domain name from this URL and then sends this off as a query to the DNS system. The DNS system then returns to you the IP address of a web server that potentially hosts that content, and the IP address is essentially a target or an address or an ID, and it is a unique string that points to the object. The difference between an ID and a name, the output and the input to a name resolution system like DNS, is essentially that IDs are harder to remember. It's harder for us human beings to remember IP addresses. It's much easier for us to remember names. Also, IP addresses change, but names don't. Now, the IP addresses might refer to a actual web server, a unique web server that actually hosts that content, so that now your client browser can send a TCP and HTTP request to that server, or it might refer to an indirect server or even a group of servers, such as in a content distribution network, such as from Akamai. The final thing about name resolution system is that they can be changed. So the ID or the address obtained from one name resolution system can be given as a name to another name resolution system, and that can return a different address, and so on and so forth. And you can keep doing this until you reach your final object itself. Graphs. So when we say graphs in computer science, we don't necessarily mean plots which have x and y axes. A graph is essentially a network. So here I'm showing you a graph of some cities, Amsterdam, Boston, Chicago, Delhi, and Edmonton, and the travel times between those cities by air, rounded up to the nearest hour. Okay, so traveling from Amsterdam to Boston takes about 6 hours. Traveling from Chicago to Delhi takes about 14 hours. Say these are the flights that are available on some particular airline, right? So you see both cities here, as well as connections between pairs of cities, and also some values along those connections, which are the number of hours that it takes to transit between those cities. These all have names in the terms in the world of graphs. So each city would be a node or a vertex. Each connection between a pair of nodes would be called an edge, and the value along an edge is called the edge weight. Also, when I say that A is adjacent to B, this means that A has an edge that connects it to B directly. Typically, an edge only goes between two nodes or two vertices. An edge does not cross three nodes. So here, for instance, I have 1, 2, 3, 4, 5 vertices. And how many edges do I have? I have an AE edge, an AB edge, a BE edge, a BC edge, and a CD edge. So I also have 5 different edges, each with its own edge weight. So in this lecture, we have covered the basic data structures such as a queue and a stack. We have seen that processes are programs in action, and then they consist of multiple different pieces. Processes, of course, run on a computer architecture, and it's important for you to know at least a simplified version of the computer architecture so that you know what's operating where when you run a process. We've seen some mathematical topics such as big O notation, which analyzes the worst case performance of any given algorithm, and then some basic probability. And finally, we have seen a few miscellaneous topics. I hope you can keep coming back to this as a reference whenever you need it throughout the course. Congrats, you've completed C3 Part 1 and you're on to C3 Part 2. If you recall, we ended C3 Part 1 with a discussion of some of the core theoretical concepts that underlie distributed systems and that are used in clouds today. This week, in the first week of the C3 Part 2 course, we complete the remaining theoretical concepts that are core in distributed systems. These include leader election and mutual exclusion, and we'll also see not just the algorithms, but also some examples of the use of these algorithms in real cloud systems today. Also, I want to remind you that at this time, if you would like to do the programming assignment for this C3 Part 2 course, please make sure that you complete the programming assignment for C3 Part 1 course first. This is very critical because the C3 Part 1's programming assignment is a component or a building block for C3 Part 2's programming assignment. Recall that C3 Part 1 is meant as a prerequisite for C3 Part 2. So if you have not taken C3 Part 1 so far, I would highly encourage you to go through the concepts in that course and also to do the programming assignment there if you intend to do the programming assignment for C3 Part 2. Hi there. In this series of lectures, we are going to look at the classical problem called leader election, which has been useful in many variants of distributed systems, including today's cloud computing systems. In this lecture today, we'll see what the leader election problem actually is. So let's start with an example. Suppose your bank account details are replicated at a few servers that are maintained by your bank. But one of the servers that the bank maintains is responsible for receiving all the reads and writes from a client, such as ATMs or the banking application on your iPad or the banking application on the website, and so on and so forth. So this single special server that is on the bank side is called the leader server among the replicas. Okay, so the leader is responsible essentially for coordinating the replicas. Now, there are several scenarios that can happen with a leader. There might be 2 leaders per customer. This might be problematic because now the group of replica servers is not sure who the leader is, and therefore reads and writes might be split across these multiple leaders. Servers might also disagree about who the leader is. Some servers might know server A as a leader, and other servers might consider a different server as a leader, and that server might not even think it's the leader. And this might again lead to inconsistency in the system. If the leader crashes, then this means that the clients may not be able to send reads and writes to the system, and once again you may need to re-elect a new leader in the system. So each of these scenarios that I've described as a question leads to either inconsistency or unavailability in the system. Some more examples of situations which require a leader. We discussed the different types of multicast ordering, and one of the ways of implementing total ordering for multicasts was to use a sequencer process, and this was a special elected process from among the group of processes itself, and there needed to be exactly one sequencer process. Okay, this sequencer is essentially the leader. If you have multiple sequencers, then total ordering may in fact be violated in the group. When we discuss time synchronization, we discuss the network time protocol, also known as NTP, and the NTP organizes all the servers into a tree, and there is one server at the root of the tree, and you need to elect who this server is from among all the potential NTP root servers. Other systems in industry that also leverage leader election include open source systems such as Apache Zookeeper and also Google's Chubby system, on top of which a lot of Google's internal systems rely on. Essentially, in a nutshell, a leader in a process group is useful for coordination among the processes in the group itself. Typically, these processes are servers in a cloud. So, in a nutshell, in a group of processes, we want to elect a leader. One of the processes needs to be elected as a leader to undertake special tasks such as coordination. Also, it's not just sufficient to elect a leader and let the leader know about it. You need to let all the other non-leaders in the group also know who the leader is. So these are the two requirements of the leader election protocol. Now, what happens when this leader crashes or it fails? Well, first of all, some process detects this failure. How does it detect this? Well, it detects this using, say, a failure detector, using any one of the failure detectors we have seen elsewhere in this course. You could also use other mechanisms, as we will see some of our systems do. But what happens after you detect this failure? Well, after this failure is detected, then you need to run another election algorithm so that a new leader is elected, and this leader is a non-faulty process, meaning one that has not crashed. And also you need to let all the other non-faulty processes in the group know who the new leader is. So that's the goal of the election algorithm. That's the leader election problem in distributed systems. So once again, when someone gives you a problem, just make sure that you know what the system model is under which you're trying to solve the problem. Essentially, the system model tells you what the assumptions are. In this case, our system model consists of n processes. Each process has a unique ID. For instance, it's IP address and port number. Messages that are sent from one process to another are delivered eventually. They may take a while, but they're delivered eventually and they're delivered reliably. Failures may also occur during the election protocol. So, for instance, while you're trying to elect a leader, the leader might itself fail. The next would-be leader might in fact fail, or one of the other processes in the system might fail, and the leader election protocol needs to be tolerant to such failures. So, a few more requirements from the viewpoint of the election itself. Any process should be able to call for an election. Why is this? Well, first of all, any process in the system may detect the failure of the leader, for instance, via the failure detector. Most failure detectors allow any process in the system to detect the failure, for instance, heartbeat-based failure detectors or gossip-style failure detectors. When a process detects that the leader has failed, it can initiate an election, which essentially means it calls for an election. A process can call for at most one election at a time. We don't want multiple elections running simultaneously. If multiple processes call an election simultaneously, we want all of those together to yield exactly one leader. We don't want them to yield conflicting leaders. But at a time, you want only one election running. Also, the result of an election must not depend on who calls it. So the initiator's ID, whichever process initiated the election, that must not influence the outcome of the election itself. Instead, the outcome of the election must be based on certain other criteria that are important to the system or are important to the application. So a little bit more formally, a run of the election algorithm must always guarantee two properties at the end. The properties are safety and liveness. Safety, once again, just to remind you, is the property that nothing bad ever happens. And in this case of the election, safety says that for all non-faulty processes P, P's elected variable, which stands for P's vision of who the current leader is, should either be Q, a particular non-faulty process with the best attribute value. I'll talk about attributes in a little bit, but essentially assume that each process in the group has an attribute, say the IP address is the attribute. Right? We want to elect that process as the leader that has the best attribute value, say the highest IP address. So safety says that P's elected variable must point to that non-faulty process in the group that has the best attribute value, or P's elected variable points to null. In other words, P never makes a mistake and points its elected variable to a leader, a process that must not be leader according to the best attribute. Liveness property, again, informally speaking, liveness says that something good eventually happens, and in this particular case, the liveness property says that for all runs of the election run terminates, meaning that something, all the processes quiesce at the end, and then for all non-faulty processes P at the end, P selected is set to non-null. Okay, so P selected is not null at the end if P is a non-faulty process. So if you combine safety and liveness, this essentially says that at the end of the leader election run, which terminates, that process with the best attribute value is elected as a leader, and all the other non-faulty processes in the system have their local elected variables pointing to this newly elected leader. So what do I mean by electing the process with the best or highest election attribute value? Well, one of the most common attributes used is the highest ID. So among all the IDs in the group, you elect that process as the leader that has the highest ID. You can also reverse this and elect the process with the lowest ID in the group. That's fine too. Other attribute examples include IP address, they include fastest CPU, or you could use a disk space, or you could use, in peer-to-peer like settings, you could use processes that have the most number of files or the least number of files. As long as this attribute is fixed in the beginning and all the processes know about it, you're going to get a consistent leader election specification and a protocol as well. So in the next lecture, we're going to see a classical leader election algorithm, and then we'll follow that up by seeing a few more leader election algorithms. In this lecture, we're going to see the first classical algorithm for a leader election. We'll see another classical algorithm later in another lecture. This classical algorithm is called the ring leader election or ring-based leader election. In the ring, we have n processes organized in a logical ring. This is somewhat similar to the virtual ring or the logical ring that we saw in the peer-to-peer systems discussion when we discussed the CORD distributed hash table. Essentially here, the ith process Pi has a communication channel to the i+1th process, that is its successor clockwise in the ring. You need to take modulo n so that the process n-1 is pointing and has a successor of process P0. All the messages are sent clockwise around the ring from only a process to its successor in the ring. Here's an example of a ring. Here I don't have process IDs in consecutively increasing orders, but essentially the processes are organized in a ring where every process has a successor in the ring. So N3, for instance, has a successor which is N32, so it can send messages to N32. N32 in turn is a process that has a successor of N5, which in turn has a successor of N80, and so on and so forth, and then N12 has a successor of N3, which completes the ring. So what does the algorithm look like? So let's look at the an informal description, pseudocode of the algorithm, and then we'll see the example played out. Any process Pi that discovers that the old coordinator or the old leader has failed initiates an election message, and the election message contains the initiator Pi's own ID along with its own attribute. Okay, the ID is needed so that you need to be able to identify who last wrote into the election message, and the attribute is needed so that you can elect the best or the highest attribute process as the leader. Pi is the initiator of the algorithm. It then passes along this election message to its successor. What does the process do when it receives an election message? Well, when a process Pi receives an election message, it looks at its own attribute value and it compares it with whatever is in the message. If the arrived attribute is greater than its own attribute, then Pi knows that it is not eligible to be a leader because it doesn't have a higher attribute. Pi merely forwards a message as is. It does not change the message. However, if the arrived attribute is smaller than Pi's own attribute value, and if Pi has not yet forwarded an election message earlier, it overwrites the message with its own ID and its own attribute, because this is the max attribute that has been seen by the message so far, and then it forwards this newly overwritten message. Now, why do we say that Pi needs to check whether it has not forwarded an election message so far? Because this will come back to the termination criterion later on. But essentially what this rule is saying over here is that when PI receives an election message, it compares the attribute in the election message with its own, and if its own attribute is higher, then it overwrites the message with its own ID and attribute. However, if the received election message has an ID and attribute that matches PI, then this means that PI's attribute was written into the message the last time it passed PI, and that the message has made one circle or one circuit around the ring and has not changed, which means that none of the other processes in the system in the ring have a higher attribute than PI's own attribute. In this case, PI knows when it receives this duplicate election message with its own ID and attribute that it must be the new coordinator or the new leader. Therefore, this process PI now sends out an elected message to its neighbor containing the ID saying that it is now the new leader. So what does the process do when it receives this elected message? When a process PI receives an elected message, it points its own local elected variable to the ID of the message, saying that it now knows who the leader is, and then it forwards the message to its successor. However, if it is the new coordinator or the new leader, it doesn't forward the message anymore, because essentially this means that the message has made one circuit around the ring and everyone has set their elected variables to the new leader. So that in a nutshell is how the lead election protocol works using the ring. Now let's see an example with the previous ring that we had discussed. Once again, here the goal is to elect the process with the highest ID as the leader in the group. And this essentially means that the attribute is the ID. The attribute we're using in the election is the ID. So N3 is the initiator. It's the one that detects the failure, or it's the one that just calls for an election because it's time to call for an election. It initiates the election by sending an election message. It includes its ID in there. It doesn't need to include a second attribute because the ID is the same as the attribute. So it sends this message, the election message, to N32. When N32 receives it, it knows that its own ID is higher than what's in the message. 32 is greater than 3, and so it overwrites the message with its own ID and then passes on the modified message to its successor. N5 receives this message, compares the ID in the message 32 with its own ID. The message's ID is higher, so it forwards the message unchanged to its successor. N80 receives this message, sees that its own ID 80 is greater than what's in the message 32, and so it overrides the message with its own ID 80 and then passes it on to its successor. Similarly, the election message goes through N6 and N12 unchanged because their IDs are lower than what's in the message. And now it reaches N3. N3 again just passes on the message. It compares what's in the message. It's the initiator, but it doesn't stop the election message from going around. What instead happens is that eventually the election message gets to N80, which sees that this is a duplicate election message and that the ID in the message is its own ID. And so the election message must have made one circle or one circuit around the ring, and it was unchanged, which means that none of the other processes in the ring have a higher ID than itself. At this point, N80 knows that it is going to be the next leader, and it starts an elected message that says that it itself is going to be elected as a new leader. When this elected message is passed on to its successor, N6, N6 receives it. It marks its own elected variable to be 80, which says that N6 knows that N80 is in fact the new leader, and then it passes on the elected message to its own successor, N12. Similarly, this elected message makes its way all the way around the ring. Everyone marks their local elected variables to be 80, and then finally it gets back to N80, the elected message. N80 sees that the elected message's ID is the same as itself, and so it can now drop the message and not forward it anymore. And at this point of time, the election protocol is done. N80 has been elected as the leader. It knows that it is a leader, and all the other non-faulty processes in the group know that N80 is in fact the leader. So that's the termination of the election over here. So let's analyze this protocol. First of all, let's assume that there are no failures that occur during the lead election protocol itself. Later we'll see the effect of failures. And let's assume that there are n processes in the ring. How many messages are exchanged in the lead election protocol? Well, the worst case occurs when the initiator is the ring successor of the would-be leader. So essentially, going back to the previous slide, if the initiator of the lead election protocol would have been N6 in this particular case, that would be the worst case. Essentially, the initiator would be the successor of the would-be leader. Why is that? Well, let's see what happens. So if the N6 is a process that initiates the lead election protocol, there are n-1 messages needed for the election message to get from the initiator to the would-be coordinator, because it loops from n6 all the way back around to n80. Then n80 marks the election message with its own ID. Now the election message needs to make one more circuit around the ring, another n hops, until it gets back to n80, and n80 knows that it is a new leader, so that's another n messages. And finally, the elected message sent by n80 makes another circuit around the ring, that's another n messages. So that's a total of n-1 plus n messages. That's 3n-1 messages for the total leader election to be completed in the worst case. The completion time is also 3n-1 message transmission times over here. If there are no failures, and if all messages are delivered eventually, this election terminates because it terminates within a finite, bounded number of message transmission times. So that guarantees liveness. Also, everyone knows about the leader at the end of the leader election protocol, and the leader knows that it is a leader, and so this guarantees safety. What is the best case that can occur? Well, the best case that can occur is that the would-be leader n80 in our example is in fact the initiator. So if n80 is initiator, then it starts the election message. It makes one circuit around the ring and gets back to n80, which then makes the elected message go around the ring again, and that's another n messages, and the protocol is done. So that's n plus n, 2n messages, and the completion time is 2n message transmission times. Now, what happens when you have multiple initiators? Remember that we said that if you have multiple initiators in a leader election run, we want all of them to yield just one leader, not every initiator's election yields a separate leader. That would be a violation of safety. Now, multiple initiators can be supported by modifying the protocol we have discussed so far, by having each process remember in its own cache the initiator of each election and elected message it receives. You can have the election elected message carry the ID of the initiator itself. Whenever a process receives an election or elected message that has a lower ID initiator than one it has seen so far, it doesn't forward those messages anymore. So this essentially means that if there are multiple initiators in the group, only the highest ID initiator will have its election complete, and therefore that will lead to exactly one leader. All the other elections called by lower ID initiators will be suppressed, and they will never complete. Okay, so this supports multiple initiators, and it still guarantees safety using our ring-based approach. Next, we need to discuss what happens with failures that occur during the election protocol itself. So for instance, if N80 fails, the new would-be leader fails when it has already sent an elected message, elected equals 80 message. Unfortunately, this is a case where the election protocol may not terminate. In fact, the termination condition here is that N80 must receive back an elected message and say, hey, this is an elected message with my own ID, and so I'm not going to forward it anymore. Unfortunately, because N80 has crashed, even if the ring were reorganized so that N5 had a new successor of N6, this selected message saying the new leader is 80 would circulate around the ring forever, essentially. So liveness would be violated over here, and this protocol would not terminate. So one option to fix failures is to have the predecessor or maybe the successor of the would-be leader N80 detect its failure and start a new election run if N80 does not stops responding. So this successor or predecessor might reinitiate the election if it receives an election message but times out waiting for the elected message from N80. Or it might receive the elected message and then it might not hear again from N80 again, or N80 may not respond to the pings that are sent by its predecessor. However, and in fact, this is the approach that is used by some systems like Apache Zookeeper, as you will see later on in another lecture in this series. However, the predecessor itself, which is responsible for detecting N80's failure, might in fact fail, right? In which case, you have no one to detect the failure of the leader. You might say, well, okay, what about the predecessor's predecessor, which might now take over for its job? What if that process also fails? A second option is to use a failure detector itself. Any process after receiving the election 80 message can detect the failure of N80 via its own local failure detector. If so, if you detect a failure, then you can start a new run of the leader election. However, failure detectors may not be complete as well as accurate, because we've already seen this is true in an asynchronous distributed system. Incompleteness means that N80's failure might not be detected at all, and this might be a violation of safety because the leader has failed and and no one has detected it, and so there is no leader that is non-faulty in the group right now. Inaccuracy in a failure detector would mean that NAD might be mistakenly detected as failed, and a new election might be initiated, and every time you may have the worst case happening, which is that the would-be leader is detected as having failed and a new election is initiated, and this means that you may never ever terminate the leader election protocol. So why is it that leader election is turning out to be so hard? Well, that's because it's related to the consensus problem. In fact, if we could solve election, then we could actually solve consensus. How would we do this? Well, a simple way to do this is to elect a process using whatever election protocol you have that is guaranteeing safety and liveness, even under failures. And then you use the leader election, the leader's ID, you use its last bit, which is either a 0 or a 1, as the consensus decision. Because everyone knows who the leader is, they know what the leader's ID's last bit is, and so everyone agrees on the value of the consensus variable. However, since we know the consensus is impossible to solve in an asynchronous system, so is leader election. However, it is still possible to use consensus solving approaches such as Paxos to solve leader election, and we'll see that in the next lecture. In this lecture, we're going to look at how election is done in a couple of popular systems in industry. They are Google's Chubby system and the open source Apache Zookeeper system. Both of these systems use consensus or consensus-like approaches to solve election. One approach to using consensus to solve election is to have each process propose a value. Everyone in the group reaches consensus on some process PI's value, and then PI is elected as a new leader. Whichever is the lucky process whose value is chosen as the consensus value, in fact becomes the lucky leader in the group. This is one approach. This is not necessarily the approach that these systems follow in industry. The systems in industry follow Paxos-like approaches for election. Paxos, as we've seen elsewhere in the course, is a consensus solving protocol. It's guaranteed to be safe, meaning that it assures that never is the case that different decisions are reached by different processes for the consensus variable, but it's only eventually live, which means that it doesn't guarantee that the protocol will ever terminate. Google's Chubby system uses a Paxos-like approach, and Apache Zookeeper also uses a Paxos-like approach. So let's look at Google Chubby first. Google Chubby is a system for locking. It is an essential part of Google's internal stack of systems. Many of Google's storage systems, such as Bigtable and Megastore, rely on Google Chubby for locking and for writing small configuration files. Chubby maintains a small group of replica servers. For instance, Chubby cell might contain 5 replica servers, server A, B, C, D, and E. And one of these servers is elected as a master server at all points of time. So at any point of time, exactly one of these servers must be the master or the leader, and all the other servers in the group must get to know about who the leader is. This is essentially our leader election problem. Right? So for instance, in this case, server D is the master here. Now, in order to make sure that there is exactly one master and everyone knows who the master is, an election protocol is required. Potential leader, a server that wants to be a master or a leader, tries to get votes from the other servers. Each server votes for at most one leader, and when a potential leader gets a majority of votes from the group, in this case a majority would be 3 or more of the servers voting for you, then that server becomes the new leader. When you have at least 3 votes from the group, you can become the leader. So why is this approach safe? Well, essentially every potential leader is trying to reach a quorum in the system. And once again, this is an example of a technique that you have seen elsewhere in the course that should be familiar to you. Quorum is essentially a majority or larger. Since any 2 quorums, no matter which processes they contain, are guaranteed to intersect in at least one process, and each process can vote for at most one leader, you cannot have the case that there are multiple leaders elected by this election protocol. So this algorithm guarantees safety. Why is this algorithm live? Well, it's only eventually live because, of course, you cannot solve consensus in an asynchronous system, and so failures may keep happening so that no leader is ever elected. But if things go right in the future, when messages are not delayed too much, when not too many bad failures happen, then the protocol has a good chance of converging and terminating. In fact, the folks at Google saw that elections typically take few seconds. That's a typical time to run an election. And the worst case that was noticed in the original paper written on Chubby by Google noticed that the worst case election run took only 30 seconds. Chubby also uses a concept known as leases. After an election finishes, meaning a leader has been elected, the other servers in the group, in this group over here, server A through E, guarantee that they will not run another election for a while. Okay, so this while of time, or this time duration, is called a master lease. This is the minimum amount of time that the master is guaranteed to be the leader. Okay, this is typically said to be a few seconds. The master lease must be renewed by the master by simply getting a majority again. So as long as it's able to get a majority, it can continue to be the leader without going through the overhead of running the entire leader election protocol all over again. This technique of leases or master leases also ensures that if the master fails to renew a lease, for instance, it has failed or has just become very slow, then automatically the other servers start a new election run where a new master is going to be elected with a new quorum. Next, we're going to look at election in Apache Zookeeper. Apache Zookeeper is an open source system that is a centralized service for maintaining configuration information. Zookeeper uses a variant of Paxos called ZAB or ZAB, which stands for Zookeeper Atomic Broadcast. Zookeeper needs to have a leader elected at all times. The way leader election works in Zookeeper, at least the vanilla way of electing leaders in Zookeeper, is by having each server create a new sequence number for itself. Let's call these sequence numbers as IDs. Essentially, each server does the following. It gets the highest ID so far, it fetches this from the Zookeeper file system, creates a next higher ID, and it writes this into the Zookeeper file system. At the end, whichever ID remains, the process that wrote it becomes the new leader. Okay, so the highest ID server becomes the new leader. So this ensures that as long as the files are written atomically, that files are overwritten completely, and you don't have partial writes from two different servers, you're ensured that there is exactly one ID in that Zookeeper file at the end, and so everyone knows who the leader is by looking at that file, and the leader also knows who the leader is by looking at that file. Okay, so for instance, N80 might be elected as leader because it has the highest ID in the group. What about failures? Well, when you have failures such as the leader itself crashes, one option is for everyone to monitor the current master, for instance, by using a failure detector such as heart beating or ping-ponging. When there is a failure detected, the processes initiate a new election run. However, when the master fails, multiple other processes in the group might initiate elections simultaneously, and this may lead to a flood of messages. Even though you could use a way to suppress the election messages so that at most one of them completes, still it does lead to an explosion of messages. So the option that is actually implemented in Zookeeper involves each process monitoring its next higher ID process. So N32, which is the second highest ID process in the system, monitors N80. N32 itself is monitored by N12, N12 is monitored by N6, and so on and so forth. And of course, N3 is monitored by N80 so that you wrap around the ring. If a process has a successor, that is the current leader in the group, this would be N32, whose successor is N80. And if that process successor has failed, then N32 can immediately become the new leader. So it doesn't even need to run a new election protocol. However, if your successor is not the leader, for instance, N12 or N6, then you need to wait for a timeout and you need to check your successor again. So if you time out waiting for your successor to respond, then you make sure that you then point to your successor's successor. If your successor was a leader, then you can become the new leader. Now, conflicts may happen in the system because two different processes might write the same sequence number into Zookeeper file, and might turn out that both of them think that they are the leader in the group. The leader might also fail during the election run. To address both these issues, Zookeeper uses a two-phase commit protocol, which is run after the sequence ID protocol that we have discussed before. In this two-phase commit, the potential leader, which sees its own sequence number in the Zookeeper file, sends a new leader message to all the processes in the group. Each process that receives a new leader message waits for a while. It might receive new leader messages from multiple prospective leaders. It responds back with at most one ACK message, with at most one vote message, and it sends it back to that potential leader that has the highest process ID. Now, what does the leader do? Well, the leader waits for a majority of processes to send it back ACKs. If it reaches a majority, then it knows that it is a leader because each process would have voted at most once. And if it's got a majority, if this leader has gotten a majority, then it's sure that no other potential leader would have gotten a majority. This is the same idea as quorums or majorities that we have seen elsewhere in the course. Once a leader has his majority of ACKs, it can then send a commit message to all saying that it is the new confirmed leader, and everyone else on receiving this commit message update their leader or elected variable to be the new leader. Okay, so this ensures that safety is still maintained because once a leader has a quorum, no one else can have a quorum, and so it becomes a new leader. However, this may not guarantee liveness. It's possible that two potential leaders that send out new leader messages simultaneously, maybe there are more than two leaders, suppose there are three leaders in the group that are sending out new leader messages, each of them gets about a third of the votes or third of the acts from the group, and so now no one has a majority, no one has 50% or more of the acts in the group. And so liveness is not guaranteed here. You may need to rerun the leader election protocol again. However, safety is guaranteed because of the use of quorums. So that concludes our discussion of election in Google Chubby and in Zookeeper. Next, we'll discuss in the next lecture another classical algorithm called the bully algorithm. In this lecture, we're going to discuss another classical algorithm called the bully algorithm. In the bully algorithm, all the processes know the other processes' IDs, and when a process finds that the coordinator or the leader has failed, it can find this via the failure detector. If the process knows that it is the process with the next highest ID after the leader, it elects itself as the new leader, and it sends a coordinator message to all the processes that have lower identifiers than itself. At this point, the election is completed. This is why this is called a bully algorithm. Essentially, if you know that the bully has crashed the highest ID process and that you're the next highest ID process, then you become the new bully and you tell everyone else with a lower ID that in fact you are the new leader and the new bully in the system. However, if you know that you are not the next highest ID process in the system, then you can't be the bully. You initiate an election by sending an election message. Whom do you send an election message to? You send election messages to only those processes that have a higher ID than yourself. Essentially, you're trying to ask these processes, hey, are you guys still alive? Are you guys willing to be the leader, or should I become the new leader? If none of these processes responds within a timeout, then this initiator becomes a new leader by becoming the bully, and it sends a coordinator message to all lower ID processes. At this point, the election is completed. However, if an answer is received within a timeout called an OK message, then there is some non-faulty process with a higher ID, and so this process needs to wait for the coordinator message. Once again, if it does not receive a coordinator message within a timeout, it starts a new election run. What does the process do when it receives an election message? Now, remember that an election message is always received from a lower ID process. When an election message is received from a lower ID process, essentially the lower ID process is saying, hey, the leader has crashed. Here's a new election run being started. Should I be the new leader? And you need to tell the lower ID process, you need to bully the lower ID process into not becoming the leader by sending it an OK message. An OK message would suppress the lower ID initiator, and it would make it wait for you. When you receive an election message, if this is the first election message you're seeing, you would need to start your own leader election by sending election messages to processes that have a higher ID than you. And the protocol continues until the highest ID process is elected as the leader. So let's see an example of this. Again, we have a system of 6 processes. N80 was the old leader, it crashed, and say N6 is the lucky one in the group who has detected the failure of N80. What it does is that it realizes that it is not the next highest ID process in the group, and so it needs to send an election message to all the processes that have higher ID than itself, which are essentially N80, the failed process. Yes, it does send a message to the failed process as well. It sends an election message to N32 and also to N12. When N32 and N12 receive these messages, they know that they are in fact alive, and so they send back an OK message to N6, which then waits for the final coordinator message. In turn, N12 and N32 also start election messages of their own by sending election messages to their higher ID processes. So N12 sends election messages to N32 and to N80, and N32 sends an election message to N80. When N32 receives N12's election message, it sends back an OK, and this suppresses N12 and makes it wait. N32 would time out waiting for N80's reply because N80 after all has failed, and it would now know that it is the new leader. It then sends a coordinator message to all the lower ID processes in the system, which essentially is all the other processes that are alive in the system, and at this point of time the election is completed. N32 is a new leader and everyone else knows about this leader. So you could also have failures that happen during the election run. So N32 might fail after it has sent the election message, but before it sends the coordinator message. And at this point of time, N12 and N6 need to do something about it. Right, so essentially what happens is that N6 or N12 would time out waiting for N32's response, and then it would start a new election run, which would send a message to N12, which would then start another election run by itself, and eventually N12 would get elected as a new leader in this particular case. If N12 also were to fail, then N6 would also time out waiting for N12's reply after N12's OK message, and then it would start the new election, and then it would time out, and then it would finally become the leader in the group. So if failures stop in the system, eventually you do elect a leader, but if failures keep happening, then you may never ever elect a leader. But how do you set these timeouts? How long do processes wait? Well, how long processes wait really depends on the worst case time to complete election. The worst case time turns out to be 5 message transmission times if there are no failures during the run. And you can set your timeout to be this. Why is it 5 message transmission times? Well, consider the worst case, which happens if the election is started from the lowest ID server in the group. So the lowest ID process in the group initiates later election. Once it sends the election messages out, it receives OK messages. So the answer that the lowest ID initiator gets from the second highest ID process, the would-be leader, takes another message transmission time. So that's step 2. Next, you have the election message from the second highest ID server that goes out to the highest ID process, which is in fact the failed leader. That's the third message transmission time. Then the second highest ID process waits for the highest ID process to respond, and there's a timeout for that as well. That's the fourth message transmission time. And then finally, when the second highest ID process realizes that it in fact is the new leader, it then sends a coordinator message to everyone. That's another message transmission time. Those who have looked at this for a while may realize that the steps 2 and 3 can in fact be commingled and done parallelly, where you can send OK messages to the lower ID processes alongside and parallelly with the election message that you send to the higher ID processes. And so in fact you can reduce this to be just 4 message transmission times if you so wish. So the worst case completion time is 5 message transmission times. That determines the timeout. What about the number of messages that are sent during this worst case? The worst case happens when the process with the lowest ID in the system detects a failure. It sends election messages to all its higher ID processes, and all the n-1 processes in the system start an election protocol by themselves. Right? So this means that the number of election messages sent out by the ith highest ID process is I-1. And so you have a total number of election messages in the system that is equal to n-1 plus n-2 plus so on and so forth, all the way plus 1. Okay, there's a number of OK messages that is equal to each value of this minus 1, because the highest ID failed leader does not respond. But essentially, the number of total messages is order of this value. This turns out to be n-1 times n divided by 2, which is order n squared. So the worst case message complexity is fairly bad. It's quadratic, but at least you have a short turnaround time for the protocol to complete. Well, that's the worst case. What about the best case? The best case happens when the second highest ID process in fact is the one that detects a leader failure. It immediately knows that it is the next highest ID process in the group and is a new leader. It simply sends out coordinator messages to the remaining n-2 processes with a lower ID than itself, and so the completion time is just 1 message transmission time, and the total number of messages involved is n-2 messages. So what about the impossibility here? It seems like this protocol might actually solve a consensus. However, since timeouts are built into the protocol itself, this means that the protocol may never terminate because liveness is not guaranteed. But it doesn't guarantee liveness in the asynchronous system where the message delays may be unpredictable and processes may be arbitrarily slow. However, in the synchronous system model, where processes have a maximum time to take an instruction a step, and there is a maximum upper bound on how long a message takes to be transmitted, you can actually calculate the worst case one-way latency as the worst case processing time for the instructions plus the worst case one-way message latency. Using these, you can set your timeouts to be the worst case values, and in fact you can guarantee liveness in this way in the synchronous system using the bully election protocol. To wrap up our discussion of leader election, election is an important component of many cloud computing systems today. We have discussed two classical leader election protocols, ring-based and bully, but they are failure prone because after all, leader election is related to consensus, which turns out to be impossible to solve in an asynchronous system. Many systems in industries such as Google Chubby, as well as Apache Zookeeper, which is an open source system, use Paxos-like approaches or quorum-like approaches in order to do elections, which guarantee safety. They may not guarantee liveness, but they guarantee eventual liveness. If things go right in the system in terms of message losses and failures, then the election succeeds and everyone knows about the unique leader that is elected in the group. Hi there. In this next series of lectures, we'll be looking at another important distributed computing problem. This problem is called mutual exclusion. Just to motivate the problem, here is an example scenario. Suppose your bank, where you store all of your money, runs its servers in the cloud. Now, say two of your customers are trying to make deposits into your company's account, and the deposits are both $10,000. The customers make these deposits simultaneously, each from a separate bank branch or from a separate ATM. Here's the set of operations executed by the two ATMs, which we'll call as the clients. Each ATM reads the initial amount, say it's $1,000, that's the balance of your bank account, from the bank's cloud server. Then each ATM adds $10,000, the amount to be deposited, to this amount, which makes it $11,000, and then each of these ATMs writes back the final amount to the server. So the server in the end is storing a value of $11,000. What really went wrong? Well, you should have been storing $21,000 at the end of it, not $11,000. So essentially you ended up losing one of the $10,000 because your clients, the ATMs, did not have mutually exclusive access to your account. If you had allowed only one client at a time to access the bank account object that represents your bank balance, then you would have guaranteed mutually exclusive access, and you would have had a balance of $21,000 at the end of this particular series of operations. So this is an example where mutual exclusion is important, where you need mutually exclusive access to a given object. In general, you need mutually exclusive access to a piece of code. In this case, the piece of code would have been the piece of code that fetches your bank balance, adds the deposit amount, and then sends the final bank balance back. If at most one client is allowed to execute in that piece of code at any point of time, then correctness would have been maintained in this particular scenario. There are other situations where mutual exclusion is important and critical. In distributed file systems, clients typically need to lock files and or directories, and in this sort of a scenario, you need mutual exclusion where at most one client is allowed to access a file at any given point of time. In general, accessing objects in any distributed system, distributed object store, is a scenario which requires mutual exclusion so that at most one server is granted access to the object. Coordination across servers is another example of a situation requiring mutual exclusion so that you can partition the work across servers and the servers can coordinate using locks. In industry, mutual exclusion is fairly widely used. Chubby is one of the core systems underlying several of Google's internal systems. We'll see Chubby in a little bit of detail later on in this lecture series. Also, many cloud computing stacks that are based on open source use Apache Zookeeper for coordination among servers. So what is the problem sort of formally? The mutual exclusion problem is also called as the critical section problem. The critical section is a piece of code which is available at all processes, but for which we need to ensure that there is at most one process executing inside that piece of code at any point of time. So each process has that piece of code in its own code, But whenever one process is inside that piece of code, the critical section code, no other process should be inside its own critical section piece of code. So essentially, this is the mutual exclusion problem. Now, the way we define an API for this problem is via essentially two main functions. They are the enter function and the exit function. The enter function is called by a process before it enters a critical section. When the process exits from the enter function, then it can enter the critical section. It can call a function like access resource that runs the critical section code. Then once the process is done with the critical section, it needs to signal in some way to the other processes that it is done, so that the next waiting process can enter the critical section. And so when a process is done with the critical section, it calls exit to exit the critical section. Here's our example from the bank scenario earlier. Here are the two ATMs. The ATM on the left is the ATM 1 and the ATM on the right is the ATM 2. And both ATMs are running identical codes, and that's the beauty of mutual exclusion, that the programs being run at the different clients could in fact be identical to each other. So let's see what one of the ATMs does. So ATM 2 does the following. ATM 1 does the same thing. First, it enters the critical section. Then it accesses the resource where it obtains a bank balance, it adds in the deposit, and then it updates the bank amount. Finally, it calls exit on the critical section, and at this point of time, it's done. So if you ensure that at most one ATM is executing the critical section in between the enter and the exit, then you're guaranteed that first either ATM 1 goes and enters its deposit, and then ATM 2 goes, or the reverse happens where ATM 2 goes first and then ATM 1 goes next. And in either case, you're going to end up with the correct bank balance of $21,000 rather than $11,000. So there are several approaches to solving mutual exclusion. Some of the most basic approaches arise when all the processes are running inside one operating system on a machine or inside a virtual machine. In this case, there are several abstractions that are provided by operating systems or their libraries. These include semaphores, mutexes, condition variables, and monitors. So when you're talking of a distributed system, however, where processes are communicating by exchanging messages, you can no longer use these abstractions that we talked about on the previous slide, because essentially those abstractions on the previous slide, they need some amount of shared variables among the processes, which is not possible in a message passing distributed system. So you need essentially three important properties for any mutual exclusion solution. They are safety, liveness, and ordering. Safety, essentially, once again, just to remind you, safety is a property that nothing bad ever happens. And in this case, the bad thing would be two or more processes in the critical section simultaneously. So safety would be that, would say that at most one process is in the critical section at any point of time. Liveness, once again, informally speaking, is the guarantee that something good happens eventually. In this mutual exclusion problem, liveness would be the guarantee that when a client wants to access a critical section, that access or that request is granted eventually. These two are essential properties, safety and liveness. There is also a desirable third property called ordering, which says that when multiple clients request access to the same critical section, these requests are granted in the order that they were made. And of course, there are many different kinds of ordering that we can talk about, and you'll see those different kinds of ordering as we discuss the different solutions that exist to mutual exclusion. So before we jump into the distributed version of the mutual exclusion problem, let's look at how the basic solution works in the case where processes are sharing an OS, and so they can actually share variables such as semaphores. So what is a semaphore? A semaphore, informally said, is an integer that can only be accessed via two special functions. It's a shared variable, so multiple processes can be sharing this variable. So the semaphore S in this particular slide is initialized to 1, and this means that 1 is the maximum number of allowed processes that are allowed inside the critical section. The two operations possible on the semaphore are wait and signal. Wait is often called as P or as down. Signal is often called as V or up. The P and V come from Dutch words that were associated with the original semaphore invention. Semaphores, of course, the word semaphore itself is, of course, an English word that's been in the dictionary for many centuries, Essentially, semaphores were used in the old days to communicate from one hilltop to another by burning a fire or beating a drum. And here in computer science, essentially, we are abstracting that out into code and using the same concept, but for mutual exclusion in an operating system. So let's look at what the wait function does. Essentially, the wait function is what a process would call before it enters a critical section. The wait function enters a while loop. In the while loop, there is another if statement, and the entire execution of the while loop, one execution of the while loop is atomic, which means that when a process is executing this particular piece of code, no other process can preempt this process on the processor. So for instance, if the process executes the if statement and the s minus minus statement, and then it's preempted by the scheduler when another process runs, that's not allowed. Once a process enters one execution of the while statement, it should complete that execution of the while statement before it is preempted. So what does each execution of the while statement do? Well, it only checks if the value of the integer s is greater than 0. If it is, then it decrements it by 1, and then it breaks from the while loop, in which case the process can then enter the critical section. So essentially, if there is only one process accessing the critical section, then it would enter the while loop and immediately break out when the value of s would be 0. If another process came along and wanted to enter the same critical section, it would call wait s, and it would essentially get stuck in this while loop. It would get stuck until the first process exited the critical section, when it called signal. Exiting process would call signal, which would simply increment the value of s by 1. Once again, this incrementing is again an atomic operation, this is the system must ensure that this is executed completely, and it's not executed in a way where the processor fetches a value of s and then gets preempted, the process gets preempted before the new value of s, the incremented value of s, can be written back to the memory. So at that point of time, the value of s is again 1, and the next execution of the while loop at the second waiting process will break out, and the second waiting process can now enter the critical section. So these atomic operations of the statement in the while loop and also the s++ operation in the signal operation are provided typically via hardware instructions, such as compare and swap, test and set, and there are several other variants in different architectures. Most hardware platforms and processors provide such instructions so that semaphores and other mutual exclusion variables can be implemented easily in the OS. So essentially, the wait would be the enter function and the signal would be the exit function. So in the example of the bank, if the ATM1 and ATM2 were on the same operating system as each other, then the code would look as follows. They would share the semaphore variable s, which would be initialized to 1. Then before entering the critical section, each ATM would call wait s, and then after being done with the critical section, each ATM would then call signal on s. So that was where processes share and can share variables in a single operating system, but in a distributed system where processes communicate by exchanging messages, these solutions will not work. So in the next lecture, we'll see a solution to the distributed mutual exclusion problem. Hi there. So in this lecture, we'll start looking at the solutions to the mutual exclusion problem in the distributed setting. So once again, before solving any problem, you need to make sure that you know what the system model is under which you're solving the problem. So here are the assumptions in our system model here. Each pair of processes that is connected by reliable channels, which means that when you send messages on these channels, they are delivered eventually. We can use TCP for these channels. The channels are all point-to-point channels, which means that they have one sender and one receiver. Messages along a channel are delivered eventually to the recipient, and they're delivered in first in, first out order, which means that if one message is sent before the second message, then the first message is received before the second message as well. And finally, we'll assume that processes do not fail. There are many variants of the algorithms that we'll discuss, all the algorithms that we'll discuss, that are fault-tolerant variants, and these are present in the literature. So our first solution is a central solution. This uses a central master or a leader, which is elected using one of our leader election algorithms that you have seen elsewhere in the course. The master keeps a queue of waiting requests from processes who wish to enter the critical section. The master also has a special message called the token message. Access to the token message allows the holder to access the critical section. So the token message is a very special message. It's like cash. If you have it, then you can use it, whether you're a good person or whether you're a thief. So when a process wants to access the critical section, it calls the enter function, where it sends a request to the master, and then it just waits in a loop for the token from the master. When the process receives a token, it enters the critical section and hangs on to the token. When it's done with the critical section, it calls the exit function, wherein it simply sends a token back to the master. What data structures does the master maintain, and what does it do? Well, when the master receives a request from a process PI, if the master currently has the token, it simply sends a token to PI, which gives PI access to the critical section. If the master does not have the token, this means that some other process has the token, and in this case, the master ends up queuing the PI request alongside other requests that may also be waiting. When the other process that has access to the critical section releases the token, this token is received back at the master, and the master then looks at its queue. If the queue is not empty, it takes the head of the queue, some process PJ whose request was sent and queued there, and this process PJ is then sent the token, which gives it access. Okay. Notice that this process PJ's request will be removed from the queue after it's sent the token. However, if the queue is empty, this means that there are no outstanding requests, and the master can then hang on to the token at this point of time. So let's analyze this algorithm. So why does this algorithm guarantee safety? It guarantees safety because it is exactly one token, and only access to the token gets you access to the critical section. Why does it guarantee liveness? Liveness is guaranteed if every request is granted eventually. This is guaranteed because there are at most n processes in the system, and so if your request is queued at the master, there's going to be at most n-1 requests ahead of you. So when each of these requests finishes, because there are no failures, eventually when your turn comes at the head of the queue, you will get access to the token and the critical section. The ordering guaranteed here is FIFO in the order received at the master. So if your request came in slightly earlier than your friend's request at the master, then you will get access to the critical section just before your friend's request. So those are correctness properties. What about performance properties? There are two requirements from mutual exclusion algorithms. One is that they involve few messages, which means that they're incurring lower overhead on the network itself. And second is that they incur low delays at the clients that access the critical section. This means that the overhead of accessing critical sections and releasing them is fairly low. There are three metrics that capture these. The first is bandwidth, which is simply the total number of messages sent in the enter and exit functions. The client delay and synchronization delay are as follows. The client delay is a delay incurred by a process when there is currently no other process in the critical section. Okay? Which means that right now there is no one in the critical section. One process comes along and says, hey, I need access to the critical section. How long does it take that process to get into the critical section? The synchronization delay is the delay between one process releasing the critical section, that is calling the exit function, and the next waiting process getting access to the critical section. Okay, so we assume that there is only one releasing process, and of course, and there is only one waiting process for the synchronization delay. So let's analyze the central algorithm for these. Bandwidth, once again, for the enter operation only involves the requesting process sending a request to the master, and it receives a token back. So that's two total messages, no matter when these messages happen, but that's two total messages. For the exit, the requesting process or the process in the critical section simply sends a token back to the master, so that's one message for the exit. For the client delay, the master has a token because there is no one in the critical section, and the requesting process sends a request to the master, which sends it back the token, so that's two message latencies or one round trip time. Synchronization delay, the process in the critical section exits the critical section by sending the token to the master, so that's one message transmission. Then the master sends the token forward to the next process in the queue, which is another message transmission, so that's two message latencies for the synchronization delay in the central algorithm. So the master, of course, here is the performance bottleneck because it could get overloaded with a lot of requests. And also if the master fails, then you have a single point of failure, which means that until a new master is elected, you cannot serve any more mutual exclusion requests. So our next algorithm tries to address this by eliminating the master altogether and instead using a ring. Here we organize all the processes in the system into a virtual ring, where each process can talk to its successor in the ring. Typically, this is a clockwise successor. So for instance, N3 is a process, its successor is N32. It can send messages to N32. N32 is another process in the ring which can then send messages to its successor N5, and so on and so forth, and the ring loops around. We have a special message called the token message, shown as a blue message here on the slide. The process that has the token message at any point of time can enter the critical section. No other process can enter the critical section. So N3 currently has access to the critical section. It, if it chooses so, can access the critical section at this point of time. When it's done, it can pass on the token to its successor in the ring. At this point of time, no one can access the critical section anywhere in the group because the token is in transit, it's on the network. When N32 receives the token, it can then access the critical section. If it's not interested, it simply passes on the token to its successor. So once again, we have N processes in a virtual ring. Each process can send a message to its successor in the ring. There is exactly one token in the ring. In order to enter a critical section, you simply wait until you get the token. There is nothing you can do to actively seek out the token. When you're done with the critical, when you're in the critical section, you hang on to the token. When you're done with the critical section, you simply pass on the token to your successor in the ring. If you get the token and you're not interested in the critical section, meaning that you're not in the enter function, then you simply pass on the token immediately to your successor in the ring. So why does this guarantee safety? Well, there is exactly one token, and for the same reasons as in the central mutual exclusion algorithm, safety is guaranteed here. Liveness is guaranteed because there is a finite number of processes in the ring, and the token eventually loops around and reaches the requesting process. This, of course, assumes no failures, which means that the token is not lost and that the ring stays intact. Bandwidth per enter operation, there is only one token message received by the requesting process. However, the other n-1 processes might have to put an effort in transmitting the token around. So the total number of messages per request might be as high as n throughout the system. There is, of course, just one message per exit operation where the process passes on the token to its successor in the ring. What about performance? Let's look at client delay. Client delay means that there is currently no one in the critical section, and suddenly one process comes up and says, aha, I need access to the critical section. The best case is when this process already has access to the token, in which case the number of message transmissions is 0. The worst case is when this process that just requested access to the critical section has just passed on the token to its neighbor or to its successor. In this case, the token now needs to make its way around the other n-1 processes, because in a system of n processes in a ring, you have n links. This means n message transmissions for the token to come around, and that's the worst case. So the client delay could be anywhere between 0 to n message transmissions. What about synchronization delay? Synchronization delay means that one process releases the token and one other process somewhere in the ring is waiting for the token. The best case is just one message transmission where the waiting process is the successor of the releasing process, which means that the token makes only one hop before it gives access to the critical section. The worst case is when the process that is waiting is the predecessor of the process that is releasing the token. In this case, the token needs to make its way around the ring in the clockwise manner to reach the requesting process. And that's n-1 message transmissions in a system of n processes in the ring. Okay, so the synchronization delay could be anywhere between 1 to n-1 message transmissions. So we solved somewhat the bottleneck problem with the central mutual exclusion algorithm, but the client delay and the synchronization delay have gone up to be order n in the ring-based approach. The question is, can we do better than this? Can we lower this client and synchronization delay further? And the answer we'll see in the next lecture. In this lecture, we look at a classical algorithm to the distributed mutual exclusion problem. This algorithm is called the Ricart-Agrawala's algorithm. Once again, before solving any problem, just remind yourself of the system model. Once again, we assume that each pair of processes that is connected by a channel has the channel be reliable. So if you send messages on the channel, they are eventually delivered, and they're delivered in first in, first out order. We also assume that processes do not fail. So Ricart-Agrawala's algorithm is a classical mutual exclusion algorithm for distributed systems. It was published in the 1980s. It was invented by Glenn Ricart from the National Institutes of Health and Ashok Agrawala from the University of Maryland. Unlike the previous algorithms you have seen for mutual exclusion, the central and ring-based algorithms, there is no token involved here. Instead, this algorithm uses notions of causality, and it uses multicast inside the group. It has a lower waiting time to enter the critical section than the ring-based approach. So here is the key idea, and then we'll see an example of the Ricart-Agrawala algorithm. When a process PI wants to enter the critical section, it multicasts a request to all the other processes. The request includes the process ID, PI of course, but it also includes the current lamport timestamp. This is the causal or logical timestamp at process PI. Once PI has sent this multicast request, it waits until all the other n-1 processes have responded positively to the request. When it receives n-1 replies, it can then enter the critical section. Requests in this system are granted in the order of causality. The PI in the request t comma PI is used to break ties, because two different processes might have concurrent requests which might in fact end up having the same timestamp. You need to have a way to break ties, and the ID of the processes is used to break ties. Okay, so here are all the messages in the Ricart-Agrawala algorithm and all the actions in their gory detail, and then we'll see an example over the next few slides. When a process PI wants to enter the critical section, it first sets its state to be wanted. It then multicasts the request to all processes. The request simply consists of the lamport timestamp at PI currently, followed by PI's ID. So that's TI comma PI. It then waits until all the n-1 other processes have sent back a reply message. Once it has received these n-1 replies, it then changes its state to be held, and it can now enter the critical section. What does the process do when it receives a request? So when a process PI receives a request from PJ, which is tagged as TJ comma PJ, TJ being the timestamp of the request, lamport timestamp, and PJ being the requester's ID, the PI process first checks if its state is held. If its state is held, then essentially it cannot send back a reply immediately, because this means that PI currently is in the critical section. In this case, PI would add the request to a local queue of waiting requests. On the other hand, if PI's state is wanted, which means that PI has currently another request for the critical section that has not yet been granted, then PI checks whether or not the timestamp of PI's own request is less than the timestamp of the incoming request. Okay, in order to do this, it first compares the lamport timestamps, TI and TJ. If TI is less than TJ, then this less than or equal to condition succeeds. If TI equals TJ, in which case the requests were concurrent, then it breaks ties by considering whether I is less than J. If this condition is true, which means that PI's own request has precedence over PJ's request, in this case also PI would queue PJ's request. However, if none of these conditions is true, then PI sends a reply back to PJ. When a process is done with the critical section at process PI, it simply changes its state to released, and it sends a reply to all of its queued requests. Now notice that when the process is in the critical section, it may receive multiple requests from multiple other processes for the critical section. It would end up queuing all of these requests. When it is done with this critical section, it would send back a reply to all of them saying, hey, I'm done with my critical section. I'm ready to acknowledge all of you as ready to enter the critical section. That's essentially the algorithm code. So let's see an example. Here is again a system of 6 processes, N3, N32, N5, N80, N6, and N12. N32 first sends a request message which has a timestamp of 102 along with the N32's own ID of 32. This is multicast out to the other n-1 processes in the system. All of them send back reply messages because none of them are waiting to access the critical section. N32 state is now held, meaning that it is currently entered in the critical section. Now let's make it slightly more complex. Suppose two other processes, N12 and N80, also want to access the critical section. Notice that N32 is currently also in the critical section. Its state continues to be held. However, for each of N12 and N80, the state now becomes wanted because these are trying to enter the critical section. N12's request has a timestamp of 115, and N80's request has a LAMPO timestamp of 110. So let's see what happens now. The next thing that happens is that these requests are received at some processes in the system. Specifically, N6, N3, and N5 receive both of the requests from N12 and N80. And because N3, N6, and N5 are not waiting to enter the critical section, they send back replies to whoever they receive requests from. At this point of time, N12 and N80 each have 3 reply messages back, but they are waiting for 2 other reply messages. The next thing that happens in the system is that N32 receives these requests from N12 and N80 one after another. Because N32 state is now held, it queues both of these requests, both the timestamp as well as the IDs. So N12's request 115,12 is queued, followed by N80's request 110,80. The order of queuing here doesn't really matter because the replies are sent to the entire queue. Notice here that N12 and N80's requests to each other are still in transit. So one of them is going to get the request first. And you might think, well, whoever gets the request first is likely to win the race or maybe lose out the race. But in fact, causality comes to our rescue here. So let's say N12's request is received first at N80. N80 receives this request. Its state is wanted. So it checks whether or not the incoming request has a lower timestamp than it. It sees that the incoming request has a timestamp of 115, which is higher than N80's own request, and so N80 ends up queuing the incoming request. Okay, since the incoming request is queued, which means that N80 would not have sent a response or a reply message back to N12. N12 is going to end up waiting for N80's reply message. Next, N80's reply message is received at N12, which then is in the wanted state, and it checks whether the incoming request has a lower timestamp than it. And in fact, this is true because the incoming request has a timestamp of 110, while N12's waiting request has a timestamp of 115. In this case, N12 will respond back with a response message or a reply message back to N80. At this point of time, N80 has 4 responses back or replies back from the group. N12 has 3 responses back to the group, and N32 is currently in the critical section. N32 then will release the critical section. Once it is done with the critical section, releases a token, sends back reply messages to N12 and N80. And at this point of time, N80 has 5 reply messages back, and it can enter the critical section. N12 cannot enter the critical section yet because it does not have a reply back from N80. It only has 4 replies. And this is fine because N80 is queuing the request from N12. When N80 is done with this critical section, it will then send a reply back to N12, which will then enter the critical section after that. Why is the Ricart-Agrawala's algorithm safe? Let's look at the proof a little bit, informally at least. 2 processes Pi and Pj cannot both have access to the critical section simultaneously. Because if they did, then both would have sent a reply message to each other, and this would have meant that in the case of one of them, Ti, I is less than Tj, j, and this is why Pj would have given permission to Pi, would have responded with a reply to Pi. And also it must be true that Tj, j is less than Ti, I, and in this case Pi would have given a reply to Pj. But both of these are not possible together. You cannot have 2 less than 3 and also 3 less than 2. That's not possible. So that's the crux of the proof. Now, of course, there is an exception which some of you might think about, which is that it's possible that Ti, I is less than Tj, j, and Pi has already replied to Pj's request with a positive reply, and only after that does Pi generate its own request. And at this point of time, it seems like Pj will also respond to Pi's request with a positive reply, and both Pi and Pj might have access to the critical section. So essentially, Pi gives Pj permission, then Pi generates a request, and because now Pi's request has a lower timestamp than Pj's, Pj will also give a permission to Pi. However, this cannot occur because once Pi has received Pj's request, any request that it generates subsequently, based on LAMPO timestamps, based on causality, will have a higher timestamp. Therefore, it must be true that Ti is greater than Tj. This follows directly from the use of LAMPO timestamps. This is where the use of Lampo timestamps really plays into the correctness and the safety of the Ricart-Agrawala algorithm. And so Ti greater than Tj is a contradiction to what we had assumed, which is that Ta comma I is less than Tj comma j. And so this situation cannot arise either. Next, liveness. Liveness is true because in the worst case, a process ends up waiting for all the other n-1 processes to send reply. And once they send a reply, which will happen, the other n-1 processes might all be in the critical section, and this process might be the very last. And when that happens, when this process is given permission, then it will be able to enter the critical section. Finally, ordering here is guaranteed in the sense that requests with lower Lampo timestamps are granted earlier. And again, if there is a conflict in timestamps, then the process ID is used to break ties. But in any case, if one process generates a request with a lower timestamp than another process, then that first process will get its request satisfied earlier than the second process. And so even though we have done better in the client synchronization delay compared to the ring-based approach, the bandwidth has gone up. And the question now is, can we do better in both of these cases? We'll see that in the next lecture. In this lecture, we are going to discuss another classical algorithm for distributed mutual exclusion, and we'll also wrap up our discussion of the mutual exclusion topic. The Ricart-Agrawala algorithm that you've seen already for mutual exclusion requires replies from all the processes in the group, which is one of the reasons that it has a high bandwidth. It has a bandwidth that is order n. The key idea in the Maekawa's algorithm, the new algorithm, is that you need to get replies from only some processes in the group, not all the processes, but only some. But you also need to ensure that only one process is given access to the critical section at any point of time, which means that safety is guaranteed. So Maekawa's algorithm works as follows. Each process Pi is associated with a voting set called Vi. The voting set consists of a few other processes from the group. Each process must belong to its own voting set Vi. Now the voting set is not all the other processes in the group, which is essentially the approach of the Ricart-Agrawala algorithm, but the voting set is only a small subset of the group. However, you need to make sure that given any two voting sets Vi and Vj of processes Pi and Pj respectively, the intersection of these two voting sets is non-empty, which means that there is at least one process that belongs to both Vi as well as Vj. So given any pair of voting sets, Vi and Vj, you need to make sure that at least one process is in common between those two voting sets. This might sound familiar to you. In fact, it is the same concept or the same idea as quorums, which you have seen elsewhere in the course. However, here the usage of this is slightly different, of course. Now, each voting set is of size k, so all the voting sets are of similar size, and each process contributes by belonging to m other voting sets, including, of course, its own. Maekawa showed that the values of k equals m equals square root of n work best. We'll see a calculation later on in this lecture which calculates why square root of n is a good value. One way of assigning voting sets so that they're always intersecting in any pair of voting sets, and so that you get order square root of n voting set sizes, is to put all the n processes in a square root of n by square root of n matrix. And wherever a process falls in the matrix, you consider that the processes column, and you also consider that processes row, and all the processes in the column and in the row are together. The union of them is considered to be the voting set of that process at the intersection of that row and the column. So this would result in a voting set size that is 2 times square root of n minus 1, which is still order of square root of n. So let's see an example. So suppose I have 4 processes in the system. Of course, this is a perfect square, so we can put them in a matrix as shown here, P1, P2, P3, P4. And if we select a process's row and column as its voting set, then we get voting sets as shown on the left side of the slide. So consider P1, the process P1, its row consists of the process P1 and P2, and its column consists of the process P1 and P3. So its voting set consists of those 3 processes, P1, P2, and P3, as shown by this circle over here. Similarly, V2, which is the voting set for P2, consists of the processes P1, P2, and P4, and so on and so forth. You'll notice that any pair of processes intersect in at least one, in many cases 2, of the processes in the system. So consider V1 and V4. They intersect in two processes, P2 and P3 in the system. So let's see how these voting sets are used then. So first of all, each process requests permission from only its voting set members, not from all. And this is one way in which the Maekawa's algorithm differs from the Ricart-Agrawala algorithm that we've seen previously in the course. Second, each process that is in the voting set gives permission to at most one process at a time. And again, this is different from the Ricart and Agrawala algorithm, where a process may have given permission to multiple, perhaps all the other processes in the group. Okay, so these are two key differences. Anyway, let's look at how the algorithm actually works. So first, initially the state of a given process, and again we describe the algorithm by describing what happens at a given process. The state of a given process is released, which means that currently it is not holding the lock, or it's not in the critical section. Also, its state for voted is false, meaning that it has not yet voted for any other process to get access to the critical section. Now, when this process PI wants to enter the critical section, it first sets its state to be wanted, meaning it wants to enter the critical section. Then it multicasts a request message to all the processes in its own voting set VI. Notice that this voting set VI also includes itself. So when PI itself receives its own request, it will have to process it. And I'll describe how this processing is done in the next slide. Then the process, after sending out this request message, it waits for a reply or a vote message from all the processes in its own voting set, and that includes a vote from itself. When it has all these votes, it can then set its state to be held and then proceed into the critical section. What happens when a process is done with the critical section? Well, the first thing it does is that it sets its state to be released, again meaning that it's done with the critical section, and then it multicasts a release message to all the processes in its own voting set VI. This is not all that there is to the protocol. Now, when a process PI receives a request from PJ, first it checks if its own state is held, meaning it currently is holding is in the critical section, or if it has voted in the past, meaning its voted variable is true. If either of these conditions is true, then it queues this new request because it means that someone else is in the critical section. Otherwise, it sends a reply or a vote back to PJ, and it sets its voted variable to be true, indicating that it has recently voted. Now, when a process PI receives a release message from process PJ, recall from the previous slide that a release message is received when PJ has just exited the critical section and informs all its voting set members that it has exited the critical section. PI looks at its queue of waiting requests. Remember that PI may be in not just PJ's voting set, but also in the voting set of other processes, and these other processes may be waiting for a vote from PI. But if PI's queue is empty, it means that PI doesn't have any outstanding requests, and so it sets its voted variable to be false and it exits at that point of time. However, if there is something in the queue, then it dequeues the head of the queue, say a process PK. Remember that this means that PK's voting set contains PI, and that PK has previously sent a request to PI which has been queued, and the queuing happened here in the past, right at the top of the slide over here. That's where the queuing happened. And in this case, the entry for PK is dequeued, and a reply message is sent to PK, meaning that PI now has voted for PK to enter the critical section, and so PI sets its voted variable to be true. So why does this algorithm guarantee safety? Well, when a process PI receives replies from all its voting set members VI, including itself, no other process PJ could have received replies from all its voting set members VJ, because VJ would have had intersection with VI in at least one process PK, and PK could have sent only one reply or vote at a time, and it already sent the vote to PI, which means that it could not have voted for PJ as well. Okay, so this means that safety is guaranteed by the Maekawa algorithm. For liveness, a process needs to wait for at most n-1 other processes to finish the critical section, and you might think this guarantees liveness. However, Maekawa's algorithm has a subtle behavior in its original form that can actually violate liveness because it can result in a deadlock. Here is an example of a deadlock. Again, in our example of 4 processes P1, P2, P3, P4, suppose all the 4 processes request access to the critical section. P1 gets some replies but is waiting for P3's reply. P3 in turn is waiting for P4's reply, which is in its voting set. P4 is waiting for P2's reply, and P2 in turn is waiting for P1's reply. Now we've completed a cycle or a circle among these processes, and this is called a deadlock. There is not going to be any more progress in the system because these processes are going to be waiting for these replies forever. So the original Maekawa's algorithm, as we've discussed it, is deadlock prone, and these deadlocks can occur. There are, of course, variants of Maekawa's algorithms that have been published that address this issue and that are free from deadlocks. Returning to the original Maekawa's algorithm, let's analyze its performance. The bandwidth involved in entering the critical section is square root of n messages that you send out to your voting set members, and then square root of n replies that you receive back, so that's 2 times square root of n messages. Per exit operation, you're simply sending a reply message to all your voting set members, so that's just square root of n messages. These numbers are better than Ricart-Agrawala's algorithms, which had bandwidths of order n. You might think square root of n is still a large number. It's not constant for sure, but it can be fairly small. So if n is 1,000,000, for instance, then the square root of n value is about 1,000, which is a fairly small number. What about the delays? Well, for the client delay, when no one has access to the critical section, a process comes up and says, hey, I need access to the critical section. It sends out a request to all of its voting set members. That's one message transmission because all these messages are in parallel. And then the responses are received back also in parallel. That's another message latency in the backwards direction. So that's one round trip time. Synchronization delay means that one process is currently in the critical section and one of the processes is waiting to get in. And at this point of time, the releasing process will send a reply message back to the process PK, which is the common process between the two voting sets of the releasing and the waiting process. Then that PK process, which is in common, will forward a vote to the waiting process, which can now enter the critical section. So that's 2 message transmission times, one from the releasing process to the common intersection voting member, and then from the voting member to the waiting process. So why is the square root of n the right size for the voting sets in Maekawa's algorithm? Once again, each voting set is of size k. Each process belongs to m other voting sets. Now the total number of voting set members is k times n, because each of the n processes has k members in its voting set, and so k times n is the total number of voting set members. Of course, because the voting sets overlap and intersect, processes may be repeated in this k times n, but each process belongs to exactly m voting sets, so k times n divided by m should be equal to n, because each process appears exactly m times in this k times n. So k times n divided by m should equal n, and if you evaluate this by cancelling n out on both sides, you get that k equals m, which means that the size of the voting set should equal the number of voting sets that each process is in. Okay, so let's have that equation and hold it to the side. Now consider a process pi, right? So the number of voting sets that are there in the system is equal to pi's own voting set, so that's the +1 over here. There are k members in pi's voting set, right? There are k processes, and each of those processes has their own voting set, right? So that's the total number of voting sets that is there in the system. Because each of these k voting set members of pi is involved in m total voting sets, but one of them is pi's own voting set, so the remaining voting sets are simply m minus 1 times k. Okay, so that's the total number of voting sets present in the system. However, the number of voting sets should equal the number of processes in the system, so we have n equaling this value. Now we substitute in the value of m equals k from the earlier equation, and you get n equals k minus 1 times k plus 1. Solving this, you'll see that k equals about a square root of n, give or take a little bit. And this explains why k equals m equals square root of n is the optimal value for minimizing the overhead of k. So in order to minimize k, we set n to be equal to m minus 1 times k plus 1, and then we use the earlier equation k equals m to give us k equals square root of n. Now, the Maekawa's algorithm, of course, does not handle failures. Neither does the ring-based or the centralized algorithm or the Ricart-Agrawala algorithm. Of course, there are fault-tolerant versions of all of these algorithms that exist out there in the literature. Other ways to handle failures include Paxos-like approaches to handle failures. Google's system called Chubby, which is used for locking, is a fairly popular way to handle failures while doing mutual exclusion inside of Google's stack. So Chubby is a system used underneath Google's storage systems such as Bigtable and Megastore. Chubby has not been open source, but the technical details and the design of Chubby has been published in a paper by Google, and that's what we're going to discuss in very brief detail in this slide and the next. Chubby provides only advisory locks. This means that clients must ensure that they access the lock before they access the the critical resource or the object itself. So if clients forget to access the log, then hey, then mutual exclusion may be violated. So this is why this is known as advisory logs. So Chubby, of course, uses a cluster of servers. There are 5 servers by default in the Chubby cell. One of the servers is marked as a master. Again, this is elected using one of the leader election protocols that we have studied before. In this particular figure, server D is a master. Chubby allows clients to not only do locking but also write small configuration files. And Chubby relies on the Paxos consensus algorithm. Chubby again is a group of servers with one elected as the master. The other servers in the group, the non-master servers, are just slaves. They replicate the same information as the master. When a client wants to read one of these small configuration files or the lock file, it sends a read request to the master, which can serve it locally. Okay, so the master serves all the requests locally. When a client wants to write, however, it sends a write request to the master, which then forwards it to all the servers in the group. It then gets a majority of them to respond back to the master. When a majority of them respond back, you reach a quorum in the system. Then the master can send back a response to the client acknowledging that the write has been done. Okay, so this is where mutual exclusion comes into play. If some other client has already gotten access to the critical section, it means that it has permissions from at least a quorum of the servers via the master, and the next request that goes to the master will not reach a quorum, and it will wait until that first process exits its critical section. Now you could have failures here. If you have failures at the master, if the master fails, then you simply rerun the election protocol to elect a new master. If a replica fails, you simply replace it or it reboots by itself, and then have the new replica catch up with the other servers in the group or with the master itself. So Chubby presents a fault-tolerant way of not just doing mutual exclusion in a distributed system, but also to maintain small configuration files, which reflects the ways in which Chubby is used inside of Google's stacks. Wrapping up our discussion of mutual exclusion, it is a very important problem in cloud computing systems. There are a variety of classical algorithms. We have discussed 4, the central, the ring-based, the Ricart-Agrawala algorithm, and the Maekawa algorithm. They're not all fault tolerant, but they are fairly efficient, and they all try to guarantee safety and liveness. And as we have progressed down from central to Maekawa, the algorithms have gotten better and better in terms of performance. Industry uses a variety of systems for coordination and for mutual exclusion. These include Chubby at Google, which is used for locking and also to maintain small configuration files, and also Apache Zookeeper, which is an open source system that is used for coordination. And I encourage you to look up Apache Zookeeper on the web. Cloud systems and distributed systems involve many thousands to millions of servers interacting with each other and also interacting with clients. When you have large numbers of clients accessing the same data at servers, there is a risk of race conditions where data is inconsistent. To combat this, we will study concurrency control techniques that coordinate different clients accessing the same data. Then when you have multiple servers that are replicating data amongst one another for fault tolerance or for load balancing, we need to have replication control where these different replicas or copies of the same data are consistent with each other. And we'll study that also in this week. Again, these are 2 very important topics and concepts that are used in cloud storage and transaction systems today. I also want to remind that for those of you doing the programming assignment for C3 Part 2, this assignment requires you to understand and use both concurrency control and replication control. So please pay specific attention to this week's, the second week's lectures on concurrency control and replication control. You will be able to reuse many of these concepts as you build your programming assignment. This assignment, the programming assignment, also uses concepts that you have learned from C3 Part 1. This includes the key value and NoSQL storage systems. And if you have not seen that, or if you have forgotten what that was about, I encourage you to please go back and look at those lectures from C3 Part 1 again. In the topic of concurrency control, which the next lecture series focuses on, one of the most important building blocks is RPCs. So in this lecture, we'll see what an RPC is and how RPCs are implemented in systems today. So RPC stands for Remote Procedure Call, and it was proposed by Birrell and Nelson in the early 1980s. They wrote a paper about it, but it's not just limited to a paper. It's an important abstraction that is implemented in many distributed systems today and most cloud computing systems, if not all. RPCs are an important abstraction that allow processes to call functions in other processes. So if you have one function in a process P1, another function in a process P2, normally you would not be able to call one function from the other, but RPCs allow you to do this. As a result, the RPCs enable code reuse. So if someone writes, for instance, a library for a special data structure, then you can call the functions of that library by using RPCs. RPCs stand for Remote Procedure Call. They have a counterpart in object-based systems known as RMIs, which stands for Remote Method Invocation, where one method is called from another method. So before we discuss what an RPC is, we need to discuss what a local procedure call is, or an LPC is. In a local procedure call, you have a calling function and a call function, and both these functions share the same address space. They lie within the same process. This means that the stack of that process, because the process has only one stack, the stack can be used to pass arguments from the calling function to the call function. When the call function is done, it can then pass the return values back along the stack again. Also, because these functions share the same process address space, they can access common objects, example via pointers if you're using C, or by reference, for instance, if you're using Java. Now, LPC or local procedure calls have exactly one semantics. This means that as long as the process which contains the two functions does not crash, the call function will be executed exactly once, not 0 times, not more than 1 time, but exactly 1 time. And this is important to discuss here because when we discuss RPCs, you'll see that the semantics may be slightly different. So what is an RPC, or a remote procedure call? While an LPC, a local procedure call, had both the calling and the call function within the same process, in an RPC, the caller and the callee functions are in different processes. This means that the function call from one function to another crosses a process boundary. It goes from one process into another. This means that you need to access objects via global references. You cannot use pointers anymore. Pointers essentially refer to virtual memory addresses within that process's address space. An address of, say, 1234 in process P1 may refer to something completely different, a different object in process P2's address space. So you can't really use pointers as is to access objects across process boundaries because the address spaces are different. And so you need to have global references if you want to access objects. For instance, a global reference may be the IP and port number of the process containing the object, along with the object number itself. This uniquely identifies the object, and this allows functions to pass essentially global references to other functions. You have RPC, and similarly you have RMI, or remote method invocation, in object-based settings where the caller method and the callee method are in different process address spaces. So vectorially, you have a process P1, it has a main function, it has two other functions, F1 and F2. If main calls F1, that's an LPC, or a local procedure call. F1 might then call F2, which again is an LPC, or a local procedure call. These are LPCs because they stay within the same process address space. They use the process stack. However, if I have a second process P2, which has its own address space, and that has another function F2, then this function F2 may be called by the F1 function in process P1. That would be an RPC, or a remote procedure call. Both these processes might reside on the same host, in which case it's still a remote procedure call. Notice that the remote procedure call here does not cross host boundaries. It stays within the same host, but because it crosses process boundaries, because it crosses over from process P1 into another process P2, it is still an RPC. Or the two processes might be on different hosts, in which case you might need messages that go over the network. One message carries the request, which is essentially carrying the arguments of the call itself. That's the RPC request message. And when the RPC is done, the RPC reply message is then carried back to the calling process P1. So what about the semantics? So we discussed exactly one semantics for LPCs, and we would really desire those for RPCs as well. However, they turn out to be very hard to guarantee in RPCs, primarily because networks, as you know, are failure prone. The request call message might be dropped, or the return message might be dropped. The difference between these two is that in one case, the call function was never executed, in the first case, where the request message was dropped. In the second case, where the reply message was dropped, it was executed. However, from the calling process viewpoint, these two scenarios are indistinguishable. All it knows is that it does not hear a reply back. Also, other failure modes could happen. For instance, the called process might fail before executing the called function, or the call process might fail after executing the called function. These cases are generally very hard to distinguish by the caller function or the caller process, and so that's what leads to a little bit of ambiguity in terms of semantics. Also, the network might be duplicating messages. So if the request message is duplicated, this means that the called function might be executed multiple times, and you might have more than one execution. So RPCs typically support three flavors of semantics. At most one semantics, which is supported by the Java RMI system. At least one semantics, which is supported, for instance, by the Sun RPC system, and maybe semantics which are supported by the Corba system. So these names mean exactly what they say. At most once means that you're guaranteed that a called function will be executed either 0 or 1 times, no more than 1 time. At least once says that a called function will be executed at least 1 time, but not 0 times eventually. And maybe it doesn't really give you any guarantees. It's essentially a best effort kind of behavior. How do you implement these? Well, let's look at different ways to implement this. So there are 3 different design decisions that you can make in order to implement these different flavors. First, if the calling function does not hear back a response, say within a timeout, it might want to retransmit the request. Second, on the call function side, if you hear a duplicate request, a request that you have already seen before, do you simply filter it out, or do you again pass it on just like another request? And third, when you receive a duplicate request, do you re-execute the function, the call function, or do you simply retransmit the old reply? Okay. So if you retransmit the request, that's the first column we're looking at, first row we're looking at here. If you retransmit the request, but you do not filter duplicates, and you simply re-execute the procedure, this guarantees that if the both the caller and the callee are alive, then eventually at least one request will make it across, and it will be executed at least 1 time. Okay, because you're re-executing the procedure here, you're not guaranteed that it will be executed exactly once, but you are guaranteed that eventually at least one execution will happen if things go right. Let's look at the second row. If you retransmit the request but you filter out duplicate requests, which means that you don't re-execute the procedure but you simply retransmit the reply, then this guarantees that eventually, when messages do make it across from the caller to the callee, this function will be executed, but it will be executed at most once. You're not guaranteed that it will be ever executed because you're not guaranteed that things will ever go right in the network, but if they do, then it will be executed at most once, but no more than 1 time because you're filtering out duplicates and not re-executing the procedure. Finally, if you don't retransmit the request and you really don't do anything on the callee side either, then this leads to maybe semantics. So these are the 3 flavors of semantics that are implemented in RPCs. Some kinds of operations, known as idempotent operations, can be repeated multiple times without having any side effects. Some examples of such operations include x equals 1. Whether you execute this operation 1 time, twice, or 1,000,000 times, the end result is the same. X is set to 1. There are no side effects. Similarly, if an RPC call is provided an argument y, which has the same value for each invocation, and if x is set to y, then the end result is the same, whether this RPC is executed once, twice, or 10 times. There are no side effects. Some examples of operations that are not idempotent are increment operations, similarly decrement operations. For an increment operation, if executed once, then x is incremented by 1, but if you call it multiple times, then x might be incremented multiple times, and so it has side effects. So this is not an idempotent operation. Similarly, multiplying x by 2 is an operation that has different results whether it is executed once or twice or some multiple number of times. Why are we discussing this? Well, idempotent operations are useful to be used with at least one semantics. If you have an idempotent operation that is inside an RPC, or rather, if an RPC consists of only idempotent operations, if the entire RPC is idempotent, then an RPC called semantics, that is an at least one semantics, plays well with such an RPC. You can implement at least one semantics, and no matter how many times the RPC is called, the end result will be the same without having any side effects. So how do you implement these RPCs? So here's an architecture of how RPCs are typically implemented. On the caller process, we call that the client. There is a client stub. There is also a communication module. On the callee process, also called the server, there is a communication module, there is a dispatcher, a server stub, and then the final callee function itself. Really, what we want to have is for the caller function to be able to make a call to the callee function, and then the reply or the response or the return values to be returned back. And so as you notice here, the caller actually calls the client stub, which then passes on the request to the communication module, which then communicates with the communication module on the server side, and then that talks to the dispatcher, and then the server stub, and then the callee, and then the response is passed back along the reverse path. So what are all these modules? Let's look at them one by one. The client stub has the same function signature as the callee. Okay, so we're talking of this function down here. So the signature or the interface of this function is the same as the client stub. This is nice because it allows the caller to call the callee function just like it was a local function. The caller does not need to know that the callee function is not residing in process P1. It is calling a function that just looks like a process that looks like the callee function. Think of a clone that essentially looks like you but is empty inside. But when someone tells something to the clone, it immediately relays the message to you. Okay, that's the client stub. The communication module is responsible simply for request reply messages. So it simply forwards the requests and replies to appropriate hosts, both from the client side and also on the server side. On the server side, you have the dispatcher. When the dispatcher receives a request from its communication module, it then needs to select the server stub, the appropriate server stub to forward the request to. And the server stub will then call the callee. And then when the callee is done, it returns the return values via P2's local stack to the server stub itself, which then transmits it back via the dispatcher all the way back to the caller itself. Okay, so now the dispatcher is needed because there might be multiple callee functions at process P2 that are being called by different clients at different parts of the system, and so you need the dispatcher to decide which callee function to call. The server stub is needed on a per callee function basis so that the callee function has someone to return the return values to via its local stack. How do you generate the code for these? Well, do you write the code for all of these components? Well, the answer is no. The programmer only needs to write code for the caller function and the callee function. Everything else in between is generated automatically. Typically, these are generated automatically from the function signatures or object interfaces if you're using object-based languages. For instance, in the Sun RPC system, there is a language called the Sun XDR, which is used for representing interfaces. So when you write RPCs in Sun RPC system, you would specify the signatures of those functions in Sun XDR. Then the Sun XDR system will use these to generate code automatically for all the components except the caller and the callee function. So the client stub, the remote communication module, the dispatcher, and the server-side stub all are generated automatically from just the interface definitions and the signatures of these functions. All of these components form a part of the middleware system. So Corba, which is Common Object Request Brokerage Architecture, is an example of a middleware system that supports RPCs, and the Sun RPC and the Java RMI are other middleware systems as well. Now, there is an important topic when you discuss RPCs, which is known as marshalling. Marshalling is needed because different architectures use different ways of representing data. And yet you want to be able to make RPCs across these different platforms. So for instance, you might have an Intel architecture running the caller function process, and an IBM Z architecture running the callee function process. And you want to be able to allow RPCs to happen across these two different architectures. However, these architectures use different ways of representing data, typically, especially integers. There are two popular ways of representing data or storing data in the architecture. They are known as big endian and little endian. These terms come from Jonathan Swift's famous novel called Gulliver's Travels, where Gulliver travels to the land of Lilliput, and the land of Lilliput has small inhabitants, really tiny inhabitants, and they fight wars. There are two nations in the land of Lilliput where they fight wars based on whether they should break an egg from the little endian side or from the big endian side, and that's where the number comes from. where these names come from. So the big endian architectures would store numbers as follows. If you have a hex number that is 12AC33, then it would store 12 in the lowest address, then AC in the next higher address, and then 33 in the highest address. Okay, if you have longer integers, they are stored in the order shown here. So the IBM Z architecture, the System 360, all of these use big endian format. The little endian format is the reverse. So a hex 12 AC33 is stored with the 33 byte in the lowest address, then AC in the next highest address, and then 12. Okay, here we are using byte level addressing. Intel architectures, for instance, follow the little endian architectures. This is why a lot of Windows machines tend to be little endian here. So this means that the caller process uses its own platform dependent way of storing data, and the callee process does the same as well. And the middleware is responsible for translating between these two. The middleware typically has a common data representation format. This is the platform independent format that is chosen only by the middleware. We call this as the CDR. And the marshalling is the process of the caller process converting the arguments of the request message into the CDR format. So it takes the arguments which are stored in its own platform dependent format and converts it into the platform independent format that's specified by the middleware. This is the process of marshalling. Then it can be packaged into the request message and then sent over to the server side or the callee side. The callee process, on the other hand, extracts the arguments from the message and converts it into its own platform dependent format. Otherwise, it would not be able to pass it to the callee function itself. Okay, this process of extracting the platform independent format into the platform dependent format is known as unmarshalling. Okay, so this is the reverse. Similarly, when the callee function is done, it would marshal its return values into the reply message, and then the caller function would then unmarshal the reply values from the response message itself. So now that we know RPCs as a building block, we can use them to understand the concept known as transactions, and that's what we'll do in the next lecture. In this lecture, we are going to see what transactions are and what are some of the challenges in them. So essentially, a transaction is a series of operations executed by a client on one side and a server on the other side, where each of the operations in this series is an RPC. However, RPCs have semantics, of course. As you have studied, RPCs have at least once, at most once, or other semantics. Transactions have a special requirement too, and this requirement is an all or nothing requirement. Essentially, this means that when a transaction completes, it has one of two choices. One, either it commits all its operations on the server side, which means that any of the updates that the transaction did, which means the client did during that transaction, are all reflected on the server side objects. So all of the operations need to be reflected. The other choice is that the transaction aborts, which essentially means that none of the updates are reflected on the server side. It's as if the server had never seen the transaction at all. So essentially, the transaction can do whatever it wants during its execution, but when it comes time to commit, the transaction has one of two choices: either commit and reflect everything on the server side, or abort and reflect nothing. Transaction before we discuss more about transactions. Here is an example of a sample transaction that might be done from a client that is trying to book a ticket on a flight to a server that is maintaining records of flights and how many seats are there. So if you notice here, the first operation here is on the client side. This entire thing is a transaction. Of course, the first operation is that the client gets a transaction ID by calling open transaction, which is also an RPC from the client side to the server side. Next, it gets the flight availability of a particular flight run by airline ABC, flight number 123 on a particular date. Server.getFlightAvailability. This is an RPC. This value is an integer and is stored in X. If X is greater than 0, meaning that there is at least one seat available on this flight, then it makes an update to that flight by booking a ticket. This is another RPC. This changes the server state. So this is essentially a write or an update to the server state. This value is stored in Y. This is maybe the ticket confirmation or something, and then once again a write is done where a write is written to the server side, where a seat preference and an IL preference is communicated to the server side. Once this is done, now it comes crunch time, where a closed transaction is called by the transaction, and at this point the transaction must either commit all these operations or abort all of them. In other words, the server must at the end of this transaction either have seen all the operations in that order or none of them at all. So for our purposes, some of these operations will be classified as reads and writes. The first operation, where we got flight availability, where none of the server state was changed, is a read operation from an object, where in this case the object is the flight on that particular date. The next two operations, where you book the ticket as well as you put an IL preference, are both write operations or update operations, because they change something on the server side. They change server state. Okay, so it's essentially these write operations that we are most concerned about. We want all these writes to be reflected on the server side, or none of them to be reflected at all at the end of the transaction. So transactions have, as I mentioned before, some requirements. The most important requirement is the atomicity requirement, which is an all or nothing principle. This means that a transaction should either complete successfully, so its effects are recorded completely on all server-side objects, or the transaction has none of its effects recorded on the server-side objects. It's as if the transaction had never executed at all. The second requirement comes from the fact that there might be multiple clients accessing the server. Imagine, there might be thousands of or hundreds of people trying to book seats on the same flight. So there are multiple clients and multiple transactions that are concurrently trying to access the same set of objects on the server side. They are all concurrently communicating with the server side. So we also need isolation among transactions. In other words, we want a transaction to be indivisible from the point of view of other transactions. This all or nothing principle, which we talked about from the server side, must also be true from one transaction to another. This means that one transaction cannot have access to the intermediate results or states of other transactions. Also, a transaction must be free from interference from operations of other transactions. Okay, so this is the isolation principle, where essentially, even though the transactions are executing concurrently, the net result, the end result as far as the server state is concerned, at the end of all of those transactions, is as if the transactions had executed one transaction at a time. They did not interfere with each other. They did not read each other's partial results or intermediate results. So why is this challenging? Well, first of all, the biggest challenge is that clients may crash. The servers may also crash, and this means that we need to have a way that preserves atomicity and isolation in spite of failures in the system. Second, transactions could run concurrently. So one easy way of assuring isolation, for instance, is to let the server execute only one transaction at a time. But this severely limits the number of transactions that you can execute concurrently. Transactions per second is a very important metric for most systems, so that they can maximize their revenue. So whether it's a banking service running on a bunch of bank servers, or whether it's an airline reservation service running on a bunch of servers, you want to maximize the transactions per second, because that maximizes revenue. It reduces the latency for the clients. So you want to allow as much concurrency as possible. You want to allow as many transactions to execute concurrently as possible, and this is somewhat at odds with the isolation principle. So you want to preserve isolation while still maximizing the transactions per second. And so this series of lectures, Concurrency Control, will look at this problem. How do you preserve isolation and atomicity and all the other requirements of transactions while still increasing the level of concurrency? Later on, we will see what happens when you replicate objects on the server side, when you have objects distributed out across multiple servers on the server side. Okay, so that we'll see later on when we discuss replication control. So atomicity and isolation are not the only two requirements from transactions. Essentially, the requirements from transactions are very nicely captured in an acronym known as ACID. ACID stands for atomicity, consistency, isolation, and durability. Atomicity says the all or nothing principle, which we talked about. Consistency says that if the server starts in a consistent state, the transaction must end the server in a consistent state. For instance, for a banking transaction, if you're transferring money from one bank account of yours to another, you want the total of those two bank accounts to be the same at the end of the transaction. That's an example of consistency. Isolation, as we talked about before, says that each transaction must be performed without interference from other transactions, meaning that non-final or intermediate or partial results of a transaction are not visible to other transactions. And finally, durability. When a transaction does commit and reflects its updates on the server side, these updates must be held for eternity. No matter what happens on the server side, these updates must not be lost at all. They must be saved in permanent storage. So why is this challenging at all? Well, it becomes challenging when you have multiple clients and one server. We are not considering replication on the server side or distributed servers. There's only one server machine. But we have multiple clients, each client executing a separate transaction with that server. So let's see a couple of examples of what could go wrong. The first thing that goes wrong when you don't care for isolation, when you don't do anything special about isolation, is a lost update problem. Here's an example of two transactions. The transactions are identical in code, but the way in which the transactions are shown shows an interleaving of the operations of the two transactions. So let's look at one of these transactions, say transaction T1. T1 gets the number of seats in a particular flight, ABC123. That is stored into a local variable x, local at that client. If x is greater than 1, then x is decremented by 1, and the value of x is written to the server object ABC123. Then the transaction tries to commit. Transaction T2 is identical. It has identical operations in the same order, but transaction T2 starts slightly after transaction T1, and so some of its operations are slightly delayed compared to the T1 counterpart. So let's see what happens if this particular interleaving, as is shown in this slide, where transaction T1 executes its first operation first, then transaction T2 goes next with its first two operations, and then transaction T1 goes with its next three operations, and so on and so forth. With this interleaving where time goes from top to bottom, let's see what could go wrong. So let's say initially the server has 10 seats available on this flight. So when transaction T1 reads the number of seats from ABC1 to 3, the local variable at x is set to 10. Notice that this local variable x is a local variable at transaction T1, and this local variable x is a local variable at transaction T2. So consider two separate processes, each with their own address spaces. Each has its own variables, and so these two x's, x in T1 and x in T2 are not related. They're in completely different address spaces. So anyway, returning to our example, next when x gets T2 gets x, stores into x, it also gets a value of 10 because at the server side the number of seats has not changed. Now next what happens is that because the transaction T1 sees that x is greater than 1, it decrements x by 1 and stores the resulting value 10 minus 1 or 9 into ABC1 to 3. At this point the server side is reflecting a new value of 9. Okay. However, T2 is still working with its old value of x equals 10, and so it decrements x by 1 to 9, and it also stores that resulting value 9 into the server side. Now essentially, say the two transactions commit, what happens is that on the server side the resultant number of seats is stored as 9 rather than 8. Instead of having two different transactions, each of which booked one seat each, we have had two transactions, each of which booked one seat each, but on the server side only one of those seats was reflected. Okay, so this is what is known as the lost update problem. Either one of T2's or T1's updates is lost in this particular example. Okay, and the reason this happens is because we didn't really make any effort at preserving the asset properties. Another example of what could go wrong is here. This is known as the inconsistent retrieval problem. Here again I have two transactions. These two transactions are different, and I'm showing an interleaving order for them. Let's see each of these transactions. So transaction T1, the one on the left, first gets seats from a flight ABC1 to 3, then gets seats from a different flight ABC789, stores them in variables x and y respectively. Again, x and y are local variables at T1. Then it transfers 5 seats from ABC1 to 3 to ABC789. It does so by simply writing x minus 5 to ABC1 to 3 and writing y plus 5 into ABC789, and then it commits. In the meantime, concurrently, transaction T2 is trying to add up or sum up the total number of seats available on these two flights. So it gets a number of seats from ABC1 to 3, stores it into x, a local variable at T2. Similarly, it gets ABC789 and stores it into y, a local variable at T2. It adds both of them and prints out the resultant value. So let's see what could go wrong. So at the server, say initially the number of seats available on ABC1 to 3 is 10 and ABC789 is 15. Okay, so really transaction T2 should output a total value of 10 plus 15 or 25 seats at the end of this. That's the value that we would expect, right? But let's see what really happens. So First, when transaction T1 executes its first three operations, it gets the values of 10 and 15. Then it writes the value of 10 minus 5 or 5 into ABC123. At this point, on the server side, ABC123 is 5. Now transaction T2 executes its get seats on ABC123 and it gets x equals 5 because that's what is the value on the server side. It gets y equals 15. That's unchanged from before. And when it adds these two, it prints out a total value of 20. Okay, so what really got lost in translation here was this 5, which was in transit in a sense in transaction T1, but transaction T2 read the partial results or the intermediate results or the dirty update. This write done by T1 was an intermediate result that was read by T2, and that is what led to the wrong result of 20, where the result should really have been 25. So this is what is known as an inconsistent retrieval problem, and this also arises because we didn't do anything special here to guarantee ACID properties. In the next lecture, we'll see mechanisms that prevent transactions from affecting each other and that try to guarantee ACID properties when you have concurrent transactions and many concurrent transactions executing with one server. Okay, with this lecture, we are going to start discussing how to let transactions satisfy the ACID properties. And so one of the first concepts we're going to discuss is known as serial equivalence. So there are concurrent transactions where multiple clients are executing transactions with the same server, and we need to prevent transactions from affecting each other. One of the simplest ways of achieving this is to just allow one client at a time to execute a transaction with the server. So a client comes in, acquires a lock on the server, for instance, and then executes its transaction. And then once it's done, the second client comes in, and so on and so forth. So this works as far as correctness is concerned, but it's pretty bad as far as performance is concerned. It reduces the number of transactions that are executing concurrently. And this is important because you want to allow more transactions to execute concurrently, because this increases the transactions per second metric. The higher the transactions per second you can support, the higher is the revenue of the company. For instance, if a flight booking website had a very low transactions per second, clients would just not use it because it would be a very slow system that would not be able to support more than one user at one time. And so you want to allow more concurrency. You want to maximize this metric, but at the same time, you also want to make sure that your system is correct. In other words, it maintains the ACID properties. Okay, and so that is the challenge overall in concurrency control. How do you increase the level of concurrency? How do you increase transactions per second? How do you allow more transactions and more transactions to execute concurrently while still not violating the ACID properties for transactions? So therein comes the concept of serial equivalence, an interleaving of a transaction operation. Say you have two transactions and their operations are interleaved in a particular order. This is the actual order in which the operations occurred in the server itself. That particular interleaving is said to be serially equivalent if and only if the following conditions are true. There is some other ordering of those transaction operations. So this is the original interleaving. Maybe there is a different interleaving that looks like this. We call that interleaving as O prime, which gives the same end result as the original interleaving O. This means that the original interleaving O left the server objects in a particular state, and the fake make-believe O prime ordering that we have also leaves the server objects in exactly the same state. So they are indistinguishable from that viewpoint. But in this new ordering O prime, you have the transaction operations such that all the operations of any given transaction are consecutively, meaning they are together in this interleaving. This means that essentially the interleaving O prime, the fake make-believe interleaving, has each transaction execute one at a time. So a transaction comes in, it executes its operations in a batch, and then the next transaction comes in, it executes its operations in a batch, and so on and so forth. Because essentially we are saying that an interleaving O, which happened in real life, is serially equivalent if there is a parallel world in which if transactions had executed one transaction at a time, then the end result, as far as the servers are concerned, would have been the same as this original interleaving O. Okay, so even though the transactions overlapped and even interfered and interleaved with each other, the end result is the same as if the transactions are executed serially, one transaction at a time. Okay? So the key here is that you are not able to distinguish the end results of the two, and so the interleaving is still serially equivalent, even though it's not actually serial. So how do you check for serial equivalence? Now an operation has an effect on the server if the operation is a write, and so the server object is then updated. The operation has an effect on the client, the return value, if the operation is a read. Okay, so we call these two as the effects of the operation, depending on whether it's a write or a read. Now two operations are said to be conflicting operations if their combined effect depends on the order in which they're executed. In other words, swapping their order will give you a different end result as far as the servers or the clients are concerned. For instance, if I have a read operation on an object X and a write operation on the same object X, for instance being executed by two different transactions, their ordering is going to make a difference. If the write came first, then the read will read this newly written value. However, the read came first, then it would read the old written value, and so their effect, the combined effect of these two operations really depends on the order in which they are executed. Similarly, a write and a read on the same variable, which is essentially symmetric as a read and a write. Also, a write and a write are conflicting because whichever write comes second, that value is going to stay for a while. Okay, that's the overriding value. However, two reads on the same object are not conflicting because as long as these are the only two operations we're talking about, the order in which they occur, whether the second read comes before the first read or whether the first read comes before the second read, it doesn't really matter. The end result is the same. The individual clients will get the same read value. Okay, so swapping them doesn't really make a difference, and so they are not conflicting operations. Also, operations on two different objects, X and Y, whether they're read or a write, are non-conflicting. Here we are assuming their objects are of course independent of each other, but in that case the operations of them are not conflicting because essentially objects don't interfere with each other. They are independent objects in and of themselves. So now that we know what conflicting operations are, we can say what the conditions are under which two transactions are serially equivalent. Okay, so given two transactions and a particular order of interleaving, that order of interleaving is said to be serially equivalent if and only if all pairs of conflicting operations where the pair contains one operation from each transaction is executed in the same transaction order for all the objects that the transactions access. So what this is saying is the following. Suppose I have two transactions, T1 and T2. I take a particular interleaving. I'm going to take all pairs of conflicting operations where one part of the pair comes from T1, the other part comes from T2. If the T1 part of the pair was executed first in that particular interleaving, then I'm going to mark that that pair as T1, T2, okay, because the T1 part occurred first. However, if the T2 part of that pair occurred first in that interleaving, then I'm going to mark that as T2, T1. You mark all the pairs of conflicting operations with either T1, T2 or T2, T1 in this way. And then at the end, all these pairs should be marked as either all T1, T2s or all T2, T1s. If either of these two conditions is true, then this particular interleaving is serially equivalent. Okay, essentially, we're saying that it is equivalent to the case where if it's all T1, T2s, then it's equivalent to the case where the fake make-believe scenario where T1 executed completely first and then T2 executed. If there are some pairs which have T1, T2 and other pairs that have T2, T1, then these two transactions, or rather their interleaving, is not serially equivalent. So we need to see this in action. So let's go back to the two problems we discussed in the previous lecture, which were giving us trouble. The first is the lost update problem. Here, two transactions T1 and T2 were simultaneously trying to update a given variable, and one of their updates was getting lost, and instead of the seats going down from 10 to 8, it was only going down from 10 to 9. Okay, so what are all the conflicting operations here? Remember that a conflicting operation pair has to be a read-write or a write-write pair on the same object. So here's one example of a conflicting operation. Transaction T1 writes to the object ABC123, and transaction T2 reads from the object ABC123. Okay, so it gets seats. So this is a read-write pair on the same object ABC123. So that's a conflicting operation pair, and this operation pair has the T2 part of its pair occurring first in this particular interleaving, and so we mark that as a T2, T1 pair. Okay, So are there other conflicting operation pairs? Well, here's another conflicting operation pair, a write-write pair on the same object ABC123. Okay, so again here you have the T1 part of the pair occurring first, and so we mark this as T1 comma T2. There is another pair of conflicting operations, which is the get seats or a read on ABC123 by T1 and the write on ABC123 by T2. And once again, this is a read-write pair on the same object ABC123, and the T1 part of the pair occurs first, so we mark that as T1 T2. Here in this interleaving, you'll notice that there is one conflicting operation pair that has a T2 T1 tag, and another one, in fact two more, that have a T1 T2 tag, and that is why this particular interleaving is not serially equivalent. And so serial equivalence, or serial equivalence using the notion of conflicting operations, catches the lost update problem in this way. What about the other problem that we discussed, the inconsistent retrieval problem? Here again, if you remember, T1 was transferring 5 seats from one flight to another, and T2 was trying to sum up the total number of seats, and it was reading partial results. So here, what are the conflicting operations? You notice that there is a lot of reads from these two objects ABC123 and ABC789, and again a lot of reads. These are not conflicting with each other because they are only read-read pairs even on the same objects. But you do have some conflicting pairs. The write on ABC123 and the read on ABC123 are conflicting. So the T1 part, the write, occurs first in this interleaving, so we mark that conflicting pair as T1 comma T2. And once again, the write to ABC789 and the read from ABC789 from T1 and T2 respectively are conflicting pairs because this is a write-read pair. And here the T2 part of the pair occurs first, and so we mark that as a T2 comma T1 pair. And so obviously now you have two pairs of conflicting operations in this particular interleaving. The first being a write-read pair that's marked as T1 T2, the second being a write-read pair that is marked as T2 T1, and so this is not serially equivalent because we need all the conflicting operations marked as either T1 T2 or all are marked as T2 T1. Okay, so serial equivalence using the notion of conflicting operations also catches the inconsistent retrievals problem, as we have seen here. So what can we do about this? At the commit point of the transaction, what you do is that you check for serial equivalence using conflicting operations. You check for serial equivalence using all the other transactions in the system. You don't need to check really with all the other transactions. You only need to check with other transactions that overlapped with transaction T, transactions that had some overlapping with some of the operations of transaction T, either transactions that are already committed or transactions that are still going on. Okay, if you find that conflicting operations violate serial equivalence, for instance, if the conflicting operations violate serial equivalence and the other transaction involved is a transaction that is already committed, then you need to absolutely abort transaction T because you cannot undo a transaction that is already committed. Okay, because you need durability. You want to make sure that a transaction that is committed has its updates reflected forever in the database. In that case, you would abort the transaction T. However, if the other transaction involved is a different transaction that is not yet committed, you might choose to abort that other transaction too. Okay, so the choice is up to you. No matter what you do, if you abort a transaction, you need to make sure that you roll back or undo any of the writes that T made to the server objects so that the nothing property of the all or nothing guarantee is enforced, and that T aborted and none of its updates were reflected on any of the server-side objects. But really, what we're noticing here is that transactions are aborting, and that means wasted work, right? So the question arises, can you prevent violations from occurring at all? In this lecture, we will see the first of two types of techniques that are used for concurrency control. In other words, to make sure that transactions satisfy the asset properties in spite of concurrency. So these two approaches are pessimistic concurrency control and optimistic concurrency control. Okay. So a pessimistic approach or pessimistic approaches assume the worst, and they prevent transactions from accessing the same object. So they prevent two transactions from accessing the same object altogether. An example of pessimistic that we'll discuss in more detail is locking. Optimistic approaches, on the other hand, assume the best, and they allow transactions to proceed as if there are no conflicts that are occurring and as if they would not interfere with each other. But at a later point of time, the optimistic approach checks whether or not the asset is satisfied, and if it's not, then it might lead to aborts. Okay, so multi-version and timestamp approaches, which we'll discuss later on, fall under the optimistic approaches. First pessimistic approach that we'll discuss is known as exclusive locking. Okay, this is the simplest and the easiest. Each object is associated with a lock, and at most one transaction can be inside a lock. When a transaction T wants to access an object O, either for reading or writing, it needs to make sure that it calls the lock of O function. And the lock of a function will block if there is at least one transaction inside the lock. When that transaction leaves the lock by calling unlock O, then another transaction is allowed in. Okay, this ensures that at most one transaction has access to the object O at any point of time. However, once a transaction T has locked an object O, it can then read and write the object O multiple times. It doesn't need to call lock every time. So it can lock the object once at its beginning and then do all its accesses and then unlock it at its end. This should sound familiar to you because this is very similar to the mutual exclusion problem and solution that we discussed earlier. In fact, you could use any of those techniques here to implement exclusive locking. Okay, but that's kind of orthogonal to what we are discussing here because we are the semantic level or the level of transactions over here. So once again, concurrency is important here because it means more transactions per second and it means more revenues for whichever is the company running the server side. And exclusive locking has the problem that it reduces concurrency. Essentially, you're only limiting transactions to read so that at most one transaction can read any object. In real life, workloads have a lot of read-only or read-mostly transactions where most of the operations are reads. And even there, the exclusive locking approach is limiting these transactions to read the objects only one transaction at a time. But this is kind of not required because reads can be done concurrently. As you've already seen, read-read conflicts on the same object are really not conflicts at all because they return the same values no matter what order they're executed in. So the hint again, or the key here as we go forward to the next approach, is that it's okay to allow two transactions to concurrently read an object because read-read is not a conflicting pair. But when writes come in, you need to be more careful. Okay, so that's the next approach, which allows two different types of locks on an object. Or rather, the lock on an object can be held in two different modes, the read mode or the write mode. As long as a transaction is holding an object in a read mode, other transactions can also hold the lock on their object in the same read mode, which means that multiple transactions can be allowed to be in the read mode. However, when any transaction is in the write mode, no other transaction can be allowed in either the read mode or the write mode. This means that this is an exclusive lock. So the operations executed are as follows. Before a transaction T reads an object O, suppose it wants to read an object O, it calls read lock on O. The transaction T is allowed in if all the other transactions that are inside the lock all are in the read mode currently. If any transaction is in a write mode, then T will have to wait. Now, what does the T do before it writes object O? So it calls write lock O. Once again, write lock succeeds, or the transaction T is allowed past it if and only if no other transaction is currently accessing the object O, meaning it has not locked object O. If T already holds a read lock on object O and it wants to now write object O, it can simply call write lock to promote its lock from the read mode to the write mode. Okay. Once again, this succeeds only if no other transactions are currently in the read mode or in the write mode. Okay, so both of these need to be true. Otherwise, the promotion will block and T will block. Okay. Well, finally, when unlock is called on the lock by a transaction T, it releases all locks no matter what modes they're in. So how do you guarantee serial equivalence with these locks? So that's the whole goal, right? We want to make sure that ACID properties are satisfied, and so they are of course satisfied when the serial equivalence is satisfied. But how do you ensure that serial equivalence is in fact satisfied? So two-phase locking is a very popular technique that's used to guarantee serial equivalence. Essentially, two-phase locking says that a transaction cannot acquire or promote any more locks after it has started releasing locks. Essentially, it says that the transaction has two phases: the growing phase where it only acquires or promotes locks, and then a shrinking phase where it starts releasing locks. And once it starts releasing locks, it cannot acquire or promote any more locks. Okay, so that's two-phase locking. You have a growing phase where you acquire or promote locks, and then once you're done with that, you have a shrinking phase where you release locks. When we're talking of phases, these are phases that would occur inside the transaction operations themselves. So each transaction has these phases while it's executing its operations. There's a variant of two-phase locking known as strict two-phase locking, where there is no shrinking phase. Instead, you release the locks only when you reach the commit point. Okay, so there is releasing of the locks occurs only at one point, at the commit point of the transaction. So why does two-phase locking, as we've discussed it, guarantee serial equivalence? Well, the proof is via contradiction, and here is the proof. Assume you have a two-phase locking system where serial equivalence is violated for two transactions T1 and T2. Because of the serial equivalence definition, it must be true that there is some object O1 where the conflicting operations in T1 and T2 are such that the tag on that conflicting pair is T1, T2. And there is some object O2, maybe the same object O1, maybe a different object, where the conflicting operation pair is the reverse, which is T2, T1. Now, because of the first T1, T2 pair, and because of the way the two-phase locking works, the shrinking phase, the growing phase first and then the shrinking phase, T1 must have released O1's lock in its shrinking phase, and then T2 acquired the lock after that, which means that T1's shrinking phase is either before or overlaps with T2's growing phase. Okay? That's just by definitions. But then using the same argument on B, we can argue that T2's shrinking phase is before or overlaps with T1's growing phase. Okay? However, this cannot be true because you can't have both of these statements be true, because the growing phase only occurs before the shrinking phase in each transaction. Okay? And that is the contradiction over here. So one of the downsides of locking is deadlocks, and so here's an example of a deadlock. So here are two transactions, T1 and T2. They are trying to do similar things but in slightly different order. So T1 is locking the object ABC 123, and then it's writing to it, and then it tries to lock object ABC 789. T2 on the other hand locks these objects in a different order. It locks ABC 789 first, and then it tries to lock ABC 123. And this is the interleaving of these two transactions. Essentially, at this point, transaction T1, when it's trying to lock ABC 789, it ends up waiting for transaction T2 to release its lock on 789. While here T2 ends up waiting for the lock on ABC 123, which is currently being held by T1. At this point, the transactions T1 and T2 are deadlocked. Each of them is waiting for the other. Okay, so this is shown by this wait for graph, where T1 is waiting for T2 to release the lock on object ABC 789. And T2 is waiting for T1 to release the lock on object ABC 123. Okay, this is an example of a deadlock where these transactions T1 and T2 will not make any more progress ever at all unless you do something about it. Okay, so deadlocks can happen in any system that uses a locking approach. So when do deadlocks occur? There are three necessary conditions for a deadlock to occur. When I say necessary, I mean that if there is a deadlock in the system, then these conditions are all definitely true. Okay. So these three conditions are as follows. Some objects are accessed in exclusive lock modes, which means that when a transaction accesses some objects, those objects are accessed so that no other transaction can access those objects. So these are exclusive lock modes. For instance, the write mode is an exclusive lock mode. Second condition is that a transaction holding a lock cannot be preempted. Okay, so a transaction doesn't necessarily just give up its locks just like that. And third, most importantly, there is a circular wait or cycle in the wait for graph that we have discussed. Okay, so we discussed a wait for graph for two transactions, but when you have thousands of transactions involved and transactions are waiting for each other to release locks, you can draw a wait for graph among these transactions. If there is a cycle in the wait for graph or a circle of directed edges, then you have a cycle and you have a deadlock in the system. So once again, these conditions are all necessary, which means that if there is a deadlock, then these conditions are definitely true. However, they're not sufficient. If these conditions are true, it doesn't guarantee that there is a deadlock. Okay? It doesn't mean there is definitely a deadlock. Okay? So the sufficiency is not true. The necessary is true. So how do you combat these deadlocks? Well, there is a few approaches. The first approach is lock timeout. When a transaction is not able to access a lock for a while, it times out and it aborts the transaction. This could be expensive, of course. It avoids deadlocks, of course, but it's expensive because transaction aborts might become very frequent, and timeouts might occur even when there is no deadlock, because the network might just be slow and transactions might be aborting just because they are facing timeouts because of a slow network. So a different approach is deadlock detection, where you allow deadlocks to happen, but you detect the deadlocks when they do happen. Essentially here you keep track of the wait for graph. For instance, you keep track of it via the global snapshot algorithm. You might recall the Chundy-Lamport algorithm, which we discussed at the very beginning of this course. And you could use that Chundy-Lamport algorithm, global snapshot algorithm, to capture the wait for graph and then detect cycles in it. Okay, for instance, you could do this periodically. If you do find a cycle, then you need to abort one or more transactions in that cycle to break that cycle and to ensure that there is no deadlock in the system. However, this still allows deadlocks to occur, so transactions might still end up waiting when they're in a deadlock before the next global snapshot algorithm is run and the cycle is broken. So a third approach that comes in is deadlock prevention, which completely prevents the deadlocks by violating one of the necessary conditions. Remember that we said necessary conditions, which means that these conditions are absolutely required for deadlocks to occur. So if you violate any one of the necessary conditions, just one of them is violated, that's sufficient for you to, that's enough for you to ensure that deadlock will not happen in the system. For instance, the first condition said that some objects are accessed in exclusive lock modes. This can be violated by ensuring, for instance, that all objects are accessed in read-only modes, meaning you don't have any exclusive locks. So in a database where where objects cannot be written at all, where objects can only be read, you can never have deadlocks because the first condition is violated, the first necessary condition is violated, and it's never true. Let's go to the next condition. Next condition says that transactions holding locks cannot be preempted. Well, you can allow transactions to be preempted or transactions to, for instance, timeout when they're waiting for locks. Again, this would prevent deadlocks from happening. The third condition says that there is a circular wait in the wait for graph. Okay, so this can be prevented by the following approach. There are many other approaches that can be used too to violate this condition, but here's one approach. A transaction locks all its objects in the beginning, so it knows all the objects that it's going to lock up front at its open transaction time, and it tries to lock all of them in the beginning. If all these locks succeed, then it proceeds, then the transaction proceeds. If at least one of these lock attempts fails, then the transaction aborts immediately. Okay, because in this approach, a transaction never waits for another transaction to release locks, because either you access all your locks or you don't. You never have any edges in your wait for graph, and so you don't have any cycles in your wait for graph, because if you don't have any edges, you don't have any cycles, and so this approach would end up preventing deadlocks as well. So we have discussed the pessimistic concurrency control approach, which uses locks, but it's still limiting, right? There are still times when some transactions are having to wait for other transactions if you still use locking. And so concurrency is still not as high as we would want it to be. And you can make it even higher by using optimistic concurrency control, which we'll discuss in the next lecture. In this lecture, we're going to discuss optimistic concurrency control, which tries to increase the level of concurrency or transactions per second compared to pessimistic concurrency control. And this is important because it improves the revenue, it improves the operations per second, and it lowers latency. Okay? And these are important even in non-transaction systems. So systems like Dropbox, Google Apps, Wikipedia, key value stores, Amazon's Dynamo, all of these, even though they don't support transactions necessarily, they prefer optimistic concurrency control approaches because it reduces latency and increases concurrency, meaning it improves operations per second. Optimistic concurrency control in general is preferable over pessimistic concurrency control when conflicts are expected to be rare. But when conflicts do occur, you need to make sure that they are caught and resolved if necessary. So the most basic approach to optimistic concurrency control is to just allow transactions. We're going to be discussing the transaction version of optimistic concurrency control. You just allow transactions and clients to read and write objects at will. When the transaction tries to commit, you check for serial equivalence. If it's violated, then you abort the transaction and roll back any updates that it made. Now, an abort by a transaction may result in other transactions that read dirty data from this transaction also being aborted, because that data was never ever reflected based on atomicity. Those are the transactions that read the dirty data by an aborted transaction also need to abort. But those transactions may have written data which may have been read by other transactions, and those transactions now transitively also need to be aborted. As a result, transaction aborts are a little bit tricky because one transaction abort might lead to a series of other cascading aborts of other transactions as well. So a second approach that tries to improve on this is known as timestamp ordering. This is used by several databases. Each transaction is assigned an ID. It's called the transaction ID. the transaction ID determines that transaction's position in the serialization order. So you want to make sure that you have a serial equivalence order that obeys the transaction ID ordering. When a transaction T executes an operation, you need to make sure that two conditions are true. T's write to an object O is allowed only if transactions that have previously read or written that object O had lower IDs than T. Okay, that's the first condition that needs to be satisfied. Second condition is that if T is trying to read an object O, that is allowed only if O was last written by a transaction with a lower ID than T. Okay, so if these two conditions are satisfied, then you can ensure that the transactions, even though they interleave their operations, follow the serialization order, and that the resulting interleaving is serially equivalent, and the ordering is the serialization order. Typically, timestamp ordering is implemented by maintaining read and write timestamps for the object. And whenever any of these two rules is violated for a transaction's operation, then the transaction is aborted. So this works for serial equivalence, but still you're still causing transactions to abort over here, right? You don't have cascading aborts anymore here necessarily, because the transaction only aborts and that's it. Or at least the cascading aborts are minimized over here, because the transaction can still abort and other transactions can be caused to abort because of it. But the aborts are minimized compared to the previous approach that we discussed on the previous slide. But essentially what I'm saying here is that you still have aborts and you might still want to do better than this. So a third approach is known as multi-version concurrency control. This is used in several systems, including some key value store systems like REAC. Here, for each object, you maintain a per transaction version of the object, right? And so each transaction maintains its own tentative version of that object. You also have a committed version, which is maintained on the server side or on the database side. Each tentative version has a timestamp of its own, and the committed version also has a timestamp. Some variants, some systems implement both a read and a write timestamp for the tentative version. Whenever a transaction wants to do a read or a write, you need to find the correct tentative version to read or write from. And this correctness, which is the correct version to choose from, is based on the transaction ID. So you want to make sure that you read only from transactions that were immediately previous writers. Okay, so you choose your point in the transaction among the versions of that object, and you choose the right version to read or write from. Okay. So this is only the sort of high-level overview of multi-version concurrency control. We are not discussing all its gory details over here. Now, eventual consistency that you have seen in key value stores is in fact a form of optimistic concurrency control. In Cassandra key value store you have seen, in the DynamoDB key value store, and also in the REAC key value store. But these systems are not transaction systems, so the optimistic approach looks different. In fact, it looks slightly simpler in some ways. So in Cassandra and DynamoDB, there is only one version of each data item, each key value pair. That's what we would call an object. And you have a last write wins or last writer wins policy, which is LWW. Essentially, the timestamp, typically based on physical time, is used to determine whether to overwrite the older value. If the new write's timestamp is higher than the current object's timestamp, you overwrite. Otherwise, you do nothing and you ignore that write. So this ensures eventual consistency, which means that eventually when writes stop, all the replicas will reflect the same value, which is the latest timestamp write. But you could have situations where a slightly older write with a fresher timestamp, because of unsynchronized clocks in a distributed system, a slightly older write with a fresher timestamp might in fact win. And so the last writer wins really is based on the notion of physical time and assumes some notion of time synchronization across clients. A different approach used in the REAC key value store uses vector clocks, and you should be familiar with vector clocks because you've studied them in the first half of the course when we discussed Lampo timestamps and then vector clocks. This notion implements causal ordering, and these vector clocks are used to detect whether a new write is strictly newer than the current value, if the vector clock value is strictly greater than, or if it's not compatible, then the new write might conflict with the old existing value. If there is a conflict, then you create a sibling value, meaning you maintain for that key two values, saying that these are two possible values for this key. These are sibling values. These need to be resolved at some point of time. They could be resolved by the user. You could bubble them up to the client or the user, which then picks one value and then does a write using that value and overwrites the existing values with a newer timestamp, or it could be resolved automatically by the application. So in any case, these are not resolved by the React system itself. They are pushed out to the client either by the user or by the application itself. Now, React uses vector clocks, and the vector clocks might get very large because the number of entries in the vector clock is potentially the same as the number of clients. And so to prevent a vector clock from getting too many entries, you use size-based pruning. You typically prune the number of entries, the maximum number of entries that can be there in a vector clock. Also, vector clocks might get very old. Some entries might have very old items, vector clock values in them. And so to prevent that from happening, you prune out or you remove entries that had very old timestamps in them. So to wrap up our discussion of concurrency control, we first discussed RPCs and RMIs, remote procedure calls, and remote method invocations, which are important building blocks in understanding what transactions are. Transactions are one of the most important concepts in database systems that have been used for many decades. For transactions, you need to maintain asset properties, and to maintain asset properties, serial equivalence is a very important technique, and typically this is detected and enforced via conflicting operations. And there's two ways or two approaches in which you can do concurrency control so that serial equivalence is still maintained. The first is pessimistic concurrency control, such as locking, which limits concurrency but is always correct. Optimistic concurrency control lets transactions proceed with their reads and writes under certain conditions, but checks later on or enforces checks at some point of time so that the asset properties and serial equivalence are in fact always obeyed. So after having seen concurrency control, we're going to see replication control in this next series of lectures. Today, in this lecture, we discuss replication. So what's the difference between concurrency control and replication control? Well, concurrency control deals with the case where you have multiple clients executing operations or transactions with just one server on the other hand. So you have multiple clients and one server on the other hand. Replication control focuses on the server side. Instead of having just one server, you have multiple server machines, and the objects are now spread out over these multiple server machines. You may have 5 objects which are stored, say 2 objects at one machine and 3 objects at another server, or you may have these objects replicated. So each of these objects has, say, 2 replicas at each of those 2 servers. So we'll discuss both the cases with and without replication in this series of lectures. So why is replication important at all? Well, first of all, replication means that an object has identical copies, each maintained by a separate server. These copies are typically called as replicas. I may use the term replica to also refer to not just the object copy itself, but also the server itself. So if I say the replica server, I mean the server that is storing a replica of the object. So why is replication important? Why is it important to have multiple identical copies of the same object? Well, there are a couple of reasons. The first reason is fault tolerance. If you maintain k replicas of each object, you can tolerate up to k-1 failures of any of the servers in the system. So if every object is replicated, say k equals 5 times, then your system, no matter how large it is, can tolerate up to 4 k-1 failures of any of the servers and still not lose any of these objects and still be able to serve out reads and writes to at least one of the copies of the objects. The second reason to do replication is load balancing. Essentially, if you have twice as many copies of of a given object, then each of the copies faces only half the number of reads and writes that it does. So increasing the number of copies lowers the load on each of the copies by a factor of k if you have k replicas compared to just one replica. In general, the fault tolerance requirement can be captured as a higher availability requirement. So let's calculate what availability really is. So if a server, if any server, say all the servers are identical, just for the purposes of this discussion. So if each server is down a fraction f of the time, f might be, some small number like 5% or 0.05. That's a server's failure probability. So if you don't have any replication where each object is stored on exactly one server, then the probability that the object is available is the probability that the server is up, which is just 1 minus the server's failure probability, or 1 minus f. Okay. So when you have k replicas, the availability of the object is the probability that at least one of the k replica servers is up, which is 1 minus the probability that all the replica servers are down. And that second probability, the probability that all the replica servers are down, is simply the failure probability of one server raised to the number of servers, or f to the power k. So that's 1 minus f power k. Okay, so for those of you who know your math and probability, you will notice that as k is higher, this number at 1 minus f power k is actually much closer to 1 than 1 minus f. How close is it? Well, let's look at some real numbers. So here is a table that shows you in the first column the failure probability f. So we have several sample values, 0.1, 0.05, 0.01. These are the failure probabilities of a single server. And then in the next column, it shows what is the availability of the object when you have no replication, where exactly one copy of the object is maintained. Essentially, this value is just 1 minus f. So 1 minus 0.1 is 0.9, which is 90%, and 1 minus 0.05 is 0.95, which is 95%, and so on and so forth. With k equals 3 replicas, you can calculate the availability of the object as 1 minus f power k, and that turns out, for f equals 0.1, it turns out to be 99.9%. This is often called as 3 nines of reliability, because you have 3 nines over here, 99.9%. With f equals 0.05, the availability goes up because the server failure probability has gone down, so it's gone up to 99.9875%. When you have f equals 0.01, you actually end up having 6 nines of reliability, 99.9999%. So that's a much higher reliability. And now, when you see nines of reliability being offered in an industry product or an industry service, now you know what exactly it means. They're actually talking about the availability percentages, as we're talking about here. With a higher number of replicas, you get a much higher availability. So just compare, when you have f equals 0.1, when you have k equals 3 replicas, you have 3 nines of reliability. But when you have k equals 5 replicas, you have 5 nines of reliability. Similarly, with failure probability of f equals 0.01, with no replication, you have 2 nines of reliability. With k equals 3 replicas, you have 6 nines of reliability. And with k equals 5 replicas, you have 10 nines of reliability. You can actually tune the number of replicas you have based on the failure probability that you expect to get the desired reliability from your system. So what's the catch? All this seems great, right? I mean, replication seems to give a lot of benefits. So what is the hard part? Well, the hard part is to guarantee 2 properties: replication transparency and replication consistency. Replication transparency essentially says that a client, any client, should not be able to see that there are multiple copies or multiple replicas of a given object. So as far as the client is concerned, the replication should be invisible or transparent. That is, the client should be able to execute operations just like there is just one copy of each object on the server side. The second, replication consistency, is similar, but it's slightly different. Here it talks about multiple clients seeing a consistent copy of the data in spite of replication. So in spite of the fact that the object is replicated, you want multiple clients to always perform operations as if there is only one copy of the data. And whenever a client updates or writes that the object, any replica of the object, all other replicas get updated, if possible, instantly. And if not instantly, at least as quickly as possible, so that before the next client performs its operation, all the replicas are up to date. Replication consistency means something stronger when you have transactions. Essentially, it means that you guarantee the ACID properties, which is atomicity, consistency, isolation, and durability, that you have seen earlier in our discussion on concurrency control. So how do you provide replication transparency? Well, typically you provide it using front end. So you have multiple clients. Think of these as, for instance, the clients accessing a flight reservation database. The replicas are storing information about the objects, such as the flights, and you have a few front-end servers. These might be front-end servers maintained at the data center, or there might be front-end servers maintained at a content distribution network, CDN, or some series of proxy servers or cache servers. Essentially, the clients only talk to the front end, so they don't see any replica groups or any replicas of the objects, and the front ends are then responsible for forwarding the requests to the corresponding replica objects. Here I have an object O that has 3 replicas marked as replica 1, replica 2, and replica 3. Whenever a front end receives a request from a client, it then forwards the request to the replica, and the replies come back from the replica group to the front end and then back to the client along the reverse path. Well, what about replication consistency? Well, there's two flavors to providing replication consistency. They are known as passive replication and active replication. In passive replication, we use a primary replica, also known as a master or a leader. In active replication, there is no leader. Instead, we use a fully distributed approach among the replicas. We'll discuss each of these approaches in the next few slides, but both these approaches use the concept of replicated state machine. Well, a state machine, some of you might know, is essentially a program or a series or a code which, when given a series of inputs, gives a series of outputs, but for each input, the internal state of the state machine might change as well. So essentially, typically you have a graph involving states and transition rules in between pairs of states, and whenever you receive an input, you have an output, but you might also transition the state machine from one state to another. Essentially, replicated state machine says that all the replicas of the given object are running the same state machine or the same code. And when they are given an identical series or an identical sequence of inputs at each of those replicated state machines, the series of states that those state machines go through is identical. Also, the series of outputs is also identical. Fred Schneider in 1990 formalized this as follows. He said that replicated state machines refer to multiple copies of the same state machine begun in the start state and receiving the same inputs in the same order will arrive at the same state, final state, having generated the same series of outputs. Okay, so that's essentially a replicated state machine. So now let's look at passive replication and active replication. So in passive replication, the group of replicas of object O elects one of the replicas as a master or a leader, and for this it uses one of our leader election protocols that you have seen earlier in the course. The front ends, whenever they receive a read or a write, they relay the operation directly to the master, and this ensures that for writes there is a total ordering of all the writes or of all the updates. For reads, some variants of passive replication allow the front ends to contact any of the three replicas for the reads, and some other flavors of passive replication direct the reads as well through the master. As far as writes are concerned, they need to go through the master because the master then sends out the corresponding writes to the other replicas inside the group. What happens when the master fails? Well, when the master fails, you again run your leader election protocol, whatever is your favorite leader election protocol, and you elect a new master. In comparison to passive replication, active replication does not use a master or a leader. Instead, each of the front ends multicasts out the request, read or write, to the entire replica group. Okay, so for this, you can use your own favorite multicast protocol that you've seen earlier in the course. So the red arrows over here show a multicast inside the replica group. Now, as you know, multicasts come in different flavors, especially ordering flavors. So you can use any flavor of multicast ordering depending on the application. And as you've seen earlier in the course, the flavors of ordering that are available to you are FIFO ordering, causal ordering, total ordering, or in fact even hybrid ordering among these two, these three. So if you use a total or hybrid ordering with total, so some form of total ordering, along with the replicated state machines, essentially it means that all the replicas are going to receive the same series of operations in the same order. And that means the series of states that they transition through and the series of outputs that they will output will all be identical at all the replicas. They may not happen at the same instant of physical time at all the replicas, but at least the ordering is the same. So what about failures? How do you incorporate failures into this multicast? Once again, as we have seen before in our discussion of multicast, you can use the concept or abstraction known as virtual synchrony or view synchrony, which orders failures along with multicasts within the group. So if you use virtual synchrony with total ordering for multicasts, essentially all the replicas see all the membership changes, failures, joins, or leaves, in the same order, and also the multicasts in the same order, and both of them, multicast and the membership changes, in the same order. Now you can use total ordering here if your application is okay with a slightly weaker form of ordering, which is causal ordering. That might be fine too. You could use that too, or even FIFO ordering if your application is willing to live with that. What do you do with transactions when you have replicated systems? Well, there is this concept known as one-copy serializability. Just like we studied serial equivalence for transactions when we studied concurrency control, In replication control for transactions, there is a concept known as one-copy serializability. What does it say? It says the following: a concurrent execution of transactions in a replicated database is one copy serializable. So when I say concurrent execution of transactions, I'm talking about multiple clients executing transactions. Replicated database means that objects have multiple replicas on the server side. So it's one copy serializable if it is equivalent to a serial execution. When I say serial, it means a serial equivalence, right? Execution of these transactions over a single logical copy of the database. Okay, so it's as if you executed these transactions one at a time over a database where there was exactly one copy of each object. Okay? In other words, this is saying that the effect of the transactions performed by the clients should be the same as if they had been performed one at a time on a single set of objects, that is one replica per object. Okay, so this essentially means serial equivalence of the transactions, right? So that's what we're talking about here. Okay, so we want to have both serial equivalence and one copy serializability, and one copy serializability appears to capture the serial equivalence notion as well. So after this, we'll discuss how do you commit transactions when you have distributed servers on the server side. Continuing our discussion of replication control, in this lecture we will see an important technique for committing transactions in replicated systems. This is known as two-phase commit. In general, committing transactions is an important problem in replicated systems, and in general in systems where you have objects across distributed servers. So here's an example of a transaction that touches objects at multiple servers. Here in this case we ignore replication for now, but let's just say each object has only one replica. So there is 26 objects here, there is 13 servers, each storing two of the objects. So server 1 stores objects A and B, server 2 stores objects C and D, and so on and so forth. Server 13 stores objects Y and Z. The transaction T here writes to all of these objects. When it reaches its commit point, we need to make sure that all of these servers commit. Okay, so when T tries to commit, we need to make sure that all the servers commit their updates. In this case, T will actually commit, the transaction T will commit, or that none of these servers commit their updates to their objects. In this case, T will abort. Okay, so this is an example of an all or nothing property here, which we want to guarantee for the transaction, but we also want to guarantee on the server side in a group of servers with distributed objects. This problem obviously should be familiar to you. This is in fact nothing but the consensus problem. In fact, in the concept of transactions, it's known as the atomic commit problem here. So one way to do an atomic commit is known as one-phase commit. This is a first-cut naive approach where you have a coordinator server, say a special server elected using leader election protocol, your favorite leader election protocol. The coordinator server is a special server that initiates the atomic commit and simply tells the 13 servers involved here, hey, why don't you commit your object updates from transaction T? If something goes wrong from the transaction side, if the transaction T wants to abort, then it tells the coordinator server to abort, and the coordinator server then relays to the servers that they should abort their updates from transaction T to their objects. So what's the problem with this? Well, the first issue is that the server storing the objects, the servers 1 through 13, have no say in whether the transaction commits or aborts. These servers are after all machines, so they have memory, and the memory might be corrupted. For instance, the object that they're storing or the updates from that particular transaction may be corrupted, and in this case you'll end up with an inconsistent system, because as far as the transaction T and the coordinator are concerned, they have wanted to commit, but the server just cannot commit. It just cannot commit because it does not have all the necessary information there. Also, the server might crash before receiving the message that asks it to commit, and in this case the updates it had from transaction T might have been stored in memory and lost. And in this case, you again have a system where you have data being lost. So to our rescue comes the two-phase commit protocol, which to this day is one of the most widely used protocols for committing transactions. Here again you have a coordinator server, again elected using a leader election protocol, and you have the remaining servers. As the name suggests, instead of using just one phase where the coordinator tells the server group, you have two phases here. So the coordinator first sends a prepare message to the servers. The prepare message asks the servers to prepare to commit. When a server receives the prepare message, it saves the updates from that particular transaction to disk. so that it is durable now. And after this, if the server fails, it can then recover starting from this log on disk. Then if everything is okay on the server side, it responds with a yes vote. If something went wrong, for instance, the memory got corrupted or it has lost its updates, it responds with a no vote. The coordinator server waits for these votes. If it receives any no vote, at least one no vote from any of the servers, it will then send out an abort message to all the servers. Okay, so this ensures that unless all the servers have voted yes, you will in fact end up aborting the entire transaction. Also, the coordinator server might not receive all the votes within a timeout. If it does not receive all the votes within a timeout, it also again sends an abort message to everyone. This is accounting for the case where a server might have failed. Server 13 might have failed and might never be able to send a vote back, and in this case the coordinator must abort because it doesn't know what happened, what went wrong with server 13 and whether server 13 will ever come back up. Okay, so once again, in summary, if the coordinator server receives at least one no vote, or it does not receive all the, in this case 13 votes within the timeout, it will send an abort message. However, if it receives all the 13 votes within the timeout, it then sends out a commit message knowing that everything has gone right on the server side, and they have saved their updates to the log on disk. Once they have voted yes or no, they can't immediately go ahead and commit, right? So if they voted yes, they can't really commit before receiving the next message. Okay, so they need to wait until the second phase commit message is received. When the commit message is received, they can then commit the updates from disk to the store, to the actual database, and they can respond back with an acknowledgement back to the coordinator. When the coordinator receives all the acknowledgements, okays, it can then say that the two-phase commit is done. How do you handle failures and how do you make sure that correctness is guaranteed? So first, if a server, one of the 13 servers in our case, voted a yes, it cannot unilaterally go ahead and commit the updates from the disk into the store or into the database. It needs to wait for the commit message. Why is this? Well, one of the other servers in the group might have voted a no or might have failed. In this case, the server might have to abort in the future. However, if a server votes no, meaning something has gone wrong on its side, if it votes no in the very first phase, then it can abort right away. Why is this? Well, this is because the coordinator would have received at least one no vote, this server's, and so it would have decided an abort in the future. Okay, so no matter when that abort is decided, it will never be a commit because this server has voted a no. Okay, so if a server votes no, it can go ahead and abort right away, but if a server votes yes, it needs to wait until the commit message is received. How do you deal with crashes? So to deal with server crashes, each server saves the tentative updates into permanent storage, meaning disk, right before replying yes or no in the first phase. It can't save it after replying yes or no because it might fail right after replying yes or no, but before saving it on disk. It needs to save it on disk before replying yes or no. If it fails before this, before it saves it on disk, anyway, the coordinator will time out waiting for this server's response and will abort the transaction. If it times out, if it crashes after saving it on disk but before replying yes or no, again, that's going to be an abort decision. If it crashes after saving it on disk and sending a yes vote, then it might be a commit decision, but at least it has all the necessary information saved on disk so that it can recover or retrieve it after its recovery, after it is rebooted. The coordinator might also crash, and so to recover from these crashes, the coordinator also logs all of its decisions and the received and sent messages, including counts of how many OKs it received on disk, so that if it fails, it can then recover and start where it left off. However, things might go wrong and the coordinator might never come back up, so a new election might be required to elect a new coordinator. In this case, the coordinator might need to either start where the old two-phase commit left off by querying the servers or just restart the two-phase commit altogether again. What about message losses? These messages that are sent out during the two-phase commit might also get lost. The prepare message, which is the first stage message going out from the coordinator to the servers asking them to prepare to commit, might get lost. Now, if the prepare message gets lost, then the server, one of the 13 servers, might decide to abort unilaterally after a timeout, waiting for the first phase message. In this case, because it will never vote a yes to the coordinator will always decide an abort for this particular transaction. Alternatively, to deal with prepare message loss, you can have the coordinator send out a second prepare message. Now, the yes-no vote in the first phase again might get lost as well. If this gets lost, then the coordinator will end up aborting the transaction. this is tough luck. Even though everything might have gone right, even though everyone might have voted yes, just because the message, one of these yes votes was dropped by the network, you decide to abort the transaction. Yes, this is pessimistic, but at least it maintains correctness. It errs on the side of safety, and in this case, the coordinator, unless it receives all the votes, will decide to abort the transaction. Finally, the commit or abort message, the second phase message, might get lost in the network itself. And in this case, you're okay, because the coordinator has already made a decision and has logged the decision on disk. So the server can poll the coordinator unless if it has not received a decision in the second phase for what its decision is. Okay, so it can poll it repeatedly until the coordinator comes back up and sends it either a commit or an abort message. So a two-phase commit is used at the commit point in distributed servers. Another alternative to two-phase commit, of course, is a consensus solution such as Paxos. So Paxos is also being widely used nowadays, increasingly used nowadays, to decide whether to commit a transaction or not. Okay, but if you use Paxos, you need to make sure that if any server votes a no, then everyone will abort. That's the only catch in using Paxos. Paxos can also be used for ordering updates that are being received by a replica group. So when a replica group receives multiple updates from multiple clients, you need to make sure that all the replicas receive the updates in the same order. This is again because of replicated state machines. You want to make sure that all the replicas have the same series of states that they transition through and the same series of outputs. So in order to do this, essentially the way you use Paxos is that a server, any one of the servers in the replica group, proposes a message for the next sequence number. So one of the updates it has, it proposes it for the next sequence number, and then the group either reaches consensus on this or not. If it doesn't, then another message is considered for the next sequence number, and you continue so on and so forth. Okay, so this is the way in which Paxos is used to totally order updates within the group itself, so that all the servers apply these updates in the same order as each other. So that wraps up our discussion of concurrency control and replication control. And for replication control, we've discussed the case where you have multiple servers, distributed servers in the cloud, which are either replicating objects for fault tolerance or load balancing objects across multiple servers with or without fault tolerance. Replication can be implemented using a couple of flavors, active replication and passive replication, and these can be implemented using concepts that you have learned earlier in the course, specifically using flavors of multicast and virtual synchrony. And finally, we have seen how to commit transactions when you have distributed servers in the cloud. The two-phase commit protocol is one of the most widely used protocols today. All right, we have completed our deep dive, and now we start to come back up to the surface. In these last 3 weeks of C3 Part 2, the remaining weeks, you will see topics that fall into one of three categories. You see topics that are either hot topics in cloud computing or orthogonal but related topics, and also we'll see a few important classical concepts. In hot topics, our goal is not to explain the entire hot topic to you, but to get you jump started with a particular topic so that you have enough information to explore it by yourself, either on the web or by trying out some of those systems. We'll see some orthogonal but related topics as well, which are not necessarily distributed algorithms, but are related to distributed systems that are on the peripheries or interact with distributed systems. And so it's important for all distributed systems and cloud systems people to know what these topics are. And then we'll also see a few more important classical topics which fall under core concepts. So in this week, week 3, we'll see some hot topics which include stream processing, such as Apache Storm. We'll see distributed graph processing, where you process very large graphs, such as the Facebook graph or the web graph. In stream processing, we'll see how large amounts of data that are streaming in, such as a Twitter stream, are processed in real time. You'll see Apache Storm, which has been used for processing some of these streaming data. Once again, our goal here is to get you jump started with these topics so that you can explore them later by yourself. In orthogonal topics, we'll see structure of networks, how networks look. Networks is not something that we study in this course, but they are, of course, something that distributed systems interact with. After all, a network is something that a distributed system sends and receives messages via. So it's important to know the characteristics of these networks so that you can better design distributed systems. And we'll study a little bit of scheduling, which is an important topic that is a core concept in distributed systems. In this lecture, we're going to be discussing stream processing. Now, stream processing is a very old branch of distributed computing, but in the last few years, it has come into the prominence because of the new workloads that we are seeing. And one of the systems that has become very popular is the Storm system, and we'll be discussing some of the details of Storm in this lecture. So we'll discuss why stream processing is important in today's workloads, and then also we'll discuss some design details of Storm. So today's workloads involve large amounts of data, whether these are feeds in a social network or whether they are information, click-through information from particular websites or from advertisement networks, or whether they are logs of accesses in any distributed computing infrastructure. So when you have such large amounts of information, you need some real-time view of these of this data so that they can be compressed and they can be distilled down into a form that is digestible to human users. So for instance, in social networks, you have the capability of search, and this is often real-time search, as you might find in the Twitter social network, where you can do a real-time search of the tweets that are being put out right now on a particular topic or with a particular keyword. When you have websites which are collecting data about who is visiting the websites, you may want to do website statistics, for instance, analytics via Google Analytics. Also, you might want to detect who are the intruders into your distributed cluster. For instance, most data centers are running some form of intrusion detection system or the other, and all of these require real-time analysis of the data that's coming in. Essentially, real-time analysis means that you have large amounts of data and you need to process very large amounts of data within a few seconds with very low latencies and with very high throughput, as much data per second as possible. And you want to produce some amount of knowledge or information out of that data that you're getting. So you want to convert data into knowledge, but fairly quickly. Even if the data cannot be processed completely, you want to still be able to glean some information out of it at least. So that's a stream processing challenge. And of course, you might think, well, the MapReduce system is available and we've already used it for batch computing before. Why not just use it? And in fact, there are variants of MapReduce that are aimed at stream processing. But essentially, MapReduce is a batch processing framework, and you need to wait for an entire computation on a large data set to complete before you can get the results. There is no notion of partial results in MapReduce at all. Even the variants of MapReduce that are tuned to stream processing or to incremental processing, there are incremental versions of MapReduce as well, still have a fairly high latency. And essentially, MapReduce is not intended for stream processing applications, and essentially it's not intended to be a long-running application, which is what stream processing really is. So the Storm system has become very popular in the last few years. It's an Apache project in the Apache incubator. It's one of the more highly active JVM projects today. Multiple languages are supported in the API, including Python and Ruby. And Storm, as is today, is used by many companies, including Twitter, for personalization and for search. So every time you do a Twitter search, you're likely using indirectly the Storm system that Twitter is running in their data centers. Flipboard uses Storm for generating custom feeds, and a variety of other companies and websites use Storm as well, including the Weather Channel, WebMD.com, and others. So Storm consists of many components, and the 5 major keywords in Storm are tuples, streams, spouts, bolts, and topologies. We'll study these, what these are over the next few slides. So a tuple is essentially an ordered list of elements. For instance, a tuple might be, in the Twitter world, a tweeter followed by the tweet itself. For instance, a tuple might be the tweeter name, which is Miley Cyrus, followed by the tweet which says, hey, here's my new song. A different tuple might be a different tweeter, Justin Bieber, followed by the tweet itself, hey, here's my new song. In a different world where you're collecting click-through logs, the tuple might be the URL followed by the IP of the clicker client, then the date and the time. For instance, the URL might be coursera.org, The IP is 101.201.301.401. Then you have the date and the time. A different tuple might be from a different client, 901, 801, 701, 601, and then a slightly later time. Okay, so each of these is a tuple, and you want to process these tuples. You don't have just one tuple as you have seen here, you have multiple tuples, and so a stream is said to be a sequence of tuples, potentially unbounded, which means that the stream might contain potentially infinite number of tuples. For instance, in our social network example, we could have all the tweets that are being put out there be a stream. So for instance, the Miley Cyrus tweet followed by the Justin Bieber tweet, followed by a tweet by Rolling Stones that says, here's my old song that's still a super hit, and so on and so forth. You can have other tuples coming in as well. Similarly, in the website example, the two tuples we discussed might be part of a stream that contain other tuples as well. Essentially, you have a sequence of tuples coming in, or a stream, and you need to process these tuples, potentially one tuple at a time. Well, who generates these tuples? The process or entity that generates these tuples is known as the spout in Storm. A spout is the source of streams. Often the spout reads from a crawler or from a database. For instance, it might be reading from a database, in the case of Twitter, the database that contains the actual tweets that are being posted. Or in the case of a web analytics application, it might be reading from a crawler that is crawling the proxy logs of a particular web page. So a spout can generate multiple streams. So here I have a green stream of green tuples and an orange stream of orange tuples being generated simultaneously by the same spout. How do you process these streams? Well, the entity that processes a stream is known as a bolt in Storm. A bolt processes input streams, typically just one input stream, but it can process multiple input streams as well. And in turn, it generates an output stream, which is then fed to other bolts. In this example, I have a spout on the left generating a green stream for the first bolt, which processes one tuple at a time, maybe multiple tuples at a time, and generates some output tuples, in this case the purple tuples, which are then fed as input to another bolt over here, the second bolt, which then generates yellow tuples, which are then fed potentially to another bolt, and so on and so forth. So a bolt is essentially a program that is given as input one or more streams, and then decides when it gets tuples from these multiple streams or from just one stream, whichever are its input streams, it decides how to generate output bolts. Okay, so that's typically the code you would be writing when you write a Storm application. You'll be writing code for each of the bolts in your application. And your application essentially consists of a series of bolts connected in a topology. So a directed graph of spouts and bolts along with output bolts is called a topology, and that's essentially equivalent or corresponds to a Storm application. So in this case, I have 3 bolts in my application, one spout, and one of these bolts is the output bolt. The rightmost bolt is the output bolt. And as shown here, essentially you would write code for each of these 3 bolts in the system as per your application requirements. And then the final bolt, the rightmost bolt, would generate some output bolts for you. Now, topologies are essentially directed graphs, and topologies may contain loops as well. They can have cycles, as is shown over here, if your application in fact requires it. But of course, when you're coding cycles, you have to be careful that you're not creating infinite loops, so that you need to be sure that tuples are not going around in the system forever. You need to make sure that tuples are in fact being processed, and then within some amount of time they leave the system. They don't stay around forever. So bolts themselves, the entity that processes streams, can come in many different flavors. 3 of the more popular flavors are filter, join, and apply. A filter essentially forwards a tuple only if it satisfies a condition. So that's essentially very similar to the SQL filtering notion. A join has a bolt receiving multiple streams. Say it receives 2 streams A and B. It computes a cross product of all the tuples in streams A and B. And for every pair of tuples, one from A, one from B, it then checks whether it satisfies a condition, and if it does, then it outputs something. Okay, perhaps something from those 2 tuples. That's again very similar to the notion of a database join. Finally, you have an apply or transform, which takes a tuple and modifies it according to a function, perhaps even according to a filter function. And there are of course many other functions that bolts can implement. In fact, you can write up your own bolt functionality that either uses these functionalities or doesn't, implements a new functionality. But no matter what bolt you implement, the bolt needs to process a lot of data. Remember that we are having very large amounts of data coming in. There are potentially gigabytes per second, maybe even terabytes per second coming into each bolt. And you need to process this large amount of data and process it fast. So in order to make each bolt fast, you can parallelize bolts. You can parallelize a bolt into multiple processes or tasks. So a bolt might consist of multiple tasks, and the incoming stream into that bolt is split among these tasks. Typically, each incoming tuple goes to one task in the bolt, but it might also go to multiple tasks. How an incoming tuple is routed among the tasks in a given bolt is decided by what is known as the grouping strategy. So there are three types of grouping that are popular, which decide how the tuples of a stream are distributed among the tasks of the bolt to which that stream is going to. So the first is shuffle grouping, which distributes the tuples of a stream evenly among the tasks of the bolt, and this is done in a round-robin fashion. So essentially, as you receive tuples, you go through the tasks in a sequential order, giving each task one or a batch of tuples, and then you loop back around to the beginning of that list of tasks, and then you do that again for the incoming tuples. However, this may not be what you want, because you may need to group the tuples based on some fields or a subset of its fields. This is where fields grouping comes into play. So here you group a stream by a subset of its fields. For instance, you may want to have all the tweets, all the tuples, where the Twitter username starts with A through M or 0 through 4 to go to task 1, and the remaining tuples to go to task 2. This allows you to, for instance, aggregate those individual classes of usernames, and this is done via fields grouping. Finally, you have all grouping as well, where all the tasks of the bolt receive all the input tuples. This is especially useful for joins. For instance, if you're trying to join the incoming stream with some other stream or with an existing database, then this is fairly useful for an all grouping. How is the Storm cluster itself run? Let's discuss a little bit about the infrastructure components. So the Storm cluster is run by a master node, again elected using leader election. The master node runs a daemon called Nimbus, and Nimbus is responsible for three functionalities, among others. It's responsible for distributing code around the cluster. So when a bolt is started up on another server, Nimbus is responsible for sending the code for that bolt to that particular server. It's responsible for assigning tasks to machines. So when a bolt is split up into multiple tasks, which task runs on which servers, that's decided by Nimbus. Also, Nimbus is responsible for failure detection. If any of these servers running bolts crashes, Nimbus needs to detect this and then potentially restart the tasks or the bolts on other servers. The servers themselves are running the worker node. This is run via a daemon known as a supervisor. This listens for work assigned to its machine, so it talks to the Nimbus server, and it also keeps track of the tasks that are running at itself, so that if any of these tasks crashes, it can then be either restarted, or the Nimbus daemon can be asked by the supervisor for a new task that needs to be run in its place. Storm also uses the Zookeeper system, which you've seen elsewhere in this course, which helps coordinate between the Nimbus and the supervisors and keep all the state of the supervisors and the Nimbus in a consistent place, so that if any of these crashes, you can then recover using what's kept in the Zookeeper system itself. What do you do with failures? So of course you can have failures. A server might crash while it is in the midst of processing a tuple, and if it does so, then those tuples might be lost. Any of the tuples that are in transit at that server might be lost. Okay, so in order to tackle this, Storm uses what is known as anchoring, where you can anchor an output to one or more of its input tuples. Okay, and the failure of this output tuple to be received causes one or more of those tuples to be replayed in the system. The way you do this is via an API, which is specified in the output collector class. This has three major functions: emit, ack, and fail. Emit essentially emits an output tuple, perhaps anchored to an input tuple, and if you want to anchor to an input tuple, you specify that as the first argument in emit. You can acknowledge that a tuple has been done by calling the ack function, and this means that the spout will now know that, hey, this input tuple that I had generated has been processed by the last bolt in the topology. Or you can fail a tuple. This immediately fails a spout tuple at the root of the tuple topology, and if so, then you would start replaying the tuples that have been missed as specified in the fail function itself. Okay, this might be done, for instance, if there is a failure or there is an exception from the database, and so on and so forth. Typically, you need to be in Storm, at least in the current version, you need to remember to explicitly acknowledge or fail each tuple. There is no implicit failure detection of the tuples themselves. And if you don't do so, then you can certainly miss tuples that will not be processed because of failures, but also because tuples consume memory. You might have memory leaks because the tuples might stay around forever inside a particular server and never be garbage collected. So in order to prevent this, you need to make sure that you use ACK or fail in a consistent manner, in an explicit manner across all the tuples that you're processing. So to wrap up our discussion of stream processing and Storm, processing data, large amounts of data in real-time systems, in today's systems in real time within a few seconds is a big requirement. And although stream processing systems have been around for a long period of time, for instance, IBM has had a very long-running project called Streams, which is a very popular and widely used proprietary system. One of the newer open source systems that has emerged for processing streams today is Storm or Apache Storm. There are many sister systems that have emerged as an offshoot of Storm, for instance, Spark Streaming from Berkeley. But in essence, Storm allows you to process large amounts of data, large streams in very short periods of time with very high throughput. To do this, it uses parallelism. It allows you to write up arbitrary applications using application topologies, and it also supports some notion of fault tolerance. Hi there. In this lecture, we're going to see the topic of distributed graph processing, which has come into prevalence in just the last few years in industry. So we'll see what distributed graph processing is, and we'll see a little bit of the overview of Google's Pregel system for distributed graph processing. Pregel is not an open source system, but Google has published a paper on it. And based on that paper, several systems have been built, including Pregel-like systems, as well as much more advanced systems that are faster than Pregel. We won't get to discuss all these systems in detail, but hopefully this lecture will give you enough of an inroads into the topic that you can go and look up these systems if you're so interested. So what is a graph first? A graph is not a plot. We are not talking of a graph as in a curve or a series of dots. A graph instead is a network, and a graph, like a network, has vertices or nodes. For instance, Facebook, the social network, can be represented as a graph, where each user is a vertex or a node. A graph also has edges. An edge connects a pair of vertices. For instance, in the Facebook graph, an edge would be a friend relationship between, say, you and one of your friends. That would be one edge. The friend relationship between you and a second friend would be a different, separate edge. Okay, so a graph consists of vertices and it consists of edges that join pairs of vertices. So there are lots of graphs around us. So on the right, I have an example, a picture of a graph taken from Wikimedia. Here you'll see the vertices or nodes shown in red and the edges shown in black, okay, joining pairs of nodes. So there are graphs all around us. The internet itself is a graph where the vertices are routers or switches, and the edges are actual links joining these routers or switches, links that actually carry packets and traffic. The World Wide Web can be represented as a graph where the vertices are web pages and the edges are URL links where one page points to another. So if you have a URL on one page pointing to another, that's an edge in the World Wide Web graph. Now, the World Wide Web graph is a special kind of graph known as a directed graph because edges are directed. Page A might point to a page B. That does not mean page B also points back to A. So edges actually have directions. They are unidirectional, and so the World Wide Web graph is an example of a directed graph. Graphs where edges are bidirectional by default are known as undirected graphs. Social graphs such as Facebook are again an example of undirected graphs. Twitter is an example of a directed graph because you can follow someone, but that doesn't mean they'll follow you back. LinkedIn is an undirected graph as well because the edges are bidirectional. Other graphs include the DNA interaction graphs, ecosystem graphs, chemical reaction graphs, and a whole lot other graphs. So in fact, in any area of science, you can find graphs, you can draw graphs, and then you want to make sense of these graphs. So graph processing operations try to derive properties from these graphs. They try to summarize graphs into statistics so that you can understand what the graphs are telling you much better. For instance, you may want to find shortest paths between pairs of vertices. In the internet graph, this is useful for shortest path routing so that your packets can get routed fairly quickly. In LinkedIn, shortest paths is useful to find the degrees of separation between you and someone else. So if you've used LinkedIn, you might notice that it says this is a first connection or a second connection or a third connection. That's the degrees of separation, and that's obtained by running the shortest path algorithm to see what is the distance between you and another user, what is the shortest distance between you and another user. In dating websites such as Match.com, graph processing operations are used to find good matches between pairs of users. And there are many other examples of graph processing applications being used. So what's so challenging about this? Well, one of the biggest challenges is that these graphs are very large. The human social network has hundreds of millions of vertices and billions of edges. If you consider the graph consisting of all the humans in the world, where every vertex represents a human in the world and edges represent friends or relative relationships, then that graph has 6 to 7 billion vertices and many hundreds of billions of edges. The World Wide Web itself has millions of vertices and edges. So these are very large graphs. They're so large that the entire graph cannot be stored on a single server for processing. Even if it were to be stored on a single server, it would be really slow on that server, even if the server had many processors. So this is where the distributed cluster or the cloud comes into action, where you can use a large number of machines in a cloud infrastructure or in a data center to process a very large graph very quickly and very efficiently. So what does a typical graph processing application look like? Here we are talking of a typical graph processing application. We are not yet talking of the distributed version of it. I'll talk about the distributed version of it soon. So a graph processing application works in iterations. So one iteration leads to the next. Each vertex is assigned a value. At the beginning of the iterations, the value is some default value like 0. Then in each iteration, each vertex in the graph gathers the values from its immediate neighbors, vertices who are adjacent to it via an edge. So for instance, at the vertex A here shown in the figure, its immediate neighboring vertices would be B, C, D, and E. Those are the vertices that join it directly with an edge. So A would obtain their values at the beginning of the iteration. So B would send its value to A, C would send its value to A, D would send its value to A, and E would also send its value to A. Once it has all these values, A would then use its immediate neighbor values along with its own value to compute its own new value. And then at the end of the iteration, it would send out its new value to its immediate neighbor. So it would send out its value to B, C, D, and E. Then B, C, D, and E, in this iteration, they had also used the value of A to compute their own new values. And in the next iteration, again, they'll use a new value of A to compute their own new values. So this series of steps 1, 2, 3 is done for every vertex in the graph during each iteration. So you keep doing this iteratively, and how many iterations do you have? Well, you can either have a fixed number of iterations after which the graph processing terminates, or if the kind of application you're running actually converges, for instance, the shortest path algorithm is one of those algorithms that actually converges, then after a while vertices will stop changing values. So they'll get values, but their new value that they compute in the second step will be the same as their old value. And if all the vertices in a given iteration do not change values, then the computation has terminated. So in order to run this in a distributed system, can we use Hadoop? That is the first thought that we have. Well, if we wrote this using Hadoop, essentially we would have a multi-stage Hadoop where you would have one map and reduce phase for each iteration. So each map and reduce stage would be one graph iteration. So if you had 100 iterations, you would have 100 chained Hadoop or map reduce jobs after another. You would use the vertex IDs as the keys in the reduce phase so that the information about a particular vertex would get routed to the same reduce task, which would then use it to compute the new value for that vertex. This is attractive because, of course, Hadoop is well known, so it may be fairly straightforward to write this application up in Hadoop, but it's fairly inefficient. At the end of every stage, that is at the end of every iteration, you essentially are transferring all the vertices values over the network to the reduce tasks, or almost all the vertices values. And this can be very slow because essentially you're transferring the entire graph during each iteration over the network. That's really slow. Also, if you're using Hadoop, at the end of the reduce phase, the vertex values may be written to the HDFS, the distributed file system, and that makes it even slower. So Hadoop may be easier to code up, but it's very slow as far as the graph processing is concerned. And our main reason for using distributed infrastructure, data center, was to speed up graph processing. So what comes to our rescue is what is known as the bulk synchronous parallel model, where essentially you have local computation being done at multiple processors parallelly. Here you think like a vertex, so each vertex is computed separately by a different processor, but at the end of the iteration, all the processors meet a barrier where all of them wait for the other processors to complete their iteration, and only then do they proceed to the next iteration. The BSP, or the bulk synchronous parallel model, was originally proposed by Valiant, and that is what is used by many of the distributed graph processing engines today. So in the basic distributed graph processing engines today, you think like a vertex. You assign each vertex to one server, so each server gets a subset of the vertices in the graph. Thereafter, in each iteration, each server performs the gather, apply, and scatter for each of its assigned vertices. For each of its vertices, it gathers all its neighboring vertices values. So for a given vertex that a server is assigned, it gets the values from the vertices that are immediately joined to that vertex by an edge. Some of these vertices may be local at that server, other vertices may be located on other servers, so you fetch their vertex values over the network. Then once you have these values, you apply. In other words, you compute this vertex's new value using its old value and the values of its immediate neighboring vertices, and then you scatter. You send the new value over to these neighboring vertices. Okay, so this is again very similar to the 3 steps we had discussed earlier in the non-distributed version of graph processing. So here it makes a difference. What makes a difference here is which server you assign a given vertex to, because this can reduce the amount of communication. If the neighboring vertices of a given vertex are on the same server as itself, then essentially you can fetch their values without involving any network overhead. So there is a couple of options in assigning servers to vertices. The first is hash based, where you take the vertex ID, you hash it using a well-known hash function, and you then take modulo number of servers, and whatever value you get is the server number to which that vertex is assigned to. Okay, so again, this is random, but it's consistent, and this should be familiar to you because this is essentially just consistent hashing, as we've discussed in peer-to-peer systems when we discuss distributed hash tables like CARD. A second option is locality based, where you assign vertices with more neighbors to the same server as its neighbors. So a vertex that has a very high number of neighbors is located on the same server, is assigned to the same server as its neighbors, and so fetching those neighbor values are just local operations and do not involve any network overhead. This reduces server-to-server communication volume at each iteration. Now, the Pregel system by Google follows the bulk synchronous parallel approach, and here is in a nutshell how it works. Pregel uses the master worker model. There is one master server, and there are multiple worker servers. These would also be master daemon, the master daemon and the worker daemons running at each of the other servers. The master server is responsible for maintaining the list of worker servers, monitoring them. If any of them fail, then you need to restart them and reassign any failed vertices to newer servers. And the master also maintains a graphical user interface and a web UI for monitoring the progress of the other workers. The workers in turn are responsible for actually carrying out the gather, apply, scatter on the vertices that are assigned to them, and also for communicating with the other workers in fetching the values of the neighboring vertices where necessary. Typically in Pregel, the persistent data is stored as files on a distributed storage system such as GFS in Pregel's Google or in the Bigtable system. And temporary data is also stored on local disk, and it's stored on local disk because essentially if the worker crashes and then recovers, you want to be able to start where you left off. So how does the Pregel execution proceed? Well, first of all, many copies of the program begin executing on the cluster. The worker daemon startup and the master daemon starts up. The master then assigns a portion of the input, that is a subset of the vertices, to each worker. Each worker loads the vertices from, say, the GFS or Bigtable and marks these vertices as active. And then in each iteration, the master instructs all the workers to perform the iterations. So the worker loops through its active vertices and computes a new value for each vertex based on its old value and the neighbor values. The messages that contain the new vertex values can be sent anytime during the iteration, but they need to be delivered before the iteration is done, that is, before the barrier is reached by all the vertices, by all the servers at the end of the iteration. When all the workers reach the barrier at the end of the iteration, then the master is informed about this, and it knows that all the workers have finished this particular iteration, and the master can then move on to the next iteration, and it repeats these 3 steps again for all the workers. When does the computation halt? Well, the computation halts when in some iteration it's true that none of the vertices are active and all the vertices are marked as being inactive, meaning their values have not changed since the last iteration, and when no messages are in transit during the particular iteration. This means that the computation has terminated, it has converged, there are going to be no more vertex value changes in the future. At this point of time, the master can instruct each worker to save its portion of the graph or its results, and you now have whatever values your application set out to compute, whether they are shortest path values, whether they are values about matching in a dating graph, or other values as far as your application is concerned. What about failures? How does Pregel handle failures? Well, Pregel uses checkpointing. Periodically, the master instructs the workers to save the state of their partitions to persistent storage. The state includes vertex values, edge values, and any messages that are in transit. And these checkpoints can then be used to recover in the future. Ping-based messages are used from the master to the worker for the master to keep track of the worker failures. If a worker fails, then the master reassigns the graph partitions to the currently available workers, so that every vertex is still assigned to one server. And then the workers all reload their partition state from the most recent checkpoint, and then they start where they left off. So when you have a failure, essentially you might end up losing the value of the work since the last checkpoint. If you're checkpointing at the end of every iteration, then you lose at most one iteration's worth of work, and you can start from the latest iteration. So how fast is Pregel? For the single source shortest path, or SSSP benchmark, on a 1 billion vertex graph, which is a tree graph, with 50 workers, computing SSSP took 180 seconds. With 800 workers, it took about 20 seconds, which is pretty fast. When you increase the size of the graph to 50 billion vertices, which is a pretty large graph, the human social network graph in the world would contain about no more than 7 billion vertices. With 50 billion vertices and 800 workers, this takes about 700 seconds, which is about 12 minutes, which is pretty fast. So that wraps up our discussion of distributed graph processing. Graphs are all around us, and large graphs are all around us, whether they are internet graphs, World Wide Web graphs, or social network graphs, and we need to process these to make sense of them. MapReduce is an attractive approach, but it's not very fast. It's not very efficient. Instead, we want to use distributed graph processing systems such as Pregel by Google, or their offshoots, including open source systems like Piccolo and Giraffe, which are very much Pregel-like in their implementation, or other systems that are much faster than Pregel, including GraphLab, PowerGraph, LFGraph, and Extreme. These are systems that have come out of research projects in the last few years, and some of these are open source, and they're being used increasingly in order to process graphs in clusters. Hi there. In this lecture, we're going to see some very interesting and cool properties of networks, or graphs, as you have seen them. So before we get started, a few definitions again. What is a network or a graph? A network or a graph are synonyms, by the way. So a network or a graph has vertices or nodes. For instance, in the Facebook graph, each user is a vertex. In the internet graph, each router or switch is a vertex. There are edges that connect pairs of vertices. In the Facebook graph, a friend relationship between you and one of your friends is an edge. Similarly, in the internet graph, the link joining two switches in the internet constitute an edge in that graph. So there are networks or graphs all around us. The internet, of course, is one of the largest networks that we use. The World Wide Web is a network where the vertices are web pages and the edges joining them are links that point from one web page to another. This is often called a directed graph, as the edges are unidirectional. There are also social networks such as Facebook, Twitter, and LinkedIn, which are all networks where the users are vertices and the friend relationships or the connections are edges. And of course, there are biological graphs such as DNA interaction graphs, ecosystem graphs, and of course, all of these are networks as well. So there's a variety of networks, and all these networks are fairly complex. They have different kinds of complexity. The first kind of complexity is structural complexity. For instance, the human social network has about 7 billion nodes. That's the number of people alive in the world as of this year, 2014. There are millions of computers on the internet. The graphs or the networks as a result of these large numbers of vertices are also structurally very, very complex. These networks evolve over time. They don't look the same now as they did 1 year ago, and they don't look the same now as they will 1 year from now. This is because people make friends all the time, new people are born, people die, relationships change over time. In the internet, the ISPs change hands all the time, so the links in the internet change as well. And of course, in the World Wide Web, as you know, the new pages are created as well as new edges and new links are added all the time. And there's a lot of diversity even inside any one of these graphs. Inside the human social network, for instance, some folks are more popular than others, so they might have more friends than others. In the World Wide Web, some websites may have many more links than others. They have many more links pointing to them than other websites do. For instance, the BBC website has many more links pointing to it than your or my personal homepage does, likely. And of course, the vertices in these networks are fairly complex. In the internet graph, the endpoints, the routers and switches have different kinds of CPUs. They're running different kinds of OSs. And these OSs themselves have a lot of complexity. And of course, human beings in the human social network are very complex individuals as well. And even though you might be able to represent each of these vertices by a few simple rules, when you put a large number of these vertices together in a network, you get some very complex global behaviors. These are often called as emergent phenomena. So even from simple end vertex behavior and end edge behavior, which are governed by simple rules, you might get very complex system-wide behavior. One of the best examples of this is climate change. So you could represent climate change as a network where the vertices are different points on the globe and the edges are causality relationships between them. And we do understand all the basics of climate change. For instance, wind flows from high pressure to lower pressure, the rainfall happens when there is lower pressure, and so on and so forth. And yet weather is kind of hard to predict. And that's precisely because it's an example of an emergent phenomenon where even though you know the simple rules, you don't necessarily, you're not necessarily able to predict the emergent global behaviors when you put all of these rules together in a very large complex system. So these networks have a lot of structure in the sense that in many of these networks, you're able to reach one node from another in just a few hops. For instance, there is this well-known myth, actually almost a fact, known as 6 degrees of Kevin Bacon. In this case, if you draw the actor graph, if you use the Internet Movie Database, IMDb, and if you represent each actor or actress by a vertex in the graph, and an edge joining two actors, if those actors have acted together in at least one movie, then it can be shown that any actor can be reached from Kevin Bacon, the vertex representing Kevin Bacon, within 6 hops. So you can take just 6 jumps, or one over each edge, and reach any actor from Kevin Bacon. Milgram, a researcher at Stanford, did an experiment in the 1970s which showed that the human social network has just a few separates any pair of human beings with just a few edges. Typically, it's again known as 6 degrees of separation, where there are an expected number of 6 hops between any two individuals on the world, no matter how far or how unrelated they happen to be. And so, the actor network, the human network, and also other networks such as the World Wide Web, the human social networks that are in real online social networks such as Facebook, Twitter, and LinkedIn, peer-to-peer overlays, electric power grids, protein networks, a lot of these share this common characteristic where you can reach any node from any other node within just a few hops, just 6 hops or so. So why is this? We should be wondering why this is. And one of the common characteristics among all of these networks is that they've evolved naturally. It's not been the case that someone has come along and said, hey, here's how the network is going to be now and forever. Instead, these networks started small and then they evolved over time. All of these, whether it's a World Wide Web, whether it's a human social network, or whether it's an electric power grid, they evolved, whether it's evolution over a few years or over a few decades, in the case of Facebook, or in the case of the electric power grid, or as in the case of the human social network, evolution over many, many centuries and millennia. A lot of these are small world networks. Here I'm introducing a new term, a very interesting and very popular term called small world networks. We need to see what exactly they are. Before we see small world networks, let's see 2 important metrics that we can use to characterize networks. They are called clustering coefficient and path length. Let's do the path length first. The path length is something that you've already seen so far in our discussion. Path length essentially is, if you take any pair of vertices in the graph, you take the shortest path in between them, the shortest number of vertices you need to jump from one to reach the other. That's the path length of that vertex pair. You calculate this path length for every pair of vertices and you take the average among them. That's the path length of the entire graph, or the average path length in that graph or network. So the longer the path length is, the more spread out the network is in a sense, and the shorter the path length is, the more clustered the network is. But clustering is captured by a different metric known as the clustering coefficient, also abbreviated as CC. This defines something like the following. Given three vertices A, B, and C, if there is an edge between A and C, given an edge between A and C, and given an edge between C and B, that is A and B are common neighbors at C, what is the probability that A and B are also connected to each other? In other words, C has two friends, A and B. What is the probability that C's two friends are also friends of each other? That is the clustering coefficient. This is a probability, so it has values between 0 and 1. If the value is 0, then it means that essentially this is a very highly unclustered graph. For instance, tree networks have a clustering coefficient of 0. However, if it has a clustering coefficient of 1.0, the highest value possible, then it means that this is a highly clustered network. For instance, a complete graph where every vertex is joined to every other vertex is an example of a graph that has a 1.0 clustering coefficient. But different graphs lie at different points on the spectrum of clustering coefficient and path length. For instance, if you take the ring graph, a graph that you have seen when we discussed peer-to-peer systems and distributed hash tables before, you take the ring graph and you add a few successors and predecessors to each vertex, you get a graph that has a very high clustering coefficient, because if you have two neighbors, they're likely also to be neighbors of each other because they're likely to be successor and predecessor as well. But it has very long paths. If you have n vertices in your network, then the paths are on average order n in length. On the other hand, if you draw a random graph where the edges are added between random pairs of vertices, this can be shown to have a very low clustering coefficient, but it has very short paths. So the paths in between any pair of vertices are very short in general. So ideally, what we are used to in the human social network is high clustering coefficient, the fact that two of your friends are also very likely to know each other, but also very short paths, as we have discussed from Milgram's experiments and the 6 degrees of separation, that you can reach any other human being within just a few hops. That is what is characterized by the small world networks, which have a high clustering coefficient and short paths. So the reason I discussed the extended ring graph and the random graph is that you can actually show how to reach some types of small world networks by using these two types of graphs. Specifically, you take an extended ring graph, which has very structured edges, and you take one edge at a time and you make that edge point to random nodes. Okay, so you don't change the number of edges, but you take one edge at a time and make it point across random pairs of nodes. What happens as a result of doing that is that eventually, when you have changed all the edges over to being random, you get to a random graph, right? So you get from an extended ring graph to a random graph. And as a result, the clustering coefficient, which is very high for extended ring graphs, falls to be very low for random graphs. And the path length also, which is very high for extended ring graphs, also falls to be very low for random graphs. But they don't fall, these two things, the clustering coefficient and path length, don't fall at the same rate. In fact, the clustering coefficient falls much slower. It stays stable for much longer as you move from the ring graph to the random graph, while the path length falls very quickly. In other words, if you change just a few edges in your extended ring graph to be random edges, the path length falls very quickly, because now a lot of the short paths will go via these random edges because they join very disparate portions of the graph. So you get these region of networks in between the ring graphs and the random graphs, which have a very high clustering coefficient, as high as the extended ring graphs, but have a very short path length, almost as low as the random graphs. And that is the region of small world networks. Once again, this is not all the small world networks that exist. This is one particular class of small world networks that exist. But essentially, this is a way of deriving small world networks which have this high clustering coefficient and short path length characteristic, as we are used to in the 6 degrees of separation and in the human social network. So small world networks are all around us. The network of actors is a small world network. The network of humans is a small world network. All online social networks such as Facebook, Twitter, LinkedIn are small world networks. Many of them have been shown by measurements to be small world networks. The co-authorship network, where vertices are researchers and edges between researchers, joint researchers who have co-authored at least one paper together, is an example of a small world network. In fact, there is a concept of an Erdos number, where the Erdos number is a number of hops between Paul Erdos, who was a very famous scientist, and you in the co-authorship network. the World Wide Web, the internet, all of these are examples of small world networks which have a very high clustering coefficient and yet have a very short path length. And many of these networks have grown incrementally, and in fact they can be modeled by using a preferential model of growth, where you add vertices sequentially or iteratively. When you add a vertex to a graph, you add some edges, and you add an edge from the new vertex to an existing vertex v with a probability proportional to the number of neighbors of v. So the number of neighbors that v already has is proportional to the probability with which v will be added to the newly added vertex. So if you use this rule, you can actually show that you end up with small world networks. So we've discussed small world networks. Let's change track a little bit, and we'll come back to small world networks. Let's try and change track a little bit and discuss degree. The degree of a given vertex in a graph or a network is essentially the number of immediate one-hop neighbors. So if a vertex has 3 edges, then its degree is 3. So the degree distribution in a network or a graph is the probability that a given node or a given vertex has k edges. There are different kinds of degree distributions. You can have a regular graph where all the nodes have exactly identical degrees, or a Gaussian distribution, or you could have a random graph with an exponential distribution where the probability that you as a vertex have k edges is e power minus k times c, where c is a constant, some constant. And of course you have a power law graph, which says that the probability that you have k edges incident on you as a vertex is proportional to k power minus alpha, where alpha is a constant. This is a very interesting distribution because when k is pretty small, like 1, 2, or 3, this probability is very high, but as k increases, this probability drops off very quickly. So there's a very large number of vertices that have very low degrees, but there are a few vertices that have very high degrees as well. So how do you represent this? Well, this can be represented by what is known as the log-log plot. This is a very well-known plot. Here you represent the node degree on the x-axis. Instead, what you plot is the logarithm of the node degree. So you notice that the values of node degree go exponentially up, 1, 10, 100, and 1000 rather than 1, 10, 20, and 30. And on the y-axis, you plot the number of nodes that actually have that node degree. So for instance, if the point is x-axis equals 1 and y-axis equals 1 million, it means 1 million vertices in this graph each have a degree of 1. Okay, so you plot this distribution function. Once again, the y-axis is also logarithmic, as you notice here. It goes from 1, 100, 10,000, and 1 million. And the power law graph, if you plot the degree distribution for a power law graph, it's going to be a straight downward sloping line, as shown by this green line over here. Okay, so a very large number of vertices have very small degrees, as in the top left portion of the curve, but some vertices also have a very high degree, and these are the high degree vertices that are present in any power law graph. The exponential graph is not a straight downward sloping line. It's curved at its head, the top left portion of the plot, and it's also curved at its tail, the bottom right portion of the plot. There are also some distributions which are heavy tail distributions, which are straight downward sloping at their tail, the bottom right portion, but they are not necessarily heavy headed, which is top left portion. Okay, so they are almost like power law graphs in the sense that they have some vertices that have a very high degree, but they don't have that many vertices with a low enough degree as a power law graph. So this log-log plot is the best way for you to distinguish when a particular graph or when a particular network is either power law or heavy tail or exponential or something else. You draw the log-log plot. If it's a straight downward sloping line, it's a power law graph. If it has a heavy tail, if it has a straight tail, then it's heavy tailed, and otherwise it's some other distribution. So a lot of small world networks are also power law graphs. For instance, the internet backbone graph, the telephone call graph, protein networks. The World Wide Web graph is in fact a small world graph, and also a power law graph that has a value of alpha equals somewhere between 2.1 and 2.4. Remember that you have in a power law graph a degree of k with probability proportional to k power minus alpha. The Nutella peer-to-peer system has a heavy tail degree distribution. It's not necessarily power law, but it is heavy tail, so it has a straight downward sloping tail in the log-log plot. Power law networks are often called as scale-free networks. For instance, in Nutella, you have about 3.4 edges per vertex, independent of the number of vertices that are present in your network or in your graph. But then not all small world networks are power law graphs, and vice versa. For instance, co-authorship networks are small world, but they're not necessarily power law. And also not all power law graphs are small world. You can generate power law networks using the degree distribution where you have disconnected components of the graph where vertices are not necessarily reachable from each other, and so the graph is not a small world network. But many small world networks are in fact powered law graphs as far as you find them in reality. And because a lot of these graphs are small world and powered law, their resilience comes into the question. Most nodes have a small degree in these graphs, but a few nodes have a very high degree in these graphs. So if you launch an attack on one of these graphs, if the attack is random, for instance, you kill a very large number of randomly chosen nodes, this will not disconnect the graph. Okay, this is why attacking a powered law small world graph randomly is not very effective at all. But if you target some of these very high degree nodes in the powered law small world graph, this has a much higher chance of disconnecting the graph. Okay? And this is essentially why in the human body, for instance, because the graph of proteins in the human body or chemicals in the human body is a small world network and also a powered law network, a few of the nutrients are very high degree nodes in the graph. So essentially edges in this protein graph are edges that join two chemicals that react with each other, and so some nutrients happen to be have a much higher degree than other nutrients because they react with a lot of other chemicals in the body. And these nutrients are essentially the vitamins in the human body, the minerals that the human body requires, like calcium and potassium. So if you have a shortage of any of these vitamins or nutrients in your body or minerals, you're likely to be in trouble. But if you have a shortage of some of these other random chemicals that are there in your human body, then it's not likely that you're going to be affected all that much. Similarly, networks like the internet as well as the electric power grid, if you target a few high degree vertices, that's much more likely to disconnect the graph and cause a partition and cause outages in the network. But if you target randomly chosen vertices, and that's not likely to have any effect on the network itself. What about routing in these networks such as the internet? If you build shortest path routes between every pair of vertices, it turns out that in small world powered law networks, most of these shortest path routes will pass through some high degree vertices in the graphs. So these high degree vertices get highly overloaded with these shortest paths, and they're likely to suffer congestions and perhaps in fact even crash. And as we have seen from the previous slide, if you disconnect some of these high degree vertices, it's also likely that the entire graph will be disconnected and you might have an outage in the network. So this should tell you why there are these frequent outages in networks such as the internet, in networks such as the electric power grid. It's because these high degree vertices suffer congestion and they might crash as a result of that, and because when they do, they disconnect large portions of the graph and you end up having an outage. So in the internet, one of the solutions to this is to add some amount of randomness in the path selection. You don't always prefer the shortest path, but you take some hops in your path that are random hops, and this avoids going through the high degree vertices with some probability, and so the load on the high degree vertices reduces, they're less congested, and they have a lower chance of crashing. To wrap up our discussion of structure of networks, networks are all around us, both man-made networks such as the internet, the World Wide Web, and peer-to-peer networks, as well as natural networks that have evolved over centuries and millennia, such as protein networks and the human social network. Yet a lot of these networks have common characteristics. Many of them are small world networks that have a very high clustering coefficient and very short path lengths. And they're also power law, where you have a very large number of vertices that have a small degree, but some vertices have very high degrees. And it's useful to know these characteristics because when you design distributed systems and distributed protocols that run over networks like the internet, that run over, that deal with social networks such as the online social networks, it's useful to know these characteristics so that you know exactly how your protocol is going to behave on these when it sends packets, when it sends messages over these networks, or when you run a graph processing algorithm that is dealing with such powered law graphs. So you can better predict how your distributed system is going to behave when it runs over such networks, small world networks, such as the internet. So in this next series of lectures, we're going to see the important topic of scheduling. In particular, today we're going to see single processor scheduling. But let's start from a higher level. So why do you need scheduling at all? Well, in any cloud computing system, you have multiple tasks to schedule. For instance, if you just consider your laptop or workstation or even your mobile device, there are multiple processes that are running on that device. On your laptop, you have your browser running, your editor running, maybe you have an IDE running, and essentially the operating system needs to schedule these processes across the limited resources that it has. Primarily, the main resource is the processor or the CPU, and if you have a single core OS or single core machine, then you have a particular series of scheduling problems. And of course, you might have a multi-core machine where you might be able to schedule multiple processes simultaneously. But once again, typically the number of processes is much more than the number of processors that you have, the number of CPU that you have. And so scheduling here becomes a challenge. In a cloud computing cluster, you might have a Hadoop job running, and that Hadoop job has multiple tasks. So the cluster needs to decide where to schedule each task of the Hadoop job. You might have multiple Hadoop jobs, each with their own tasks, and they might be competing for resources. And now the cloud scheduler needs to decide where to schedule these different tasks of these different Hadoop jobs. You have a large number of tasks, and there are limited resources that these tasks absolutely need. So each task typically needs some amount of processing capacity, a processor, some amount of memory, and of course it needs disk and network as well. But typically scheduling algorithms vary about processor and memory because these are the resources for which there is most contention. There are two goals of scheduling algorithms. The first is to increase the throughput, or the number of jobs you can execute per time unit. And related to that is reducing the response time, or reducing the time that it takes one job to complete in your system. Okay, so essentially we'll just take into account the completion time of jobs. The second is high utilization of resources. You want your resource to be utilized as much as possible. You want all of your processors to be utilized 100% of the time, all of your memory to be utilized 100% of the time, so that you're making the most out of the resources that you invested your money in. So let's look at single processor scheduling in this lecture. So you have just one processor in this particular problem, and you might have multiple tasks that are trying to compete for these resources. In this example, I have three tasks: task 1, task 2, task 3. Task 1 arrives at time 0. It has a running time of 10 time units. Task 2 arrives at time 6. It has a running time of 5 time units. And task 3 arrives at time 8. It has a running time of 3 time units. So you need to decide when to schedule each of these tasks at what time on this single processor. So one of the basic scheduling algorithms is what is known as FIFO, or first in, first out. This is also known as FCFS, or first come, first serve. So in this algorithm, you maintain the tasks in a queue in the order in which the tasks arrive. So tasks that arrived earlier are ahead in the queue, tasks that arrive later are later on in the queue. Whenever a processor is free, you dequeue the task at the head of the queue and you schedule it on the processor. So for instance, at time 0, when task 1 arrives, place it in the queue. It's the only task right now, and so it executes until time 6. At that point, task 2 arrives, it's placed in the queue, but then task 1 is still executing on the processor, so task 1 is allowed to complete. At time 8, task 3 arrives and it's added to the queue, but after task 2. At time 10, when task 1 finishes, the head of the queue is task 2, so that's dequeued and it's scheduled on the processor. It runs until completion, which happens at time 15, at which time, once again, the head of the queue, which is task 3 now, is dequeued and is scheduled on the processor. Task 3 finishes at time 18. So task 1 finished at time 10, task 2, which arrived second, finished at time 15, task 3, which arrived last, finished at time 18. This is the FIFO algorithm, and even though we are discussing it for a single processor scenario here, FIFO is in fact used by a variety of different cloud computing schedulers, including the Hadoop scheduler. So how about the performance of FIFO or FCFS? Well, the average completion time, which is really what we care about, we want completion time to be as small as possible, may be kind of high for FIFO. For instance, for example, the average completion time can be calculated by adding the completion times for the 3 tasks and then dividing them by 3. So that's 10 plus 15 plus 18 by 3, or 43 by 3, or 14.33 time units. This is on the higher side, I'm telling you, but can we do better than 14.33? What is another scheduling algorithm that does better than 14.33? Well, that better scheduling algorithm is known as shortest task first. So in this particular approach, again, you maintain all the tasks in a queue, but not in the order of arrival. Instead, you maintain the tasks in increasing order of running time. So tasks that are shorter are maintained towards the head of the queue, and tasks that are longer are maintained at the tail of the queue. Whenever the processor is free, you dequeue the head task and you schedule it on the processor. So once again, let's go to an example where we have 3 tasks, tasks 1, 2, and 3 with task lengths of 10, 5, and 3. The arrival times here are all zeros because I want to show you an example where the STF scheduling algorithm in fact has to make decisions among tasks. And so here task 3, which has the shortest length, is chosen to run first. It starts running at time 0, finishes at time 3, at which point task 2, which is the next shortest task, is scheduled. It runs from time 3, finishes at time 8, and finally task 1, the longest task, is run from time 8 to time 18. So this is the shortest task first scheduling algorithm, STF. Sometimes this algorithm is also known as SJF, or shortest job first scheduling algorithm. But we'll stick with STF because I want to maintain the uniformity of terminology here. So why does STF do better than FIFO? Well, STF in fact can be proved, formally proved, to create the shortest or the smallest average completion time among all possible scheduling approaches for a single processor system. So given a single processor system and a bunch of tasks that you need to schedule, among all the possible scheduling strategies that you might have, the STF strategy gives you the smallest average completion time. For instance, for our previous example, the average completion time of STF is the sum of the 3 completion times for the 3 tasks divided by 3, which happens to be 18 plus 8 plus 3 divided by 3, which is 29 by 3, which is 9.66. And this is much smaller than the completion time of 14.33, which we had for the FIFO or FCFS approach. The other nice thing about STF is that it is actually a special case of what is known as priority scheduling. In this particular STF scheduling approach, we sorted the tasks according to their running time. And in fact, we treated the running time as a priority, but instead the priority might be specified by the user. For instance, the user might specify a higher priority for interactive tasks that involve keyboard and mouse input, but a lower priority for background batch tasks that don't require any user input but have an output at the end of a long run. You would always place the higher priority tasks at the head of the queue, and whenever those tasks wanted to compute, you let them run on the processor. A third scheduling algorithm is what is known as round-robin scheduling algorithm. In this scheduling algorithm, you allow tasks to be run in pieces or in chunks. In other words, you split up a task into small quanta, and the quantum may be just a small time unit, such as say 1 time unit as in our example here, and you run only a portion of a task at the head of the queue. When that portion of the task is done, you preempt that task. In other words, you save the task of the state of that task, and then you add the task back again to the tail of the queue. You take the head of the queue task again, whatever task happens to be the head of the queue, and then you start running that task at the processor. In order to run this again, you may need to bring back in the saved state of that task if it was preempted in the past. So again, in our example, we go back to our example of 3 tasks 1, 2, and 3, which arrive at times 0, 6, and 8 respectively. So task 1 arrives first. It's the only one, so it's run so that it occupies the entire processor until time 6, at which point of time task 2 arrives, and so task 2 is now run for 1 time unit. And then when it's run for 1 time unit, it is put back at the end of the queue, and task 1 is allowed to run. So at this point of time, task 1 has run for 6 plus 1, 7 time units. Task 2 has run for only 1 time unit. Then at time 8, task 3 arrives, and now it is allowed to run for 1 time unit because it's at the head of the queue. And now after it runs for 1 time unit, it's put at the tail of the queue, and then task 1 and task 2 are allowed to run, and then again task 3. Okay, so this pattern repeats again. Then again you have all the 3 tasks run, and at this point of time, task 1 has run for 9 time units. You have 6 plus 3 greens, that's 9 greens. Task 2 has run for 3 time units, and task 3 here, the blue ones, has run for 3 time units, 1, 2, and 3. And so task 3 is actually done at time 15. Okay. So after this, you have only task 1 and task 2 to cycle through, so you round robin through them, and then this continues for a while. At this point of time, actually task 1 is done at time instant 17. Round robin essentially gives a fair share of the resource, the processor, to all the tasks that are present in the system. So when do you prefer round robin, and when do you prefer shortest task first or FIFO? Well, round robin is more preferable for interactive applications that periodically need access to the processor so that they can run and process things like the keyboard input, the mouse input, and so on and so forth. Okay? These are applications where the user needs quick responses from the system. On the other hand, FIFO or shortest task first is more preferable for batch applications where the user submits a job, goes away for a while, and then comes back later on to get the result. For these, you don't necessarily need to have applications that run in quanta, but you can give them access to the CPU all at once. And in fact, there are many hybrid scheduling approaches that combine both the round robin that we have seen and the FIFO STF that we have seen. These are known as hierarchical approaches. So to wrap up our discussion of single process scheduling algorithms, we've discussed some of the classical algorithms, including FIFO or FCFS, which schedules tasks in the order of arrival, shortest task first, which schedules the smaller tasks first, and priority, which is a generalized case of the shortest task first scheduling, where each task is scheduled in the order of the user specified priority. Also, round robin scheduling algorithms, which are well matched for interactive applications, where each task is given small shares to run. And of course, this is only a sliver of the many scheduling algorithms that are out there, which I encourage you to look up. We haven't discussed cloud scheduling yet, and that's what we're going to discuss in the next lecture in this series. Hi there. In this lecture, we're going to see two types of scheduling approaches that are very popularly used with Hadoop clusters today. So a Hadoop job, if you recall, consists of map tasks and reduce tasks. When you have one job in the cluster, and that's the only job in the cluster, its tasks can occupy the entire cluster. So different resources in the cluster can be allocated to that particular job's tasks. However, you might have multiple customers with multiple jobs, and these users, customers, or jobs are known as tenants in the cluster. So you have essentially a multi-tenant system where there are multiple tenants occupying the cluster and competing for resources that the cluster has. So you need an approach or a strategy to schedule all these jobs from across the different tenants. And when I say schedule jobs, I essentially mean schedule the tasks that are inside these jobs. And sometimes you want to be fair across the different tenants in your system. You don't want to give one tenant much more resources than another tenant. You do not want to allow one tenant to completely hog your cluster and deny access to the cluster to the other tenants. So Hadoop Yarn has two schedulers that are very popular with installations today, the Hadoop Capacity Scheduler and the Hadoop Fair Scheduler. We'll discuss the Capacity Scheduler first and then the Fair Scheduler. The Hadoop Capacity Scheduler contains multiple queues. If you recall from our discussion of single process scheduling algorithms, the queues essentially contain jobs. So each queue contains multiple jobs. Each queue is guaranteed some portion of the cluster capacity. For instance, you might configure your system with two queues, Q1, which has 80% of the cluster, and Q2, which has 20% of the cluster. And in this case, you might have the higher priority jobs in your system go to Q1 because it has a lot more of the resources in the cluster. For jobs that are within the same queue, typically first in first out scheduling or first come first served scheduling, FCFS, FIFO FCFS is used. This is again something that you have seen in the single processor scheduling approach. But essentially what happens here is that a job that arrived earlier would be given resources first. So whatever resources it needs for its tasks, it's given first. And then when that job is done, the next job in the queue is taken and given resources. If the job is not able to fill that entire queue's capacity, for instance, if a job in Q1 occupies only 40% of the cluster, another job can be allowed to run concurrently with it in Q1 itself. So FIFO is typically used, but again, it's not necessarily used. You could modify the Hadoop Capacity Scheduler to use a different approach. Administrators are allowed to configure the queues, these queues that I've discussed. So you can configure each queue to have limits. There might be a soft limit, which specifies how much percentage of the cluster resources that particular queue is guaranteed to occupy. Optionally, you can also specify a hard limit, which is the maximum percentage of the cluster resources that queue is guaranteed to occupy. So this means that the queue cannot cross the hard limit. So if the hard limit is 90%, it means that that queue cannot ever be given more than 90% of the cluster resources. Elasticity is allowed by this particular approach because if, for instance, there is only one queue that has jobs, then the queue might expand as much as possible to occupy the entire cluster. So if your hard cap, for instance, your hard limit is 100%, then that queue could be expanded to occupy the entire cluster, and its jobs can get the entire cluster as long as resources are free. But if there are other queues in the system that are below their capacity limit, so for instance, if another queue had a soft limit of 20% and it is running at 5%, it now needs to get more resources because, for instance, it might be having more jobs. That other queue may need to be given resources. which means that this queue that is currently occupying the entire cluster needs to give up some of its resources. So one way to do this might be to kill the tasks in that queue, but that's not what is done in the Hadoop capacity scheduler approach. Instead, you do not allow preemption at all because you do not want to waste tasks that are sort of partway through. You don't want to kill any tasks. Instead, you simply wait for those tasks to finish. When a task finishes, you take away that part of the resource from the first queue and give it to the other queue that is now requiring resources. So essentially, the elasticity or the scaling in portion here happens slowly as tasks finish. The resources are then taken away from that queue which the tasks belong to, and it is given to the other queue that is requiring resources. Okay, so this approach here that you're seeing is slightly different in the Hadoop Fair Scheduler approach, which we'll see in a few slides. A few other features in the Hadoop Capacity Scheduler: the queues themselves can be hierarchical, so a queue might contain child subqueues, which may then contain child subqueues, and so on and so forth. And this is useful so that child subqueues can be made to share resources equally in between each other. So for instance, if a queue is given to one particular organization, that organization might have multiple departments, and these departments are each given a child subqueue, and these child subqueues now share resources equally among each other. Scheduling in the Hadoop Capacity Scheduler can also take memory requirements into account, where the memory is typically specified by the user. And as of this particular recording, the Hadoop Capacity Scheduler only supports memory as a resource being specified. It does not support multiple resources being specified. So let's look at the other scheduler, the Hadoop Fair Scheduler. Here, the goal is to target a multi-tenant system where you have multiple jobs or users occupying a cluster, and you want to ensure that all the jobs get an equal share of the resources in the cluster. But of course, when only one job is present, you want it to get the entire cluster if that job requires the entire cluster. So fairness does not mean you starve a job even though resources are available. However, as other jobs arrive in the cluster, each job is given an equal percentage of the cluster resources. For instance, each job might be given an equal number of cluster-wide yarn containers, where a container is a set of processor and memory resources that is enough to run one task of one job. Okay, container is a well-accepted term in yarn, which you have seen elsewhere in the course. So the Hadoop Fair Scheduler divides the cluster into pools, and typically there is one pool per user. The resources are divided equally among pools. This ensures that each user gets a fair share of the cluster because each pool gets the same amount of resources. Within each pool, you can use either fair share scheduling, so all the jobs belonging to one user can either share resources fairly with each other, or you could use first in, first out, or first come, first serve scheduling, FIFO FCFS, as you have seen before. This is also configurable. You can also configure what kind of scheduling algorithm you want to use within each pool. Some pools are specified, are configured to have minimum shares. This is the minimum percentage of the cluster resources that particular pool is guaranteed. When for a particular pool the minimum share has not been met for a while, then you take resources away from the other pools and you give it to this pool. And here the Hadoop Fair Scheduler differs from the Hadoop Capacity Scheduler in how it takes away resources. It takes away resources from a pool by in fact killing some of the tasks in that pool. In fact, it preempts the jobs in those pools by killing some of the currently running tasks of those jobs in the pool from which it wants to take away resources. These tasks can be restarted later anyway, and these tasks are idempotent. By idempotent, I mean that if you run the tasks multiple times on the same input, you're going to get the same output. So there are no side effects of these tasks. So killing a task partway through and then just restarting it later on the original input is fine. It leads to some wasted work, but this wasted work can be minimized by picking as a victim to kill some tasks which were started recently. So tasks that have only started recently are picked first to be killed, and then if you need to kill more tasks, you kill tasks that started farther in the past. This again minimizes the amount of wasted work because tasks that started recently have probably done just a little bit of work, and so killing them will minimize the amount of wasted work. But it does result in some wasted work. There have been some proposals since then from the research community that have proposed, in fact, saving the state and then rerunning the tasks starting from their saved state. However, the Hadoop Fair Scheduler does not support that. A few other features in the Hadoop Fair Scheduler: you can also set limits on the number of concurrent jobs per user, a limit on the number of concurrent jobs per pool, and the limit on the number of concurrent tasks per pool. All of this prevents a cluster from being hogged by just one user or by just one job. It also prevents too many tasks or too many jobs of one user from competing for a small number of resources that are being allocated to that particular pool. So far, we have seen that Hadoop Capacity Scheduler and Hadoop Fair Scheduler tend to use the FIFO, or the first come, first serve, or first in, first out approach, FIFO FCFS. But as we have seen in the previous lecture in the series, FIFO is not necessarily optimal as far as completion time is concerned. And the question might be arising in your mind, why not use shortest task first instead? In fact, that is optimal, right, as we know it. The challenge with Hadoop is that it's hard to estimate the expected running time of a task before the task is actually completed, right? So it's hard. So when tasks are generated by a Hadoop job, the tasks do not come specified with the exact time that the task is going to run for. Okay, and as a programmer, you don't know that either. So a way to combat this, to address this, and so that you can use algorithms like shortest task first, is to estimate the task length. Okay, so a few approaches that can be used. So within a job, you can calculate the running time of a task, or estimate the running time of a task as being proportional to the size of its input. So if one particular job with a 1 megabyte input took 20 seconds, one task with a 1 megabyte input took 20 seconds to compute, another task with a 2 megabyte input, twice the size of the first task, will take 40 seconds to compute. You can also do the estimation across jobs, where you can calculate the running time of a task in a given job as the average of other tasks in that given job. So you can take the average running time across all the tasks in that job that have completed, and then based on that you can calculate the running time of a task. And then also you can weight this by the input size of that particular task to get a more accurate running estimate. But of course, these are only estimates, and so they may not actually be true, and so you may not actually get an optimal running time here, even though you're using shortest task first, because the estimates may be off. Okay, there's been a lot of recent research results and research work in this particular area here. So to wrap up a discussion of Hadoop scheduling in Yarn, we have discussed two schedulers: Hadoop Capacity Scheduler, which tends to be the default scheduler, and the Hadoop Fair Scheduler, which is used in a variety of different scenarios and a variety of different Hadoop clusters. Yet so far in this lecture and the previous lecture, we've only talked about one kind of resource. In the previous lecture, it was processor. In this lecture, it's predominantly memory. But typically, jobs such as VMs, for instance, have multi-resource requirements. Some jobs may have some CPU requirements and also some memory requirements. And how do you handle these? We'll discuss this in the next lecture. In this lecture of the scheduling series, we're going to see dominant resource fair scheduling, which is a new concept that has been invented in just the last few years, but has had a lot of impact. So here we're discussing the problem of scheduling large numbers of jobs across a cluster. For instance, scheduling VMs in a cloud or in a cluster. Different jobs may have different requirements, and these requirements may span multiple resources. So for instance, a job 1 may have tasks where each task requires 2 CPUs and 8 gigabytes. Job 2 may have tasks where each task requires 6 CPUs and 2 gigabytes. So then the questions arise when you have these jobs that are together in a cluster. How do you schedule these jobs in a manner that is fair across different jobs? In other words, how many tasks of each job in this particular example, our example, do we allow in the cluster to run concurrently so that you ensure fairness as far as resource allocation is concerned across different jobs? In fact, what does fairness even mean in this particular case? So dominant resource fairness, or DRF, addresses these questions. It was proposed by researchers from University of California, Berkeley. It proposes a notion of fairness across jobs with where the jobs have multi-resource requirements. And the researchers showed that the dominant resource fairness is fair for multi-tenant systems. It is strategy proof. This means that tenants cannot benefit by lying. So if a tenant lies about its requirements, it does not really benefit by it. It can only suffer or just stay where it is. It's also envy-free, which means that a tenant cannot envy the allocation that is given to another tenant in the system. Okay, all of these are desirable properties because they eliminate the tenants from strategizing the system and from gaming the system. So DRF is useful in scheduling virtual machines in a cluster. It's also useful in scheduling Hadoop in a cluster. It's useful wherever you have jobs and these jobs have tasks which need to be scheduled in a cluster, and the tasks themselves have multi-resource requirements. DRF is used in Mesos, an operating system that was invented by researchers at Berkeley that is intended, and the operating system is intended as a distributed operating system for cloud environments. And DRF-like strategies are also used in cloud computing operating systems that have been built by several cloud computing companies. How does DRF work? Well, let's look at DRF through our example. So job 1, once again, our example has tasks where each task requires 2 CPUs and 8 gigabytes. We denote that as job 1's resource vector, which consists of 2 CPUs, 8 gigabytes, where 8 gigabytes is the RAM or the memory required by the job. Job 2's task requires 6 CPUs and 2 gigabytes, so its resource vector is 6, 2. Now consider a cloud or a data center which has 18 CPUs and 36 gigabytes of RAM. That's the resource vector of the cloud itself. Now let's look at job 1. So each task of job 1 consumes a percentage of total CPUs, which is, it requires 2 CPUs, and the total number of CPUs in the cloud is 18. So the percentage of the total CPUs consumed by one task from job 1 is 2 by 18, which is 1/9. Similarly, each task of job 1 requires 8 gigabytes of RAM. The total RAM present in the cluster is 36, so the percentage consumed by each task of job 1 is 8 by 36, which is 2 by 9. So 1 by 9 is less than 2 by 9, which means that job 1's dominant resource is the orange resource, which is RAM. So job 1 is more memory intensive or RAM intensive than it is CPU intensive. So that's job 1. Let's do a similar calculation for job 2. Job 2's single task consumes percentage of total CPUs, which is 6 CPUs divided by 18 total CPUs, that's 6 by 18. As far as RAM is concerned, each consumes 2 gigabytes of RAM. The total gigabytes of RAM is 36, so that's 2 by 36, which is 1 by 18. Here, the blue value, 6 by 18, is larger than the orange value. And so 6 by 18 is greater than 1 by 18, which means that job 2's dominant resource is CPU. So it is more CPU intensive than it is memory intensive. So job 1's dominant resource was RAM, and job 2's dominant resource is CPU. So different jobs may have different resource types that they are dominant on. And DRF ensures the following property. For a given job, the percentage of its dominant resource type that it gets cluster-wide is the same for all jobs. In other words, you allocate tasks to job 1 and you allocate tasks to job 2 so that the total percentage of RAM that job 1's total tasks get is equal to the total percentage of CPU that job 2's tasks get, because RAM is the dominant resource of job 1 and CPU is the dominant resource of job 2. These constraints can be written as linear equations and solved. We won't go through those equations and solutions here. Let me just tell you the solution for our particular example. Okay, so for our example, the solution turns out to be that job 1 gets 3 tasks, each with the resource vector 2 CPUs and 8 gigabytes, and job 2 gets 2 tasks, each with the resource vector 6 CPUs and 2 gigabytes. Let's ensure that this actually satisfies the DRF fairness rule. So job 1's percentage of RAM is the total number of tasks given to job 1 times the amount of RAM per task, that's the total RAM to job 1, the numerator, divided by the total cluster RAM. So the number of tasks it gets is 3 times 8 gigabytes per task divided by 36 gigabytes, that's 2 by 3. Let's do the similar calculation for job 2's dominant resource, which is CPU. The number of tasks given to job 2 is 2. The CPU per task is 6 CPUs divided by the total number of cluster CPUs, which is 18. So that's 2 times 6 by 18, which is also 2 over 3. Okay, so that's that ensures that job 1's percentage of RAM equals the job 2's percentage of CPU. So every job gets the same percentage of the cluster as far as its dominant resource is concerned. And you can verify that allocating job 1 3 tasks and allocating job 2 2 tasks also satisfies the total number of resources that you have. Right? So job 1 gets 3 times 2 6 CPUs, job 2 gets 2 times 6 12 CPUs, so that's a total of 18 CPUs. You do have 18 CPUs in the system. The RAM given to job 1 is 3 times 8 24. Job 2 gets 2 times 2 4, so that's 28 gigabytes, which is less than the 36 gigabytes you have. So you're using less than the total amount of memory in your system, but that's fine because it's the price you pay for fairness in your system. So DRF, even though we've discussed it only for 2 types of resources, where a resource vector has only 2 components, the CPU and the RAM, it also generalizes to cases where jobs might have multiple resource requirements. It also generalizes to cases where you have multiple jobs, not just 2 jobs in your system. So you can have multiple jobs, and each job can have CPU requirements, memory requirements, also network, and maybe even disk requirements, and so on and so forth, and DRF would generalize even to those. DRF essentially ensures that each job gets a fair share of that type of resource which that particular job desires the most, meaning its dominant resource. And this is why DRF is in fact fair across different jobs with multi-resource requirements. So to wrap up our entire discussion of scheduling, scheduling is a very important problem in cloud computing because you have limited resources, typically processor and memory resources, and yet you have a lot of jobs with tasks that require access to these resources. So which jobs run when on which resources is the scheduling problem. We've discussed classical single process scheduling algorithms such as first in, first out, shortest task first, priority, and round robin. We've also discussed Hadoop scheduling strategies that are popular today, such as Capacity Scheduler and the Hadoop Fair Scheduler. And finally, we've discussed strategies that are fair across multiple tenants in a multi-tenant cloud environment. Especially, we've discussed the dominant resource fairness strategy, which is actually gaining popularity today.
First, download the Apache Storm from their wiki website and extract it to your local directory. Once done, first thing we need to do is to change the configuration file to update the details of Storm topology. Let's now open storm.yaml file. Modify the path to Storm's local directory where Storm saves its intermediate files. Also update the details of the Zookeeper server. Similarly, modify the details of Nimbus and update the port of Storm UI. Here we're specifying the Storm worker node details. We can leave other configurations default. We can see there are 4 worker nodes specified. Once the changes are done, save the configuration file and let's move on to configuring Zookeeper. Download the Zookeeper and extract the Zookeeper in a local directory. Let's modify the zoo.conf file to update the Zookeeper's data directory path. This is the path where Zookeeper saves its local files. We can leave the other configurations default. Once the configurations are saved, let's start the Zookeeper. The Zookeeper has been started now. Now let's start Nimbus and supervisors in a similar fashion. To start this Nimbus, we can use the storm command with the argument Nimbus. It may take a while to start, so meanwhile we can start the supervisor node in the similar fashion. Use the same storm command with the argument supervisor to start the supervisor. Storm also provides inbuilt support for UI, which also runs on the same port configured in the storm.yaml before. To start the UI, use the same storm command with the argument UI. It may take a few seconds for the topology to start. The UI is set to start here. Once it's started, we can open the Storm UI on any browser at the specified port. So now that it has started, let's open a browser and go to the port number 8080. The Storm UI provides a summary of cluster, and we can view all the previous running topologies and their configurations. We can also see the Nimbus configurations listed here. We can now view one of the topology which was run earlier. It also gives a UI, mention how long it has been running, what is the status as of now, and also provides options to terminate, activate, kill the topology from the UI. We can also see the number of spouts and bolts configured for this topology. And it also provides a topology visualization tool where we can actually see how spouts and bolts are connected. In this example, we can see that there is one spout connected to a split bolt, and the split bolt is in turn connected to a count bolt. It also has information about the topology configuration, which is also available in the YAML file seen before. We can also look in detail of any of those specific bolts or spouts. Here we are taking a look at the spout. We can also see the number of executors which was active during the topology execution. This is same as what we had configured in the storm.yml file. Now that we have seen how to start the topology and navigate the UI, let's dive into the demo of viewing top-end tweets. The first thing we need to do is create a Java file where we design the topology. We use the topology builder for this purpose provided by the Storm. Since we are going to use Twitter, we need also the Twitter authentication to be provided in the code. So once that's done, let's see how we can create spouts and bolts and connect the topology. We can see that we have a single spout called tweet spout, which is connected to the Twitter spout. We are also using a set of bolts. The first bolt which we connect this spout to is called parse tweet bolt. It is connected using shuffle grouping on the tweet spout keyword with a parallelism of 10. This indicates number of tasks which run inside the bolt. The parse tweet bolt is in turn connected to another bolt called count bolt via fields grouping on the field tweet word. So all these bolts are in turn classes. The highlighted bolts are a set of open source bolts provided by the Storm team. One of it is intermediate rankings bolt, which is connected via fields grouping on the field word coming from the count bolt. And the other one is total rankings bolt, which is connected via global grouping on the intermediate ranker bolt. The final bolt is the report bolt, which is connected via global grouping on the total ranker bolt to give us the final top and trending words. All these bolts are intern classes where we define the functionality of what to do with the tuple and how to emit the tuple. We'll look at one of the bolts, parse tweet bolt, in detail now. Let's see how we can create a new bolt. Here we are creating a bolt, parse tweet bolt, which is extending the base rich bolt provided by the Storm. The functionality of this bolt is to prevent stop words or skip words from getting counted. It has methods such as prepare, execute, and declare output fields. The declare output fields method specify the name of the field on which the tuple will be emitted on. So here in this case it's tweet word. The execute method is used to specify the functionality of how to process the input tuple and emit. Here we can see we are using the collector.emit function to emit a value. The tweet word is the same field name on which the fields grouping is done in the count bolt. Similarly, we have functionalities defined for each of the classes of the bolts. So now that we have seen in code how to create the topology, let's see how we can feed that into the Nimbus. The first thing we need to do is create a package. We can use mvn package command to create a jar file. It may take a while for the package to complete, pulling all the dependencies. Once it's done, it will create a snapshot jar with dependencies.jar file, which we can feed into the Nimbus. The Nimbus will then take care to distribute among its supervisor nodes. Remember, no code is executed in Nimbus. So let's wait for the build process to complete, and then we can look at how we can feed this data into the Nimbus. So now that the process is completed, we can use the Storm's jar command and specify the jar which was created along with the base class where the topology is designed. So this way we can feed the data jar into the Nimbus, and the Storm topology is started now. We also have a simple web server which is connected to the Storm in the backend to visualize the top trending tweets in real time. As the Storm continues to run, the web page will be able to show you the top trending words in real time, increasing in size depending on their count.
In this lecture, we'll be going over Apache Spark, which is a big data analytics framework that came out of UC Berkeley in 2012, and ever since then, it has gained a lot of traction both in academia and in industry. But before we get into the nitty-gritty of the system itself, let's try and understand why people thought it was required. Because by the time it appeared on the scene, we had already had MapReduce for quite a while, and we know that MapReduce simplifies batch processing on large commodity clusters to a very significant extent. However, MapReduce suffers from a problem, and that problem is that sometimes it can be quite slow. This is because at the end of the map phase, it has to write all of the output of the map tasks to disk. We know that this is actually done for good reason. This is done because of fault tolerance. However, it can make the runtime of the job very, very long. So, the main motivation behind Spark is that MapReduce can actually be infeasible for some kinds of applications. For example, in iterative applications, where you have to iterate over the same piece of data multiple times until you converge to a result, it is very expensive to keep saving data to disk at the end of every map phase. Examples of these kinds of applications include training jobs for machine learning models and graph processing applications. Another kind of applications for which MapReduce doesn't really work is interactive applications. These applications involve running ad hoc queries over some piece of data multiple times in order to get quick results. So we can summarize this and say that the problem with MapReduce is actually that it lacks efficient data sharing between each of its stages. So before Spark appeared on the scene, different companies had created different systems to solve these problems in individual domains. For example, Prigil is a graph processing system that came out of Google to solve graph processing problems quickly. So let's take a look at the solution that Spark proposes. Spark proposes a new data abstraction called Resilient Distributed Datasets, or RDDs for short. RDDs are simply immutable partitioned collection of records. What this means is, once an RDD is created, it cannot be changed, and it is partitioned in different ways across nodes on a cluster. RDDs can be built through different kinds of coarse-grained transformations. What this means is you can't manipulate individual records in an RDD. Either you apply an operation to the whole RDD or not at all. Finally, RDDs can be cached in memory for efficient reuse. Let's look at an example to see what this means. So let's imagine that we want to perform word count on some input data set, and our input data set is stored in a data store like HDFS. All we have to do is we have to read the input data into memory, and this will create our first RDD. Now, as I said, you can partition your RDD in different ways across the cluster. Here, we've just partitioned our RDD on 2 nodes in the cluster. Next, as we do in word count, we simply apply our map function, and this creates a new RDD. We take the resultant RDD and apply the reduce function to it to get our final result. Now we can cache this final result into memory so that if anybody wants to run ad hoc queries on the result, they can. However, the moment you talk about putting data in memory, you've created a problem, and the problem is that of fault tolerance. What if one of the nodes that contains a portion of the RDD fails? In order to solve this problem, Spark proposes an interesting idea, and that is of lineage. All they do there is they log all of the coarse-grained operations that were applied on each individual RDD. What this means is, if you lose a portion of the RDD, all you have to do is you fetch the input data and you apply the log of coarse-grained operations to get your result back. The best part of this is, if there is no failure, you paid no cost of checkpointing. So now in our simple example, let's try and understand what the lineage looks like. So actually, it's pretty straightforward. All you did was you read your input data, you applied a map function to it, and finally you performed a reduce to get your result. And just this is your lineage. So then what happens if a particular node fails and you lose a portion of your RDD? Let's assume that this node failed. Then all you have to do is get your input from the previous stage. That would just be the input from the map stage that took place here, and then you would just simply apply the reduce function to it to get your data back. So simply RDDs track the graph of transformations that built them, so that if there is a failure, all they have to do is they fetch the input data and they apply the coarse-grained transformation to it to reconstruct the lost partition. Now that we understand how Spark works, what can we actually do with it? So we can create RDDs through different kinds of operations. For example, you can apply a filter to a pre-existing RDD to remove some of its records and create a new RDD. You can also perform actions on the RDDs themselves. For example, you can count the number of individual records that occur in an RDD. Spark also gives you control over how you can partition your RDDs, and I'll give a more interesting example in the next slide. And it also allows you to choose whether you want to persist your RDD onto disk or not. So this is different from MapReduce because here, persisting your RDD onto disk is a choice that you have. It is not fundamentally built into the framework. So let's see how Spark allows you to partition your data in ways that can help you reduce runtime of your job. So the example that we'll look at here is that of PageRank, and PageRank is an iterative graph processing algorithm. What you want to do in PageRank is to find the most popular web pages in a set of web pages that you might have from the web. The way that you would do is, you'd find the popularity of a web page by finding out how many other URLs point to that web page. However, just the number of URLs that point to a web page isn't enough. If a popular web page points to your website, that could also give you a lot of hits. Think of it this way. If your friend creates a website and points to your website, that doesn't really help you. But if Lady Gaga creates a website and points to your website, that means that you could get a lot of hits. So the way that we model this in terms of an algorithm is, first, you have two input data sets. First, you have the links dataset, which just consists of all of the URLs that you have and their neighbors. And you also have the ranks dataset, which just consists of a rank per URL that you had in the links dataset. In the beginning, all of the ranks for all of the URLs are the same. So what you do is you perform a join between these two datasets based on the URL, and you calculate how much each URL contributes to a page that it is pointing to. Given this information, you can update the ranks for each URL. Then you perform a join again to find the updated contributions, and you continue to do this until the ranks converge. Now, if you think about it, you can see that we are performing joins repeatedly. Now, if datasets are partitioned naively across the cluster, that would mean that for each of the join, a lot of data would have to go over the network, and this would become very, very expensive. However, what you could do is, you could use, for example, hash partitioning to make sure that the same URLs from the links and the ranks dataset end up on the same nodes. In this way, the join operation just becomes a local operation. Because of the different kinds of operations that Spark supports, it can be used to build different kinds of programming models. In fact, people have built stream processing, graph processing, and machine learning systems on top of it. For example, Apache Mahout is a distributed machine learning framework that used to use Hadoop for its backend, but has now switched to using Apache Spark. So in the next few slides, I'll show you how Apache Spark can support different kinds of applications, particularly graph processing applications. They have a library that is called GraphX, which allows you to run graph processing applications on top of Spark. The model that GraphX supports is the gather, apply, scatter model that you have studied in a different part of this course. So on the left here, we have a logical representation of a graph. All you have there is a bunch of nodes that are connected to each other through edges. However, physically, we could represent this data through an adjacency list where you simply maintain a list of all of the vertices and their neighbors. The way that Spark chooses to represent this information is through triplets. So triplets just maintain all of the possible combinations of vertices and neighbor pairs. The three parts in the triplets are the two vertices that are the neighbors and the edge that is between them. So let's see how we can run gather, apply, scatter on top of GraphX. In our example, we'll just be considering what happens at node A. So in order to perform a gather, all we have to do logically is to get data from the neighboring vertices. But remember that physically, our data is represented in the form of triplets. So what we do is we just apply a group by on our triplets and we group them by the vertex for which we want data. So here we would apply a group by on A, and this would automatically give us the values from B and C. The apply function is actually the easiest to run. What we simply do is we run a map function where the key can be A and the values are the values that we would receive from B and C. The scatter, however, is slightly complicated. Logically, all you have to do is send data from A to its neighboring vertices. But remember that our data is actually in the form of triplets, and the neighboring vertices can be in different triplets. For example, here, C is a neighbor of A that is in this triplet. So in order to make sure that all of the information is disseminated to all of the triplets, we have to perform a join based on the neighboring vertices. Thus, we make sure that all of the triplets are correctly updated. So in summary, RDDs provide a very simple and efficient programming model that can be generalized to a broad set of applications. Spark also uses the lineage of coarse-grained operations to recover from failures. If you'd like to know more about Spark, please be sure to look up their publications. And if you want to stay up to date with the system, be sure to check out their official website.
This week we're going to study two important classical topics. Distributed file systems. We'll specifically see the design of NFS as well as AFS. This is a very classical topic. Distributed file systems have been around for a long time. Today's generations of file systems such as HDFS are not the first distributed file systems. So there are many important concepts that we can learn by looking at these old classical distributed systems, many of which continue to be used today. NFS and AFS are still used today. We also study distributed shared memory, which may be coming back into prevalence with some of the trends in today's market. And orthogonal topics, we'll see sensor networks. Once again, this is a topic that's not necessarily related to cloud computing, but is on the periphery. And so here we'll give you a teaser so that you can go and look up the topic more by yourself. In this next series of lectures, we'll be seeing what distributed file systems look like. In today's lecture, we're going to look at what the file system abstraction is, and we'll look at a design for a vanilla distributed file system. In the next lecture, we'll look at a couple of real distributed file systems. So what is a file system? A file system, as many of you know and have used in your real life, contains files and it contains directories. Sometimes the directories are known as folders. Essentially, files contain data. They might be your programs, they might be text, they might be executable files, and there might be a variety of other kinds of files. And the directories, of course, contain many files inside of them. Files and directories which are provided by the file system give a higher level of abstraction, and this enables users and processes to think about data stored in files and directories rather than forcing users and processes to think about the disk blocks where the files and directories are stored. That would be very uncomfortable, right? I mean, if you were thinking of what are the disk blocks on which my particular programming assignment or my particular videos are stored, that would be kind of an uncomfortable lower level of abstraction. Here, the file system provides you a higher level of abstraction so that you're able to think about user-centric aspects, and processes are also able to think about files rather than dealing with low-level details. So a typical file may consist of the following components. It consists of a header, and then it consists of the blocks. Typically, the blocks are of the same size because the file system imposes a maximum size on the block. The block size might be a few megabytes. That's typical, but of course it varies from file system to another. Those blocks, block 0 through block n minus 1 shown over here, contain the actual data for the file itself. So if you have a text file, then your actual text will be contained in these blocks. The header in turn contains a lot of meta information about the file. For instance, it may contain timestamps. When was the time when this file was created? That's a creation timestamp. That would include the date and the time at which the file was created. When was the file last read? So whenever the file is read by any process, the read timestamp is updated. When was the file last written is maintained in the write timestamp similarly. And finally, when was the header last updated? If the header was last updated at some time, then that time and date is written in the header timestamp. Now, of course, these are only samples. There might be other kinds of timestamps in the actual file systems themselves. Next, the header contains what kind of a file this is. So it may contain information about whether this is a program file like a .c or a .java, or whether it's a text file like a .text or a .doc, or whether it's an executable file like a .exe or even an object file like .o. This is useful for processes that are opening this file to know what kind of a file it is. Next, you have ownership. Who is the actual owner of this file? Which is the user, what is the user ID of the user who actually owns this file right now? The owner may not be the only one who can access this file. There might be other users who are allowed to access the file in different modes. Some users may be allowed to write the file. Other users may be allowed to only read but not write the file. And that is maintained in the access control list. The access control list maintains a list of all the users who are allowed to access this file. And for each user, it maintains information about which modes this user is allowed to access this file in. Is it a read-only mode? Is it a read-write mode? Is it a write-only mode? Or is it an executable mode or something else? Finally, you have the reference count in the header. This is an important integer that is maintained in the header. The reference count refers to how many directories contain this particular file. By default, when you create a file inside a directory, the reference count is set to 1. This means that this file is contained in one directory. However, you could hard link the same file from other directories, and this would increment the reference count. When you delete a file, the reference count goes down by 1. You'll see this when we discuss the API soon. But essentially, when the reference count reaches 0, you can delete the file. Okay? But by default, the reference count is 1, and it's incremented whenever you hard link the file. So what about directories? We have discussed files so far, but directories are just treated like files by the file system. Instead of containing data, however, the directories contain information about the files that are there in the directories. The directories don't actually contain the files themselves that are inside them. Instead, they contain pointers on disk, for instance, to the files, so that when you list the directory, it gives you the names and meta information about the files, but also from the directory itself, you can access those files on disk itself. So for most of our discussion, we'll be focusing only on files because directories are only a special case of files. So let's discuss what happens in the Unix file system, which is one of the more classical file systems, and a lot of today's file systems are based off of the Unix file system. The Unix file system uses a notion of file descriptors. A file descriptor is essentially a handle for a process to access, that is, read or write a file. Each process needs to open the file and obtain a file descriptor before it executes any operations on it. And then after it is done executing the operations, it needs to close the file descriptor. Whenever a file is opened by a process, the operating system creates an internal data structure for that file descriptor. So it creates a new file descriptor, creates an internal data structure, and then returns a handle to the process. Then the handle can be used by the process for subsequent read and write operations. So for instance, in a typical Unix system or Unix-like system, the process might call open to open a given file that already exists in the system with the file name and in a particular mode. The mode might specify that it's a read mode, or it's a write mode, or it's a read-write mode, both are allowed to, or it's an executable mode, or some combination of these three. This call goes to the operating system, which is running the file system, and then the operating system returns a handle, which is a file descriptor. Typically, the file descriptor is just an integer, which when passed to the file system itself, or the operating system, tells it what is the internal data structure to access. If the file doesn't exist in the system, then you can call create on the file itself, and that will again return a file descriptor after creating the file. Then you can do your reads and writes, and finally when you're done, when the process is done with all its operations on the file, it can close the file descriptor. This does not delete the file. This only closes that file descriptor and says to the operating system or to the file system that this particular process is done with its operations on this file for now. So essentially, the open or create opens a session where a process reads a file, and the close closes that session for reading and writing the file. So how do you read and write the file? Well, once you have the file descriptor, after you have called open or create, you can use the file descriptor as an argument in your read call. So a process, once it has opened a file, may call read on that file descriptor with an internal buffer specified and the number of bytes that it wants to read. Well, this call doesn't really specify where in the file you start reading from. Well, that is done by maintaining a read-write pointer as a part of the file descriptor. So the file descriptor, which is maintained internally inside the file system, maintains a read-write pointer, which is pointing to an offset within the file. Typically, the offset, the offset is initially 0 by default, but when you call a read with a num byte set to some value, say 10, right, the read will start reading from the beginning of the file in the beginning, because the read-write pointer points to the beginning of the file. And then returns, it returns the first 10 bytes, because num bytes is 10, into the buffer, the internal buffer of the process. But then after the read is done, the read-write pointer is automatically advanced by num bytes. So the read-write pointer now points to the 11th byte in the file. A subsequent read done to the same file descriptor will start from the 11th byte onwards. Okay, so there is an implicit read-write pointer involved here, so that processes do not need to deal with explicitly saying where in the file they want to read from. The same thing is true for writes as well. When you call write on a file descriptor with a buffer that says what you want to write in the file, and the number of bytes that says how many bytes do you want to write, again the write starts from the read-write pointer that is currently pointing to some offset in the file. After the write is done, the read-write pointer is advanced by num bytes. Now, the read-write pointer is kind of convenient because the processes do not now need to deal with explicitly saying where you are in the file, but sometimes you may need to do so. You may need to actually locate your file descriptor read-write pointer in a file, and that's where lseek comes into play. With lseek, you can take a file descriptor and you can say that you want it to point to a particular offset within a file. Okay, so this resets the read-write pointer to that offset within a file. This offset may be an absolute offset. You may say 10 here and say absolute here for whence, in which case the read-write pointer will point to the 10th byte of the file. Or you may say the offset is 10 and whence is relative, in which case the read-write pointer is advanced by 10 compared to where it is now. So that's a relative advancement, or a relative lseek. A few more operations that are useful. These are control operations: link, unlink, and stat. So remember, I mentioned hard linking in the beginning of this lecture. Well, here is where linking and unlinking can be done. So you can link a file that is at an old link to a new link by specifying these as parameters. This does not remove the file from the old link. Instead, it creates a new link that also points to the file. Okay? So it creates a new link at the second argument, pointing to the file at the first argument. It does not duplicate the file, it just creates a new pointer inside the file system. Now, essentially, you'll have, after this link returns, you're going to have two different directories pointing to the same file that is located on disk. And in this case, these old link and new link are Unix style names, and so the directories actually point to those files. Whenever you call link, this is hard linking here, it increments a reference count to the file because the reference count refers to how many directories contain the file. This is known as hard linking, and there is a different kind of linking known as soft linking or symbolic linking, which does not affect reference counts. When you soft link or symbolic link a file, essentially you're creating a separate file that contains a pointer inside of that file to the file that you're linking to. When you delete the original file, the symbolic file stays on. It may refer to junk on the file system, but it stays on because it does not affect the reference count itself. When you want to unlink a file, remove it from a directory, you call unlink on the link, and this decrements the reference count. So if you link the file originally and its reference count was 2, you can now unlink it from one of the old links, and the reference count will go down to 1. The file will not be deleted. The file will still stay around with a reference count of 1 with the directory, with one of the directories pointing to it. When you unlink the file from the second directory that it was contained in, then the reference count goes down to 0, and now that file can be deleted. Finally, you can use these functions known as stat and fstat on the file name to get information from the header, such as the timestamps and the reference counts, into a buffer in the process itself. Now, these API functions that I've discussed are only the tip of the iceberg. Unix supports a variety of other APIs and API functions, and if you're interested in them, you should look them up. So what about distributed file systems? So far, we have discussed a case where the client process that is accessing the file system is using the same operating system as the file system itself, and the file system was running inside the OS. What happens when you have clients running on different machines and on different OSs than the server, which is running on a different OS? Well, the files are stored on a server machine in these cases. The client machine, or the client process rather, does RPCs, or remote procedure calls, to the server machine or the server process in order to perform operations on the file. We'll see this played out in more detail over the next few slides, but what do we desire from a distributed file system? Well, we desire a few properties. First, we desire transparency. Transparency essentially says that a client process should be able to access DFS files, distributed system files, as if they were indistinguishable from local, say, Unix files. Okay? So accessing a distributed file located in a DFS should be no different from accessing a local file. In other words, the API should be the same. In other words, the code that the client uses to access a local file should be the same as the code that the client uses to access the remote file. Also, the distributed file system may be changing the location of the file. For instance, if the server is changed, it may be replicating the file for fault tolerance. It may be storing multiple copies of the file on different servers, and all of this should be invisible to the client. The client processes should not need to be able to know about where the file is located, whether or not the file is replicated, in order to access the file and do reads and writes on it. Next, you want to support concurrent clients. So the whole one of the bigger reasons to have a distributed file system is to allow multiple clients to concurrently or simultaneously read and write a file. Okay? And so you want a DFS to support concurrent clients. And finally, you want to have replication for fault tolerance. You may want to replicate the file or certain blocks of the file across different servers, so that if some servers fail, you don't lose the file. You still have at least one copy of the file around. So when you have replication or concurrent accesses, once again, there's a couple of semantics that you need to worry about. The first is one copy update semantics. This essentially says that when a file is replicated, its contents as visible to clients are no different from when the file has exactly one replica. Okay, so essentially this is saying that even though the file is replicated, as far as the client operations are concerned, the end result is the same as if the file had exactly one copy and was not replicated at all. Since you have RPCs going on in between the client, each of the clients and the server, you need to choose the semantics of your RPCs. You might remember from our discussion of RPCs earlier in the course that RPCs may have semantics. At least once operation semantics were the two common cases that we discussed. You need to choose which of these you use for your file system very carefully. If you choose at most once for a particular operation, you need to make sure that those operations are not repeated. For instance, append operations are okay with at most once because then those are not repeated, right? You don't want to repeat appending the same piece of information to a file multiple times. However, some operations can be repeated multiple times without any side effects, even though they are repeated multiple times. These are known as idempotent operations. For instance, reading a file at an absolute position or an absolute offset within the file is an idempotent operation, and no matter whether you do it one time or a million times, you're going to return the same result as long as the file doesn't change. So operations that are idempotent can be used with at least once semantics. Next, you need to worry about security. When you have a distributed file system, your messages are going to cross over the network, and this means that attackers might be able to intercept and modify your messages. And so you need to make sure that two properties are satisfied. They are authentication and authorization. Authentication essentially says that the server is convinced that the client process is acting on behalf of the user that in fact it is claiming to act on behalf of. Okay, so this essentially authenticates the client process. After a user is authenticated, or after a client process is authenticated, you need to verify that that user or that client process is actually allowed to access the file and perform operations in a legal manner. Okay, if the process is trying to read the file, then the process should actually be authorized to read that file. In fact, it should be present in the access control lists of that file. If it's trying to write the file, then it should actually have permission to write that file. So how do you maintain these permissions? Well, there's two popular flavors for maintaining these permissions. They are ACLs, or access control lists, and capability lists. One is the inverse of the other. The access control lists maintain on a per file basis the list of allowed users who are allowed to access that file, and for each user what mode it is allowed to access that file in. For Unix like DFS's distributed file systems, typically the mode is read, write, execute, or some combination thereof. But for other distributed file systems, you could have other access modes allowed as well. But essentially, access control lists are per file lists of users and their allowed access modes. Capability list is the inverse, which is a per user list, and on a per user basis, it specifies the list of files and directories, if necessary, that that particular user is allowed to access, and for each of those files, what mode or what modes that user is allowed to access those files in. Now, capability lists are often split up into capabilities. Each capability would specify, for instance, for a pair of user comma file, whether that user is allowed to access that file and what mode it is allowed to access it in. If there is not a capability for a particular user file pair, then essentially that user is not allowed any access to that file. Okay, so now you know what access control lists mean, or what ACLs mean, and what capabilities mean. These are fairly commonly used terms in distributed file systems, and in general whenever security is being talked of in distributed systems. Next, let's build a distributed file system. We'll call it our vanilla distributed file system, or a vanilla DFS. The vanilla DFS runs on a server, and it also runs at multiple clients. It consists of three types of processes, two of them running at the server, one running at the client. At the server, you run the flat file service and the directory service. The directory service uses the flat file service. In other words, it's a client of the flat file service, even though it's running on the server machine. And the client service runs at each of the clients, and it talks to the directory service and the flat file service. Essentially, the flat file service stores files without worrying about their hierarchical structure. The Unix files and also Windows files, Mac files, all these file systems have a hierarchical structure for their files. The flat file service does not worry about the hierarchical structure. It simply takes the file IDs into account. The hierarchical structure is put into the directory service itself. So let's look at what the flat file services API looks like. So you can read a file by providing it the file ID. This is a unique ID of the file. Specify a buffer into which you want to read. You can specify the position in the file from which you want to read. This is the actual absolute position in the file. And you want to specify the number of bytes that you want to read. So this reads num bytes from the absolute position in the file, which has the file ID, into the buffer in the process's address space. Now, a few things to note here. File ID is not a file descriptor. There is no notion of file descriptors in our vanilla DFS. Okay? The file ID is a unique ID of that file. It's not a file name, it's a unique ID, and you obtain that ID by using the file name from the directory service, as you'll see soon. The other thing to notice is that we are using an absolute position in the file. We are not using an automatic read-write pointer. Why not? Well, because you're using RPCs here, you want to support at least once semantics, and you want this operation to be idempotent. You don't want this operation to be repeated multiple times and cause side effects. If you were using an automatic read-write pointer, then at least one semantics would just not sit well with this particular with the distributed file system, and so you don't want to use automatic read-write pointers. You want the operation to be repeatable without any side effects, and that's why you want to do a read at an absolute position. So this operation, the read operation that I've specified here at the top of the slide, can be repeated multiple times, and it will result in the same end effects without causing any extra side effects. Second, we don't use file descriptors. Why not? Well, essentially we want the servers to be stateless. We don't want to maintain any information on the server side, including any data structures like file descriptors, because the server might crash. If the server crashes, we don't want to lose any data and leave the server in an inconsistent state. We want the server to be able to recover from where it left off without using any state from the previous incarnation. Okay, so keeping the server stateless makes it easier to recover the server after failures because there is no state to restore. So in contrast, as we have discussed, the Unix single machine operating system file system is neither idempotent nor is it stateless. Writes are done similarly from an absolute position to an absolute position in a file. They have the same semantics as a read. You can also create or delete a file with a given file ID, and you can get or set the attributes of that file ID using a buffer. What about a directory service? A directory service allows you to obtain a file ID for a given file in a given directory using the file name. This directory would be the /delimited hierarchical name of that directory within which that file is located. Then after you locate this file ID, you can then use this file ID in the flat file service that we already discussed to then execute operations on the file. You can also add a name to a particular directory with a given file name, and this increments the reference count. You can also unname a particular file name in a given directory. This decrements the reference count. If it reaches 0, then the server can then delete that file. For a given directory, you can also get the list of all files that match a given pattern. This is kind of like ls-al or dir in Windows, followed by a grep in Unix or a find in Windows. Okay, so that's our vanilla distributed file system. In the next lecture, we're going to see the design of two very popular distributed file systems that continue to be used today. They are NFS and AFS. So after having seen what a vanilla distributed file system looks like, we're going to see a couple of real file systems, the NFS file system and the AFS file system. These are very popular and continue to be used even today. First, the NFS file system. It's the network file system. It was developed by Sun Microsystem in the 1980s, and it continues to be used widely even today, both in clusters, data centers, as well as in smaller scale clusters. So here is what the NFS architecture looks like, and then I'll play it out in more detail over the next few slides. So you have the server machine, of course, and then you have multiple client machines. On the client machines, there might be multiple processes that are trying to access files. The processes execute operations with what is known as a virtual file system module. You'll notice that there is a virtual file system module also on the server side over here on the right. When a process makes a call to the virtual file system module, it then decides, depending on whether the file is local or remote, whether to relay the call to the local Unix file system or to the NFS client system. If the file is local, then the Unix file system is accessed, and that in turn accesses the local disk and then returns the information directly to the process. However, if the file is remote, if it is located on the server, then the NFS client system forwards a request to the NFS server system. This is done via typically an RPC. And then the NFS server system forwards a request to the virtual file system on the server side, which then forwards it to the Unix file system on the server side, because after all, on the server, the file is stored on local disk, and the file is then accessed from the local disk. then the information about the file, such as a block being read, is returned on the reverse path shown by these arrows. So you'll notice a few components here: the NFS client system, the NFS server system, and the virtual file system. Let's discuss those in a little bit more detail. The NFS client system is similar to our client service that we discussed in the vanilla distributed file system. Here it is integrated with the kernel, that is with the OS, so it executes in the with kernel level privileges. Okay. It performs RPCs to the NFS server system whenever distributed file system operations are involved. The NFS server system plays the role of both the flat file service and the directory service from our vanilla distributed file system, which we discussed in the previous lecture. NFS allows mounting of files and directories. This means that clients can mount remote directories to a local directory name. So for instance, if we mount /user /edison /inventions into a local directory /user /tesla /my competitors, now user /tesla /my competitors /foo actually refers to a file user /edison /inventions /foo. Okay, so mounting doesn't copy files over, instead it just creates a pointer to a remote directory so that now you can use a pseudonym, a clone name to refer to those files. It makes it convenient for users as well as processes to refer name files, name directories, and access files and directories. What about the virtual file system module, which is present on both the client side and the server side? That's the third module we saw on that figure. The virtual file system module allows processes to access files via file descriptors. Well, this should kind of surprise you at the beginning, because we discussed in the vanilla distributed file system that the vanilla distributed file system does not use file descriptors, primarily because of idempotency requirements. However, you want to use file descriptors because you want to have transparency. You want processes to be able to access local and remote files via the same API. And since local files are accessed using file descriptors, you want to support the same for remote files as well. That's what is supported by the virtual file system modules. Okay, so as far as client processes are concerned, they access local and remote files via the same API using file descriptors. But when an access is received by the virtual file system module, or the VFS module, it decides whether to route it to the local file system or to the NFS client system. And here's where the translation from file descriptors to the idempotent operations happens. Okay? So all the files, local or remote, are named uniquely using NFS file handles by the virtual file system module. The virtual file system keeps a data structure for each mounted file system. It also keeps a data structure for each file that is open. This is called a vnode data structure. Okay, here's where the translation happens. If the file is local, that is stored locally on the client machine, then the vnode points to the local disk address called the inode block. However, if the file is remote, then the vnode contains the address of the remote NFS server, so that RPCs can now be sent to that NFS server to obtain blocks of that file. Okay, so here is where this data structure, the vnode data structure maintained by the virtual file system module, is the one that does the translation between the stateful, non-idempotent file descriptors and the stateless behavior, the idempotent operations that we really desire from the distributed file system. Now, NFS uses several optimizations, and these are the main reasons why NFS is a fast system. Server caching is one of those optimizations. It's useful for doing reads. Essentially, on the server side, you store in memory, in RAM, some of the recently accessed blocks of files and directories. Okay? Now, these might be blocks accessed by different client processes at different machines. But why does this work? Well, this works because most programs written by humans tend to have what is known as locality of access. Locality of access essentially says that if a program or a process has accessed a block in the recent past, it's likely going to be accessed in the near future again. This means that if you store that block in memory, you can then access those near future accesses to that block can be done very, very quickly. Instead of going to disk, you simply access the block from memory itself. Then when you do a write at the server, when a write is received at the server, there are two flavors in which this can be done. The first is known as a delayed write. The second is a write through. In a delayed write flavor, you do that write only in memory. You don't write it to disk immediately. Instead, periodically, say every 30 seconds, you flush it to disk. Okay, this is done, for instance, via the Unix sync operation. This is fast because the write can be now done in memory fairly quickly. but it may not be consistent. Why is it not consistent? Well, if the server crashes before it does the next sync, then any of the writes that were in memory but not yet flushed to disk might in fact be lost. If you want to be really consistent, you should use write through. Write through whenever a client write is received at the server, essentially the write is done immediately to disk before an ACK is sent to the client. This ensures the best consistency, that all the writes are in fact done durably on the server side, but it may be slow because it involves a disk seek and a disk write. What about on the client side? Well, on the client side too, you can do caching. So you don't need to cache blocks only on the server side. Clients can also cache, because locality of access is also true for each process. So a client caches recently accessed blocks. Each block that is present in the cache on the client side is tagged with the time at which the cache entry was last validated, known as TC, and also TM, the time at which the block was last modified at the server. A cache entry at a given time t is said to be valid if the difference between t and tc is less than a small value of small t, or if the time at which the block was last modified at the server is the same as the timestamp that is maintained at the client. Okay, so if the second condition is true, essentially you're saying that the copy of the file or the block at the client is the same as the copy of the block at the server. But doing this second operation requires you to do an RPC to the server, which may be expensive and it may involve some amount of latency. To avoid that RPC, you give some amount of laxity to the block that you're storing and say that, hey, if the block is less than small t old, I'm going to still consider that block as being fresh. Okay, so t is known as the freshness interval. This is a compromise between consistency and efficiency. If the value of t is very, very small, essentially, say t is 0, for instance, then essentially it means that you'll never do this check. You'll always go and query the server for its timestamp. Okay, so that's the most consistent system, but it may be fairly slow. If the value of t, small t, is large, it means that you're willing to tolerate some amount of staleness for fast accesses. Typically, this value of t is set to be set adaptively by a system like Sun Solaris, sets t adaptively between 3 to 30 seconds for files and between 30 to 60 seconds for directories. When on the client side, when a block is written by the process, you do a delayed write to the server, because after all, if you have a non-zero value for small t, you're going to have stale blocks anyway, so you might as well do a delayed write, which is a more efficient form of doing a write. So that was NFS. Now let's quickly discuss AFS. We won't discuss all the design details of AFS. We'll discuss a few design details that are kind of interesting. So the name Andrew in the Andrew file system name comes from the Andrew in Andrew Carnegie and Andrew Mellon, who are the co-founders of the Carnegie Mellon University, and shouldn't be a surprise to you that AFS was in fact designed at CMU, which is how its name came about to be. It's used in many clusters today, especially in university labs. So AFS involves two very interesting design decisions, whole file serving and whole file caching. So earlier when we discussed NFS, we were talking about blocks being cached on the server side and on the client side. AFS does not deal with blocks of the file. Instead, it deals with the entire file. When a client accesses or opens a file, it is given the entire file, not just the opening block of the file. Also, when a client caches a file, it caches the entire file. It doesn't cache just a few blocks of the file. Okay, so everything is done on the file level basis rather than on a block level basis. Also on the client side, the cache is permanent, meaning that it is stored on disk. And so even if the client crashes, it can then recover and then access its cache. Why is whole file serving a good alternative? Well, you might think that the files that are very large, like gigabytes or terabytes large, would involve a lot of overhead. But in fact, these design decisions are based on measurements which showed on real file systems that showed that most file accesses are by a single user, and most files tend to be small. Okay, so this is the common case for most file accesses, and so AFS is catering to this common case over here. It's making these common cases really fast. So yes, files that are gigabytes or terabytes in size may become very slow, but those are not the common files anyway. The most common files are small and accessed by a single user, and those are made really fast by dealing with entire files rather than blocks. Also, even a client cache as large as a few hundreds of megabytes can be stored in RAM, and nowadays you can store caches that are even a few gigabytes in RAM. Also, finally, file reads are much more frequent than file writes, and so if you serve out entire files, then the reads can be served locally at the client itself rather than going to the server for blocks. Okay? And typically these reads are also sequential, so storing these files on disk is fairly efficient because now you access consecutive blocks on disk at the client side. A few more details about AFS. The client system is known as a Venus service, so every client is running a Venus daemon, and on the server side it's known as a Vice service or the Vice daemon. Reads and writes are optimistic because whenever a file is opened, the entire file is sent over to the client side. The read and write can be done on the local copy of the file at the client machine at Venus. When a file is closed, if any writes were done to that file, then those writes are propagated to the Vice, which then updates its copy of the file. When a client opens a file, the Vice of course sends it the entire file as we've discussed, but it also gives it a callback promise. The callback promise essentially is a promise that says that if another client modifies this file and then closes it, then a callback will be sent from Vice to this Venus. Okay, so essentially if a particular client Venus has opened a file, it's given a callback promise that says that if another client opens, modifies, and then closes the file, then this client will be informed about that modification. Typically, the callback state that is maintained at Venus is only binary. It says that the state is either valid, or if the callback is actually done as a result of another client's updates, then that state is set to be cancelled, which means that essentially this Venus will then need to go and fetch the file again from the Vice daemon. Okay, so that wraps up our discussion of distributed file systems, which are very widely used today both in data centers and in smaller scale clusters. We've discussed the design of a vanilla distributed file system as well as two very popular file systems, NFS and AFS. Now, this is only the tip of the iceberg, and there are many other file systems out there today, both cutting edge research file systems as well as file systems that are in use today very widely in clusters and in data centers. Hi there. In this lecture, we're going to discuss this concept known as distributed shared memory. So far in the course, whenever we've assumed that processes communicate with each other over a distributed system, we've assumed that they use a network. This is a message passing network where a process sends a message and another process receives a message. But what if we allowed processes instead to share memory pages with each other, where processes might be able to write and read pages? So if a process wrote to a page number 5 and another process read from a page number 5, this would make it much more easier to write programs. We could then take programs that were written for regular multiprocessor operating systems and then just run them over a distributed system where you have a network underneath. So you might be able to reuse programs as well. So this is the concept that is known as distributed shared memory, where you have processes sharing pages with each other, but in fact they're doing this over a message passing network that is underneath. So processes virtually share pages with each other, but underneath the underlying distributed shared memory system is implementing this by using message passing. Okay, so that's the main challenge over here. So distributed shared memory in fact is trying to achieve in software what has already been achieved in hardware in multiprocessor operating systems. So in multiprocessor operating systems, you have multiple processors sharing a common bus, sharing a common memory, and they already communicate with each other and they share the memory, right? So they share the pages of the memory. Now you want to implement the same thing in software over a distributed system. So it's the software version of multiprocessor communication, but over the network. Okay, so that's a main challenge over here. In fact, distributed shared memory and message passing are equivalent to each other in the sense that given a distributed shared memory system, you can implement a message passing system. You do this by sharing a common page as a buffer where you read and write messages. Essentially, you use it as a producer-consumer buffer. You can also do the reverse, where you can implement distributed shared memory over a message passing network, and we'll see how to do that in this lecture. So in order to do that, you need to maintain at each process a cache. A cache stores some pages that were recently accessed by that process. When the process wants to read or write a memory address in a page, it first checks if that page is present in the cache. If it is present, then it uses that version of the cache. If it's not, then it may need to fetch that page from somewhere else in the system. So essentially, a cache is a collection of pages that have been recently accessed by the process that owns that particular cache. So you'll notice in this figure that every process has its own local cache. Typically, this cache is of course located on the same machine and on the same memory and on the same operating system as that process itself. Now, pages are typically mapped to the local memory of that process. The cache is mapped to the local memory as well. When a page is present in memory, it is called a page hit. So when the process tries to access a page and it is already present in memory, it's a page hit. However, if the page is not present in memory, it's called a page miss, and this leads to a page fault. Okay, a page fault happens in regular paging systems that are implemented by operating systems as well. And typically in a regular paging system in an operating system, when a page fault occurs, the operating system goes and fetches that particular block from the disk and stores it in main memory. In a distributed shared memory system, however, the page fault handler, the kernel trap handler that is invoked on a page fault, runs the distributed shared memory software, which then might fetch the page from a different process elsewhere on the network. Okay? And typically it does this by using multicast. So we're replacing some portion of the kernel in there with our DSM software. So essentially, distributed shared memory can be implemented in any system that involves paging by replacing the page fault handler and a few other pieces of software in there with appropriate software. So a few terms before we describe several scenarios. The owner is that special process that has the latest version of a particular page. So every page has an owner process at any given point of time. That process owns the latest version of the page. The owner of a page might change from time to time, as you will see as we go along. Second, each page is either in the read state or the write state. We note this as the R state or the W state respectively. When a page is in the R state, the owner has a read copy, but other processes might also have read copies. Okay, so this means that multiple processes are allowed to read a given page simultaneously. However, no write copies exist of that page. When any write copy exists, when a given page is in the W state, only owner has a copy of the page. No other copy of the page exists at any of the other processes in the group. This means that essentially writes are exclusive, but reads can be shared with other processes. Of course, here when I'm saying an owner has a copy, I mean that the owner has a copy of the page in its own cache. When I say a process has a copy, I essentially am meaning that the process has a copy of that page in its own cache. So let's discuss a few scenarios that might occur when a process is trying to do a read. Here, in all of these scenarios, process 1 is attempting a read, and there are 6 scenarios I'm going to discuss here. In this first scenario, the process 1 is the owner of the page and has the page already in the R state. In this case, the read is served directly from the cache of process 1 and no messages need to be sent out over the network. So that's the first scenario. Let's look at the second scenario. In the second scenario, the process 1 is the owner of the page and the page is in the write or W state. Once again, in this case, a read by process 1 can be done directly from the cache and it does not need any messages to be sent over the network. In the third scenario, the process 1 is the owner, has the page in the read state, but there are a bunch of other processes that also have the same page in the read state. In this case, processes 3 and 4 are in the read state for that given page. Once again, process 1, when it reads the page, the read can be served from the cache and no messages need to be sent. The fourth scenario is where, similar to the third scenario, except that someone else is the owner, and once again here, the read can be served from the cache at process 1 and no messages need to be sent. Now let's get to the other scenarios which need something else to happen. So in the fifth scenario here, process 1 does not have the page in its own cache. Other processes have the page in the R state. So in this case, processes 3 and 4 have the page in the R state. In this case, process 1 asks for a copy of the page. For this, it uses multicast inside the group of DSM processes here. When it sends out a multicast message asking for this particular page, say page number 5, then the owner responds back with the latest version of the page, and then process 1 marks the page as R, as in read state, and then it can do the read directly from the cache itself. So the end state in this particular case would look like this, where process 1 would fetch the page and then mark it as R and then do the read from itself. Let's get to the sixth and the final scenario. where process 1 is trying to read the page and there is a write copy of the page located elsewhere, in this case process 4, which is also of course the owner of that page. In this case, process 1 needs to ask the other process to degrade its copy to the read mode. It locates this process via multicast, so essentially it sends out a multicast to the group, and the other process, that is the owner, responds back to the multicast saying, hey, I am the owner. So process 1 fetches the page, marks it as R, and it does a read. And in the meantime, process 4 also degrades its copy from a W to an R. So the end state in this case looks like this, where process 4 has changed its copy from W to an R. It still retains a copy of the page so that it can continue to read it. And process 1 also has a read copy of the page so it can continue to read it. Process 4, if it wanted to write the page again, it would then need to do something else. It cannot write this page as is in this particular state. So let's discuss what happens with writes. So here is one scenario for a write. Process 1 is trying to write a given page, and it is the owner of the page, and it has a write copy of the page. In this case, the write can be done directly to the cache and no messages need to be sent out over the network. Second scenario, process 1 is the owner of the page. It has the page in the read state, and other processes have the page in the read state. In this case, process 1 needs to ask the other processes to invalidate their copies of the page. Okay, so it does this by using multicast. It sends out a multicast message saying, hey, please invalidate all your copies of the page. I want to do a write. Once this is done, it marks its own copy as W, meaning it can be now written, and then it does a write in this particular state. So in this case, you'll notice that processes 3 and 4 have invalidated their copies of the page, so they can no longer use that copy of the page. If they want to do any operations on that particular page, they'll need to fetch a new copy from the new owner. In the meantime, process 1 now has a write copy of the page, and it can go ahead and do both reads as well as writes on this copy. So that's the second scenario for the write. Let's discuss the third scenario. In this case, someone else is the owner, and process 1 has the page in the read state. Once again, this is similar to the previous case, except that the process 1 now additionally needs to become the owner. So the other processes are asked to invalidate their copies of the page. They do so. Processes 3 and 4 do so here in this particular figure. And process 1 gets the ownership of the page as well as marks the page as W, and then does a write on that page. And here's the fourth scenario. Process 1 does not have the page at all. Other processes have the page in either the read state or the R state or the W state. In this case, I've just shown the R state, but it doesn't really matter. The operations are similar if other processes have it in the write state as well. Essentially, process 1 asks other processes to invalidate their copies of the page. Again, it uses multicast for this. It fetches all copies, it uses the latest copy, or it can just fetch the copy directly from the owner. It marks its copy as W, and it becomes the owner. Other processes 3 and 4 in this case invalidate their copies of the page, so they can't use that copy anymore. They need to fetch a copy from the latest owner. So even though the slide here says fetch all copies, you really don't need to fetch all copies. You just need to send out a multicast and have only the owner respond back to you with the latest version of the page. So that is known as the invalidate approach, where when you do a write and other processes have a copy of the page, you ask them to invalidate their copies of the page. The invalidate approach works well in many of the cases. However, there are some cases where you might have bad behavior in the invalidate approach. If two processes write the same page concurrently, for instance, if they're writing different variables that happen to reside on the same page, then this may result in flip-flopping behavior where one process invalidates the other, and then soon after the second process invalidates the first one. And this involves lots of network transfer, because essentially on every invalidate you fetch the new copy of the page over to another process. Okay, so this is what is known as false sharing, when unrelated variables fall on the same page, and this results in flip-flopping behavior in the invalidate approach to distributed shared memory. Essentially what's happening here is that false sharing happens when the page size is so large that it captures more than the locality of interest. So every process has a locality of interest, which is typically the window within which it is accessing variables and changing variables. The page size needs to be just about the locality of interest. But this is of course hard to know, because the locality of interest depends on the application, it depends on the processes themselves, and of course it can vary over time. In general, you want your page size to capture the locality of interest. If the page size is much larger, you can have false sharing, where different processes have variables on the same page and results in this flip-flopping behavior that we just discussed. If the page size is too small, then you're capturing only a small portion of the locality of interest, and you end up incurring too many page transfers. There are way too many pages in the system, and so you incur a very high overhead in transferring these pages, and this also is very inefficient. So setting the page size is an important concern in disparate shared memory systems. You want it set not too high, but not too low either. An alternative approach to the invalidate approach is what is known as the update approach. In this approach, multiple processes are allowed to have the page in the right state. So unlike in the invalidate approach, where at most one process could have a given page in the right state, here multiple processes are allowed to have a given page in the right state. When a process writes to a page, it does not invalidate the other processes. Instead, it sends them multicast saying, hey, I have written the bytes at address so and so with these new values. Please update your copies of the page. Okay, so that's why this is known as the update approach. On a write, you send update messages to the other processes that are currently holding write copies of this page. So in this way, the other processes can then continue reading and writing this particular page. The update approach here is preferable over invalidate under some situations only, when there is a lot of sharing among processes, when writes happen to very small variables, and when page sizes are very large. But in general, though, the invalidate approach is the more preferable approach because it tends to work well in more of the cases, more of the realistic cases than the update approach. Consistency. Whenever you have multiple processes sharing data, such as pages, consistency comes into the picture. We have discussed consistency before. We have discussed several consistency models when we discussed key value stores and NoSQL storage systems. And those same consistency models apply here as well. Those include linearizability and sequential consistency, very strong models, causal consistency, FIFO consistency, which otherwise is known as pipeline RAM consistency, and also eventual consistency. There are also other models such as release consistency that originated from the distributed shared memory and the multiprocessor architecture areas, and these should be familiar to you from earlier in the course. In fact, all of these terms that you see here originated from the area of hardware architecture and multiprocessor architecture, as well as distributed shared memory, and then later on they were adapted by key value stores and NoSQL storage systems, because after all it's the same concept there where processes share certain memory. So as one goes down the order, as you know, the speed of the system increases, the speed of reads and writes increases, but of course the consistency gets weaker and weaker. So distributed shared memory has been a very popular area for a while. It was popular up until about a decade ago, and then it started falling in popularity. But some have surmised that it may be making a comeback now with faster networks like InfiniBand and other faster networks, as well as with solid-state drives and other newer versions of solid-state drives coming into the picture. Remote direct memory access, also known as RDMA, where one machine or a processor on one machine accesses the RAM of another machine over the network, that is becoming more and more widespread now. It's becoming more realistic now. And only time will tell whether DSM or distributed shared memory will make a comeback and become more widespread in today's machines. As of now, it's not really very widely used today. So we've discussed distributed shared memory where processes share pages instead of sending and receiving messages. This is a useful abstraction to write code where if you've written code for processes that share the same memory over one operating system, now you can simply take the same code and run it over a distributed shared memory system where these processes are instead at different machines communicating over a network. So distributed shared memory essentially provides a virtual abstraction of processes sharing pages, while underneath it is running over a message passing network. So distributed shared memory can be implemented over a message passing interface and also vice versa. So these two forms of communication are in fact equivalent. And we've discussed two different flavors of implementing distributed shared memory. They are known as invalidate, which is a more popular approach, and update, which is a less popular approach, but is an alternative available to you. Hi there. In this lecture, we're going to see a little bit about sensors which have emerged in the last decade or so, and wireless networks that might be joining them. What do I mean by a sensor? This is an example of a sensor I have here, which was originally fabricated by researchers at Berkeley, then later on made by a company called Crossbow, which has later on been acquired by another company, Moog. I'll tell you a little bit more about these kinds of sensors, why they have emerged, and so on and so forth. But let's start at a much more broader or higher level. So everything is getting smaller all around us. In fact, the smallest state-of-the-art transistor that's being made today can be made from a single gold atom. Of course, this is still in research, not yet in industry, but just imagine a world where you could make a transistor of just one gold atom. And let's do some calculations just for fun. Pentium P4, which is a fairly old processor by Intel, contains about 42 million transistors. The atomic weight of gold is about 196 to 200, depending on which isotope you look at. 1 gram of gold contains 3 times 10 to the 21 atoms, which means that if you use all the atoms correctly to make one transistor each, then you can make 7.5 times 10 to the 18 Pentium 4 processors from 1 gram of gold, which means that from 1 gram of gold, you have enough processors, Pentium 4 processors, to give each person in the world a billion Pentium 4 processors. That's with just 1 gram of gold. Okay, so you can imagine that as these, what are known as form factors get smaller and smaller, as the sizes get smaller, you can make many more of these sensor nodes, many more of these processors. In general, the speed up of a CPU is directly proportional to the square root of the transistors that you can put on the die. So we are not talking very far from reality with these ballpark calculations. But of course, we are pretty far from this reality because, after all, you still cannot make in a production a transistor from one gold atom. But essentially, the point I'm trying to make here is that everything is getting smaller, and it's easier and easier to make smaller computers such as this one over here. So sensors have been around for a long time. Coal mines have used, and all kinds of mines have used sensors for carbon monoxide and carbon dioxide. In the old days, when we did not have technology, these sensors used to be birds in cages. This is where canary in a coal mine, the phrase, comes from. Essentially, if the bird died, you knew that something was wrong, that the level of carbon monoxide in the mine might be too high, and it was time for the miners to get out. Today, of course, many mines in the world, not all, but many mines use advanced technological sensors. Industry has used sensors for a long time. For instance, on the assembly line where cars are being manufactured one step at a time, you need to use sensors so that the assembly line is moving all the time. Today, however, we deal with excessive information, and we need to process this information and data and convert it into knowledge. For instance, environmentalists might want to collect data on an island which is uninhabited, where there are no people and where the terrain may be inhospitable. Armies might want to collect data in the battlefield without putting the lives of the soldiers at risk. And in general, humans want to collect data from across a wider geographical area, for instance, around a volcano, where they might want to measure earthquake movement, volcanic movement, and predict the movement of the volcanoes based on the sensors. You really don't want to have people over there mucking around when a volcano might erupt any point of time. And this is where sensor networking technology comes into place, where you might deploy, say, a few hundred of these around the volcano and then detect acoustic movements which might hint at the volcano erupting in the near future. So the growth of any technology, such as sensor networking technology, but in reality any technology requires three components in there. It needs hardware, good hardware. It needs good operating systems and distributed protocols, especially when you have the hundreds of these sensors networked with each other. And of course, you need applications. We won't talk much about the applications. Let me just say that there are both military applications for these sensor networks as well as civilian applications such as the environmental observation as well as the case of monitoring volcanoes. So these sensor networks have been deployed in cases where you want to monitor the movement of whales in the ocean, where each whale has been fitted out with a sensor, where you want to monitor the temperature and humidity in a forest in in an island, and for instance, the Great Duck Island, which is one of the islands that has a very interesting ecosystem, was outfitted with sensors to measure the temperature and humidity inside the forest. And then, of course, the volcanoes in South America have been outfitted with sensor networks to measure their activity. So let's discuss the other two. The sensor nodes themselves have emerged because of several trends. First of all, there is Moore's law, which says that, in general, Moore's law has said that the processing capacity doubles every 18 months. Nowadays, this processing capacity stands more for the number of processors you can put per die and less for the CPU speed. But in general, over the last few decades, Moore's law has made processors faster and faster. Wireless communication is also advanced. And then finally, you have MEMS, which is known as micro electromechanical sensors, where essentially you have sensors that convert some form of energy into an electrical impulse, which can then be sent to a processor so that the processor can then process it. And that's essentially what's going on with these sensor boards over here. So you have this board, which has the processor over here. You can see it's a 900 megahertz processor here. And then it has a little bit of memory on it. I'll say a little bit about how much memory it has in a little bit. But what you do is you attach this sensor board, which has a bunch of sensors on it. So this has an acoustic sensor, a sound box, a thermometer, and a few other sensors. And you attach it on top of this, essentially. Let me make sure I'm getting this the right way here. And voila, you have a working sensor. Sensor board where the sensors on this top board can convert some form of energy. For instance, the microphone on this would be able to convert sound energy into an electrical impulse, which is then sent over to the processor, which is also on the board over here, which can then process it according to the application that you've written. Second, it needs a microprocessor, as you've seen here. Third, it needs a communication link, and in this case, you have this wireless antenna. So this is the wireless communication link, so that this sensor mode can then talk with other sensor modes out there, and they can network together in a wireless network. And finally, you need a power source, because these are likely to be deployed in terrains where it may not be possible for humans to go out there and recharge them, and of course, it may not be possible to power them using just regular AC electricity off the wall. You need batteries, and this particular model has 2 AA batteries running on it. So the sizes of these modes are very small. This mode that I've shown you is called a Mika mode or a Maeka mode. And then there are smaller models. A Mika dot mode, which is also manufactured by the same company, is smaller. It's also running the same CPU, 900 megahertz, and it has, as you can notice, a wireless antenna. Intel modes were manufactured by Intel subsequently. Here's an example of an Intel mode for you. And the Intel mode, of course, typically has an ARM processor. Here I have the Intel mode has two pieces. The sensor board is on top. This is the sensor board over here. And then the other board is on the bottom. And you can see it says Intel Research over here. And of course, it has batteries. In this case, they are lithium batteries running over here. Okay, and there is an on button here. You switch it on, and after a while, well, you can see that it starts blinking over here, which means that, well, now it's active. It went from white to blue, and it means that it's now active. Let me switch this off. And then there are other sensor modes like this, which have been created that are even smaller. For instance, Golem Dust, which is one of the sensor modes that was created by Crossbow, had a volume of only a few cubic millimeter, which is really, really small. It's much smaller than a typical penny coin that you might find. In any case, in all of these sensors, everything is on one chip. So you notice that when you have this processing board and this sensor board, everything is on just one chip. There is no other peripherals you can attach to this. There is no disk over here. There is no monitor over here. There is no mouse. There is no keyboard to this. Everything is on one chip. So this consists of the processor, the transceiver, which is a fancy word to say transmitter plus receiver. Essentially, this is the wireless antenna, the battery, the sensors. And it also contains a little bit of memory and, of course, buses to connect the memory with the processors. These are very wimpy machines. The Mika mode, for instance, has a 4 megahertz processor. It's got a wireless bandwidth of about 40 kilobits per second. it's got only 4 kilobits of RAM. So that's the amount of RAM you have, not 4 megabytes, not 4 gigabytes, which you might find on your workstations today, but just 4 kilobytes. This is really, really puny. This is very tiny. It has 512 kilobytes of serial flash, but essentially you need to fit almost everything in the program on 4 kilobytes of RAM. If you let it run for on full blast on the batteries, then it lasts for only 7 days, which means that it's very important for programs that you write to conserve the energy, to conserve the battery. You don't want to be running at full blast all the time. You want to potentially go to sleep at some point of time so that the sensor node can then save its energy for later on. So there are many different kinds of sensors that are available. You could have acceleration sensors, vibration sensors, which might be useful on the battlefield to detect tanks, sound sensors, gyroscope sensors, tilt, magnetic, motion, pressure, temperature, of course, light, moisture, humidity, barometric. A variety of sensors can be outfitted, and in fact these sensor boards can be daisy chained on top of each other. So you can take one more sensor board and put it on top of this, and then you can stack them on as you desire. Other deployments, for instance, in some of the metros in some of the larger cities in the world have used chemical sensors such as carbon monoxide, carbon dioxide, and radon sensors, as well as biological sensors which detect pathogens. In some cases, actuators are used too. These involve mirrors, motors, smart surfaces, and micro robots. So when you have sensors on the same board as a processor, how do you connect them? Well, typically on these boards such as the Maekawa moat, the bus has to be a low power and fast bus, and the bus used on these is called the I2C bus, or the inter-IC connect bus. This was developed by Philips. This connects the sensors to the microprocessors. It's very simple. It has only 2 wires. Both the wires are bidirectional. One of them is for data. It's called the serial data bus. The other one is for the clock, which is called the serial clock bus. The serial clock bus is typically used to make sure that the sensors and the processors are talking at the same speed so that they can send data to each other over the serial data bus. Even though this has only 2 wires, it has a fairly high bandwidth, 3.4 megabits per second, which is high enough for a computer as puny as this. What about the transmission medium? Well, in all of these cases, whether it's a Maekawa moat, whether it's the Maekawa dot moat, or whether it's the Intel moat, the communication medium is radio frequency, which is the typical communication medium that, for instance, your cell phone or your laptop uses when it talks to a base station. Essentially, you're sending RF waves out over the wireless medium. This is a broadcast medium, which means that when one sensor is talking to another, the second sensor needs to receive the packet from the first sensor, store it, process it, and then forward it to the next sensor. Links are typically bidirectional, which means that when sensor A can hear sensor B, it's also true that sensor B can hear sensor A. What do I mean by broadcast? This means that when a sensor transmits, any sensor within hearing range, no matter which direction it is in, can receive its transmission. When you go smaller, when you're talking about smart dust, which is a really small, smaller than a penny sensor node, RF is not necessarily attractive because it has high frequency and it consumes a lot of power. And at those small form factors, you really don't have enough energy saved up in your battery to support RF communication. Instead, you want to support optical transmission. Some of these smaller models support optical transmission. This involves simpler hardware and it consumes lower power. However, it comes with a few challenges. Here, optical transmission essentially means that you have a laser, right? You have one sensor sending its packets via a laser to another sensor, and this means that you don't have a broadcast medium anymore. You have a directional antenna, and you need to make sure that the laser is pointed at the receiving sensor. Broadcast is very expensive. You can't necessarily send out a packet to all of the sensors in your hearing range. You need to direct it to every sensor that you want to send a packet to. Line of sight is required. Laser cannot go through walls, so you need to make sure that the receiving sensor is within viewing distance of the sending sensor. In some cases, you may need to move antennas around because if you want to direct the laser accurately at the receiving sensor, this involves mechanical antenna movements that might use up a bit of energy. So switching links might be costly. However, one of the advantages is that you can use mirrors to go around walls. So you can use an intermediate sensor which simply reflects your beam. This is known as wormhole routing, where the intermediate sensor is not storing and forwarding packets, unlike RF communication, but instead is simply routing your packet as is via a mirror. So this is fairly fast. Finally, links are unidirectional. So sensor A being able to send to sensor B doesn't mean that sensor B's laser beam, optical transmission beam, is directed at sensor A. It may be directed somewhere else. So to summarize the sensor node discussion, the size of these sensor nodes is very small. It's a few millimeters to a few inches. They have limited processing and communication. They are very puny, just a few megahertz of clock, just a few megabytes of flash, just a few kilobytes of RAM, and a few tens of kilobits per second of wireless, in some cases a few hundreds of kilobits per second. They have limited power. They're typically running on batteries, and you cannot recharge those batteries in inhospitable terrains, so you need to be sure that you conserve energy when you write code for these sensor nodes. They're also failure prone, and both these nodes are failure prone, as well as the links are failure prone. So if you deploy this in the battlefield, a tank might run over it and destroy it. If you deploy it in the forest, an animal might come and destroy it or just eat it. Also, the links are failure prone, so if you send out a packet over the wireless medium, it might get dropped because there is noise in the wireless medium. But of course, they are easy to manufacture and deploy in large numbers, and so you need to offset this with protocols, distributed protocols, and operating system design that are scalable, that scale to very large numbers of these sensor nodes talking with each other, and also that are fault tolerant, that work where the protocols work in spite of the fact that some of these sensor nodes might fail. So what about the operating system? What operating system do sensor nodes like this run? Well, there's a few considerations here when you want to build an operating system. First, you want your operating system to be small because you only have a few kilobytes of RAM, 4 kilobytes of RAM on the Maekawa mode. You need your operating system to be compact and fit in memory very compactly. Embedded operating systems which run on intelligent washing machines and intelligent microwaves, for instance, are not applicable because they use several hundreds of kilobytes of read-only memory or hundreds of kilobytes of memory, and they won't fit on the sensor mode. You need to worry about what your workload characteristics are. For these sensor modes, typically the workload characteristics are bursty. Typically the sensor modes are not doing anything until something interesting happens in the neighborhood. For instance, there is a tank movement or there is some rumbling on the surface of the volcano. You want to reuse these same sensor nodes. You don't want to build a sensor mode that is specifically built for the volcano. You want to reuse the same board for the enemy battle tank deployment as well. And finally, you need to worry about scheduling and real-time characteristics where you want to process things very quickly. Of course, you want to make sure that your sensors don't consume much power and that the communication is also optimized. So all of these requirements were summarized by researchers at Berkeley who built the operating system known as the TinyOS operating system for these small devices. So the Maekawa mode over here is running TinyOS operating system. The Maekawa dot is running a TinyOS operating system too, and many versions of the Intel mode are also running a variant of the TinyOS operating system. So the fact that you need bursty data flow driven computations, the fact that you want to support multiple data streams, the fact that you want real-time computations and power conservation, as we have discussed on the last slide, all of these led to TinyOS being an event-driven execution, a reactive mode. So unlike your workstation and laptop, which are always running some process all the time, these modes might actually go to sleep when there's nothing interesting going on in the neighborhood. When something interesting happens, these modes then react and then might undertake some computation in order to react to that stimulus. Also, you want your OS to be small, operating system to be small, and you want to accommodate a diverse set of applications. And these led the researchers to build a modular operating system with modular structure and components with clean interfaces between these components. So in order to program these TinyOS modes, yes, you can program these. You use a language called NestC, which stands for Nested C. It's a variant of C. So if you're familiar with C or C++, NestC should be fairly easy. NestC defines components, and a component can be either a module or a configuration. A module specifies a set of methods and some internal storage. This is sort of like a Java class. Essentially, it is a Java class with its own internal storage, a few fields and a few methods to access those fields, but it's a static Java class. And why do you want a static Java class? Because you have limited memory. You don't really want dynamic memory allocation on these small devices. You could write a module that corresponds to a hardware element. This would be sort of like the device driver for that element, for instance, for the clock or for the LED, or to a user-defined software module, for instance, for the routing protocol among the sensors that are connected in the network. Modules implement and use interfaces. This is just like your regular Java classes, so that other modules can then call the methods in this module. So now you can wire these modules together by having one module call the methods in another module, and this together is called a configuration. Okay, so a program that you write where you have multiple modules that are talking with each other by calling each other's methods, that would be called a configuration. A complete NSC application consists of one configuration where you have multiple modules in there talking with each other. So component invocation is event driven, which means that components don't start executing just by themselves. They start executing only when they are invoked by some other event. So for instance, when something interesting happens in the neighborhood, when there is a vibration, for instance, the acoustic sensor might come into play. That particular module that runs the acoustic sensor might run. It might then call the routing module, which might then transmit a packet over to another sensor mode. You have static allocation here only. Here you typically don't have dynamic allocation because you don't want to have runtime overhead being incurred when you have only limited amounts of memory available. You can also do real-time scheduling, both hard real-time scheduling where you have deadlines for tasks, as well as soft real-time scheduling where you have soft deadlines for tasks. And finally, you have explicit interfaces by these modules so that you can accommodate different applications. A routing module that you write for the volcanic deployment could be reused in the enemy battle tank deployment scenario as well. Once you've written your application, and this discussion applies to the Mika mote over here, you would write your application on your laptop or workstation. Let's say that's your PC. It would be an SC program. You would compile it to an executable for the mote. You would then simulate it and debug it on your PC itself, on your workstation, laptop, whatever, but before deploying it on the mote itself. It's easier to simulate it on your workstation and easier to debug it there. TinyOS typically comes bundled with a TinyOS simulator known as TOSSIM, which allows you to simulate hundreds of sensor modes talking with each other and executing your program so that you can now debug your application very easily. Then typically for the Mika mote, you plug your mote into the port on your machine. So you plug your mote in here, and this would go into your machine, and you would download the program onto the mote, and then it's running your program when you switch it on. Some of the newer versions of motes allow you to download the program wirelessly over the wireless link onto the mote itself. And when you turn on your mote, it is running your application. Most of these motes run only one application at a time, but you can modify the TinyOS operating system to support multiple applications running as well. So what about energy savings? So these have very limited battery supply, and they're typically running in scenarios where it's difficult to recharge them. So these modes, like the Mika modes, come with multiple power saving modes. They could either be active, idle, or sleep. Sleep means, typically the Mika mode is asleep. It might wake up after a while, or it might wake up when one of the sensors goes on. Active means that the Mika mode is sending and receiving messages. Idle means that it is alive, it's awake, but it's not necessarily doing anything interesting. It may be computing something, but it's not sending and receiving messages. Now, there is a tremendous variance in energy supply and demand. You could use batteries, you could use solar cells, you could use vibration to power your batteries and recharge your batteries. And in some cases, if you're deploying these sensor modes, some of these sensor modes in a building or in a bridge, you might actually be able to use power off the wall, of the AC socket of the wall, to charge these. So you don't necessarily need to worry about recharging the batteries or replacing the batteries. In essence, you need to worry about sources when you think about what your deployment requirements are. If you have a long-term deployment requirement where you're deploying these in inhospitable terrains, then you want to make sure that you're conserving power. If you have a short-term deployment, then you could worry less about power. Also, how much bandwidth is being used by your application is another thing that you need to worry about. Some numbers here from the 2AA batteries being used. This consumes 200 microamps of average current. This may not mean much in this particular scenario, but it's an interesting fact. So the TinyOS itself is a fairly small operating system. The software footprint is just 3.4 kilobytes, which fits just about perfectly on the 4 kilobytes of RAM that is there on these Mika modes. But this also means that you can't really load a lot of data. You need to process data rather than just store data on there. Power saving modes, as we've discussed, are active, idle, and sleep. Among all the capabilities on this Mika mode, the radio transmission is the most expensive. It consumes the most power. It consumes 12 milliamps of power. The second highest power consuming capability is the CPU being active, where it's computing actively, which consumes only 4.6 milliamps of power. This essentially means that when you write a program for these Mika modes, you may want to prefer computation over transmission of data. So it's much better for you to compute an average, and then send over the average rather than send over the raw data itself. And this has led to many in-network aggregation approaches being used for sensor networks where these sensors are talking with each other over the wireless network. Essentially, in these network aggregation approaches, you would build trees among the sensor nodes with the base station at the root of the tree, and internal nodes would receive values from their children, would compute an average of these values or some other summary, and then transmit these values up to their parent. And finally, the base station, which is at the root of the tree, gets the summary value, the final average value. This is far more efficient than either sending the raw values over to the base station or communicating directly with the base station, which involves far more power because you're sending over much longer distances. This also allows the base station to be fairly far from the center of action. For instance, you don't want the base station to be near the volcano, you want it to be far away. So this is also the correct, sensor nodes also have the correct direction for the future technology, because today's growth rates are that the size of data is growing much faster than the cost effectiveness of storage, which in turn is growing much faster than the speed of CPU, which in turn is growing much faster than the speed of communication growth, which in turn is growing much faster than the battery. So the energy storage, the batteries themselves are growing at the smallest rate. Due to hostile environments, whether they're battlefields or the environmental scenarios, as well as the cheap fabrication, you could have higher failure rates in sensor nodes. And so you need these sensor networks to be self-organizing, you need them to be self-managing, you need them to be self-healing. When a failure occurs, you want the sensor nodes themselves to figure out new paths to send the data to the base station. And finally, you want these distributed protocols to be scalable. You want the number of messages to scale well as the number of sensors grows. So if your number of sensors doubles and your number of messages goes up by a quadratic, if it goes up by a factor of 4, that's not a good scalable protocol. You want it to be growing up linearly, if possible sublinearly, as the size of the sensor network grows. In general, related to this direction of sensor nodes are a couple of other directions that have also emerged recently. ASICs, known as application specific integrated chips, are chips that are built for specific applications, and those can be used on these sensor modes. FPGAs, or field programmable gate arrays, where you can actually program the hardware itself for a specific application, have also emerged in the last few years. These are of course much faster because you are moving a lot of capability and functionality into the hardware, and anything that you can put into hardware is much faster than doing it in software. Sensor nodes are cheap and battery limited. You can deploy them in inhospitable terrains, whether they're enemy battle tank deployments or around the periphery of a volcano or in an island to monitor heat and humidity. But you need to conserve power because it's difficult to recharge these sensor modes frequently. So you need to be smart about the design of the operating system, and the TinyOS operating system has been built exactly for this. And you also need to build distributed protocols very, very well. We've discussed the design of TinyOS and a few challenges when it comes to designing distributed protocols for these scenarios. Related to this discussion are a few other topics that you can look up. The Raspberry Pi and the Arduino platforms have emerged in the last few years, which allow you to program small manageable computers very easily. And you might want to look these up. These are very interesting topics if you've not heard about them. Home automation systems use a lot of sensors. These include companies such as Nest, Amex, Home Logic, Honeywell, etc. Typically, these are sensors that control the temperature in your home or control the locks in your home. The power concerns are smaller because they're typically connected to AC power, but you have security and accuracy concerns here. You want your home automation systems to be accurate, to let you in the door, to set the correct temperature when you so desire. Typically, it's possible to network these devices together in your home. These are known as Internet of Things. That's a key phrase that you might hear. Essentially, this means that you're networking many devices or many of these sensors together into a network, and you're then managing them over the network. Often these are known as cyber physical systems. When you have human beings involved along with sensors and devices networked with each other, these are known as cyber physical systems. Cars and vehicles today, for instance, have become networks of sensors, where you have sensors at the tires monitoring the pressure, you have sensors in the engine monitoring the status of the engine, and all of these are talking with each other and are then relaying the alerts to you on your dashboard when you're driving. These combinations of humans and machines are often called cyber physical systems, and these are becoming more and more widespread For instance, in operation theaters and hospitals, doctors are increasingly using machines around them to make sure that there is more accuracy and in the operations itself, and that the doctors are being assisted as much as possible. Hi everyone, we are here at the University of Illinois campus in the Siebel Center for Computer Science. That's the Department of Computer Science. And today we are talking with someone who is an expert in SDNs, or software-defined networks. And we are here with Professor Brighten Godfrey, who's going to tell us more about SDNs.
Hi, so thanks for having me, Andy. So my name is Brighten. I'm a professor in computer science here. I've been at the University of Illinois for about 5 years. And before that, I was at Berkeley, where I did my PhD with Jan Stoika. And before that, Carnegie Mellon. So now I am in the systems and networking group here. So I work on a broad range of things within networking and theory of networks. So including algorithms and software-defined networks, network verification, data centers, and the wide area internet.
So can you tell us a little bit about what software-defined networks are?
We have networks that work reasonably well because we have, these brilliant masters of complexity who can deal with that level of complexity to run a modern network. What the vision of software-defined networking is that that structure of network needs to be refactored and abstracted. And there's, I would say, 3 key features that you would find in a software-defined network to achieve that goal of programmability. The first is a well-defined interface to the switching hardware. So what we would call the data plane, where packets go into a box and they are, inspected and processed and sent out. So that involves, looking up a destination in a table, maybe doing access control on packets, some kinds of packet filtering, basically the fast path of processing packets. That's what you have specialized network hardware for, is handling data flow through the network quickly. But the idea is we want a low-level, well-defined interface to that fast hardware. And that piece of SDN is today embodied in the OpenFlow protocol, but it wouldn't have to be the OpenFlow protocol, and even OpenFlow itself is evolving. So we've got an interface to the data plane. If we have that interface, what we can do is lift out the intelligence from the individual boxes and centralize it. So we have a central controller or multiple controllers that are coordinated as a distributed system, but a logically centralized controller that's now going to define the policy and push it out to the switching gear. So that's the second key abstraction, is this idea that we can centralize the intelligence. Once we have that centralization, then the third idea is that we can build programming abstractions that help us orchestrate that whole network. Right? So the sort of minimal level of this would be that the network operating system, if you will, that's running on the central controller will take care of building a picture of the topology, snapshot of the topology, and presenting that to a higher level application. And then it will also take care of, once a decision has been made about how to handle data flow, pushing that out to the devices in the network. And then you can think about higher level abstractions, and this is where a lot of the interesting research has been, of how would you make networks easily programmable? Do you need a new programming language? Do you need libraries for doing certain kinds of computations? How do you structure network programming? So that's kind of a quick overview of these, some of the key features that you find in an SDN. And it's a term that it is sometimes overused and applied in different ways. But those three key features are part of what I would say is the consensus vision, that you have a well-defined interface to the data plane. You have the ability to centralize intelligence, and then you can build higher-level policy abstractions in that centralized controller.
So from what you described, it seems like the collection of routers and switches in the network, they behave as a distributed system with maybe a central controller or a distributed controller. Does that mean that distributed algorithms like the ones that the students are learning in the class, things like consensus, Paxos, those are now directly applicable in SDNs?
Absolutely, yes. In fact, they're already used in deployed controllers because you like this abstraction of a single centralized controller. So that's how we like to program. It's easy to program, a single app, single-threaded, has one view of the world. It's not a distributed system, but that, of course, is a lie. It is a distributed system, and you can't have just a single controller because it would be unreliable, right? So the single controller can fail. The connections between controllers and switches can fail. The network itself can become partitioned, and then that controller is going to be on one side or the other side of a partition and wouldn't be able to control the gear on the other side, right? So if you look at production deployments, like, for example, Google's deployment of SDN in their wide area backbone, it's a distributed system all over the place in every layer, including the switching gear itself, where there's very interesting questions of timing of events that you install into the switching gear. Like, I asked the switch to start dropping these packets or sending these packets over here, and I asked this other switch to do something else. But I don't know exactly when those events are going to happen. And so you get into consistency problems within the network itself that might manifest in packets going in a loop, or a service being unreachable, or potentially even worse, if maybe leaking out sensitive data if you don't take care to understand that the switching gear itself is a distributed system and you don't have good control over the timing. And in the controllers, in production deployments, like I said, there are replicated distributed controllers that run algorithms that I'm sure your students are learning, Paxos and other variants, to build a consensus view of what the network is, so that you can then write a policy on top of it and install it into the switches.
And are SDNs applicable only to the wide area network, but or also to data center networks themselves inside the data center?
Yeah, that's a good question. So I think there's a lot of excitement around SDN, and there's a vision that SDN will be everywhere, right? And that may be true, but one question is, what are really the killer applications that are going to drive early deployment? And I would say there are two applications that, at least, that have become really valuable. And one is in the wide area and one is in the data center. In the wide area, and a good example is Google's wide area backbone, these are very expensive networks carrying huge volumes of data between large data centers, for example, 12 or 13 sites in Google's network. And so optimizing that flow of data very carefully has a huge amount of value because the cost of sending it and the volume is so high, right? So having the ability to do optimization of that data flow programmatically, of course, is really valuable, right? And using traditional algorithms in Gear, it would be very hard to just say abstract away the data flow and plug it into some optimization package like a linear program solver to find an optimal flow of traffic, and then plug that into the network. But once you've gone to the significant amount of work that it takes to build an SDN, then you can do that. Then you can say, all right, here's my traffic flow. I'm going to optimize it. This is exactly what I want to happen. Program the switches, and you're done. So that's a wide area app. Now, in the data center, a killer app that's been there that's gotten a lot of traction is virtualization of the data center. So you want to be able to dynamically provision virtual networks, such as for a tenant within a data center, that are isolated from other virtual networks and that present to that tenant when you're renting space in a cloud. You want it to look like your network, and potentially even a network with certain functionality or topology, but just at a minimum, you've got a collection of virtual machines and you want them to be connected on some virtual network, and those virtual machines may actually be behind the scenes moving around, and the virtual network can be moving around. So orchestrating that dynamic provisioning of virtual networks in data centers has been one of the early applications of SDN.
So software-defined data center, software-defined storage are new terms that are coming up right now. Do you think there are lessons that can be learned from software-defined networks that can be applied to these areas?
The ability to think of the whole data center as sort of one organism, and develop effectively an operating system for a data center I think that's the idea that these different research and industry thrusts are pushing at, right? So instead of having a monolithic operating system on each individual router and switch that has all its intelligence there, now we're thinking about the network as one cohesive unit that we want to coordinate, right? And then we have to think about traditional distributed systems issues. We have to think about traditional operating systems issues like resource isolation and task scheduling. And bringing these together with other parts of the data center, storage and compute, and then thinking about that whole together, that's a pretty interesting direction, actually. So I think we're going to see more and more work on, for example, jointly coordinating and optimizing flows in the network along with placement of VMs and applications, for example.
So I want to return to something that you mentioned earlier, which is data center topologies. And I know you have done quite a bit of work in that area. Can you say a little bit about the work that you have done in data center topologies?
Sure. So now some of our research has been on thinking about how you structure this topology of the network. And there's a couple problems with a fat tree-like design. One is that both the fat tree and a number of other structures that have been proposed, topologies that have been proposed, and there are many of them, are rather inflexible because you're building a very specific structure with certain numbers of switches that are connected in certain patterns. And so if you're incrementally expanding your network, or if you want to use heterogeneous components, right, you get upgrades, then how do you build it? What does your network look like? And it can be very inconvenient to either restructure it or to maybe leave ports free for later expansion, but then you're wasting capacity.
Right, so scaling is hard.
Scaling is hard. Scaling is hard. And then another problem is just that, well, you'd like to be as efficient as possible. These networks are very expensive because they're provisioned for worst case traffic, right? So these are not cheap networks. So what we looked at was taking a step back and said, okay, well, if these rigid structures are rather inflexible, hard to scale, what if we get rid of structure completely? What if we build a network out of a random graph? And this sounds a little bit crazy at first, because you have no idea what you're going to get. Why would you take this data center that you want to be very highly reliable and high performance and just completely randomize its network so it looks like a bowl of spaghetti? The first reason for doing this is that it's extremely flexible, right? So if you want to expand your network, it becomes adding a switch and doing a few random swaps of links, and you're done. If you want to use heterogeneous components, no problem. Just throw it into the mix, randomly wire it in, and you're done. So that's a clear advantage, and you can quantify that and get, show a clear cost savings. Now, a surprising thing is that, okay, what happens to performance? Do you do worse? How much worse do you do when you completely randomize this topology? And the answer turns out to be that the random graph gets higher performance with the same equipment by roughly 25 to 40%. And that's kind of a counterintuitive result, that you can take these carefully structured networks that people have been using and designing for decades, not only in data centers, but going back to high performance computing. And there's more and more connections between HPC and data centers. You take these networks that have been very carefully designed and structured and completely randomize them, and you get better performance. That's kind of a counterintuitive result, but what it stems from is the idea that is sometimes called 6 degrees of separation. Okay, that when you're in a network that has randomness, like a social network, like people we know, you're connected by very short paths with basically anybody else. And the reason is that the connectivity is very diverse. The connections to other nodes in the network are very diverse. So diverse connections means that you can reach a large number of people in a small number of hops through this network. Same for the data center network. You can reach servers on average in fewer hops. So if you have shorter paths in terms of number of switches that you have to traverse, then you're using less network resource to send the same packet, right? If I go 2 hops instead of 4 hops, I'm using half as much bandwidth. So that means that you can support more servers with the same equipment.
Would you also say that a random network costs less to build than a factory network where you have some very high-powered servers or switches?
The goal is that you can have higher performance with the same equipment, or you can have the same performance with less equipment, right? So you can choose to use fewer switches, fewer links. And there's a lot of interesting questions here. I'm making it sound kind of simple, but there's some big questions about how do you cable up this complex topology? Is that going to be difficult? Are you going to get consistent performance with an unstructured network? How do you do routing in an unstructured network, and how do you do load balancing so that you can really extract all of the value from that potential bandwidth? So those are systems design questions that are good questions, and we've solved those problems, but there's interesting stuff in there. The routing in particular connects with SDN. So this is a good example of where you can use SDN for routing. If you use traditional means of pushing data through a network, you don't actually get a great load balance, especially with a complex topology. So it's particularly for this random network, for this jellyfish design as we call it, in the Jellyfish network, you can use SDN to great advantage because you can do better traffic optimization, and it makes a particularly big difference in this unstructured network.
Where do you think software-defined networks are headed in the next 5 years?
Those are big questions. So for software-defined networking, I think what's particularly interesting is how do you build this operating system that makes programming networks convenient? And I feel like we're just scratching the surface. There's some interesting work on programming languages for networks, but there's many different possible programming languages. Do you need a programming language? Do you need good libraries? Should you think about maybe using a database-like interface to a network, which is something that one of our postdocs here, Anduo Wang, is exploring. The question of how you build these abstractions that make networks easy to program, so you can basically control a network in an intuitive and powerful way, whether that's optimizing traffic or responding quickly to security threats. I think that's going to be a really interesting space. And both in research and in industry, there's a lot of uncertainty about what those controllers are going to look like. I think the general vision towards opening up an interface to the data plane and centralizing that intelligence is a direction that's pretty clear. But then how we make that programming convenient and powerful is, and what particular controller implementations are really going to take off in industry. Those are big open questions that we're going to sort out as a community over the next 5 years.
My last question is more about how it feels like to work here at the University of Illinois, and also working at your startup company. What does it feel like here?
So UIUC has been a great place. The best thing about being a professor anywhere is getting to work with students, and we have great students here. Sitting down with students and just talking for a couple hours at a whiteboard about ideas, and then going home and thinking about something in the shower, and you get an idea and you come back and talk to your students the next day. That's a really fun process, and seeing that over time. When you start in research, it can seem hard to make progress. But then if you keep, persistently plugging away at it, and then look at what you've done, over a period of a year, then you can see, hey, I really did something new. And the process of doing that for myself when I was a grad student, and now also, seeing that happen and seeing students get excited about research has been great. So I love teaching. We have great students and great colleagues, and you're getting to teach a lot of students. So you're particularly lucky.
Congrats, you have made it to the week 5 of C3 Part 2. This week we're going to study the classical concept of security. We'll see some of the basic security concepts. We won't go into the depth of security concepts. After all, you can teach an entire course on security in cloud and distributed systems. But in this series of lectures here, we'll just provide you some of the basics. We'll also see some interesting case studies of data center outages. We'll learn from real examples of what went wrong in real data centers and what caused these cloud outages, so that we can be better prepared with designing applications that run on these clouds, applications that are tolerant to such outages, and also if you happen to be in charge of such a data center, how you can avoid such data center outages in the future. Hi there. In this next series of lectures, we're going to see some of the basic security concepts as applicable to not just distributed systems, but also as used in general computer systems. So there are many different kinds of security threats that can be launched on a distributed system or any system that uses servers. Three of the common security threats are leakage, tampering, and vandalism. Leakage essentially means that someone gets unauthorized access to a service or to a data, that they're able to read the data or access the service while they should not actually be able to. For instance, if someone else gets to know your bank balance, who is not authorized to know your bank balance, who is not one of the account holders on your bank account, then that's leakage. Tampering goes a step further, where someone not just gets access but is able to modify data or is able to modify the service. For instance, if an unauthorized individual modifies the balance in your bank account without you having authorized that, without you having written a check or done a bank transfer, then that is known as tampering. And finally, vandalism essentially means that someone interferes with the normal service or normal operation of the system without necessarily benefiting directly from this attack. The most common type of vandalism attack is a denial of service, where, for instance, a particular service may be inaccessible to legal customers because an attacker is bombarding that service with a lot of unnecessary messages. So these threats are typically carried out via some attacks. Some of the common attacks are listed on this slide. Eavesdropping essentially means that the attacker is able to listen to messages by tapping into the network. For instance, if someone is able to intercept all the messages in the network, then they're eavesdropping. Masquerading goes a step further, where the attacker is not just able to read messages, but is able to pretend to be someone else. And you'll see an example of this as we discuss some of our security protocols. Essentially, this is similar to identity theft, but in the computer world, where a machine claims to be acting on behalf of user Alice, while in fact they're acting on behalf of user Eve, who is evil. Then you have message tampering, where the attacker is able to modify messages in the underlying network and send them forward so that they can, for instance, masquerade to be someone else. You have replay attacks, where the attacker is able to replay old messages. This is a particularly insidious form of attack, where by replaying old messages, for instance, you can prove yourself to be someone else that you're not. And finally, denial of service is typically carried out by bombarding a particular port, say the HTTP port, so that the other regular messages by valid legal clients cannot get through that port, just because of being overwhelmed by the other messages being sent by the attacker. So how do you address these challenges? Well, there are three properties that secure systems typically try to provide. These are known as the CIA properties. They stand for confidentiality, integrity, and availability. Confidentiality essentially says that you're protected against disclosure of your data to unauthorized individuals. This addresses the threat of leakage. It says that your data is essentially confidential, and only those who are allowed to read the data are able to do so. Integrity essentially says that only those who are allowed to alter the data are allowed to do so, who are able to write the data are allowed to do so. For instance, for your bank account, it may be only you who is allowed to alter the data, and of course the bank, who might be acting on behalf of you. Anyone else would not be able to alter or corrupt your data. This addresses the threat of tampering. And finally, availability says that the service or the data is always reachable, is always readable and writable. That is, you're able to carry your operations on the service or the data. And this addresses the threat of vandalism. So these three properties are examples of properties that we desire in a system. This is what we want the system to achieve. We haven't yet said how the system achieves these three properties. So this difference between what and how can be laid out by differentiating between policy and mechanism. And this is one of the key aspects, key concepts in distributed systems as far as security is concerned. This is very important for us to understand. This has been advocated by many scientists and is actually used by secure systems today to differentiate between what and how. A security policy indicates what a secure system wishes to accomplish. Okay, so this is typically a human level goal of what you want the system to be secure against and how you want it to be secure. For instance, the CIA properties, the confidentiality, integrity, and availability properties are properties that we desire from a secure system, and so these are security policies. A security mechanism, on the other hand, indicates how these goals are accomplished. So given a security policy, you can design security mechanisms which then implement that particular policy. For instance, you could use encryption capabilities and a variety of other mechanisms that we'll all see in this series of lectures to implement a given set of policies. It's very important for you to be able to distinguish between a security policy and a security mechanism, because typically these are separate, and it's not always the case that a set of security mechanisms always accomplishes a security policy. That gap is typically what a designer of a secure protocol needs to bridge. So what kinds of mechanisms exist? Well, there are three types of mechanisms that are popularly used. These are known as the golden A's by some security researchers. They are authentication, authorization, and auditing. Authentication essentially is a mechanism that verifies that a user claiming to be, say, Alice is in fact Alice. And of course, the user is communicating over the network, so the only way you have of authenticating the user is via message. Suppose we authenticated the user and we know that Alice is in fact Alice, but we need to check that Alice, who is trying to access file foo, in fact is allowed to access file foo. Is Alice really authorized to access file foo in the particular mode that Alice is attempting to? That is what is known as authorization. That's the second A. The third A is auditing, and that stands for essentially knowing how a particular attack was carried out. So for instance, if Eve managed to attack the system and gain access to some data, how was that attack carried out, so that we can fix the system for the future. Typically, this is done by logging all the operations in the system and then later on looking at the logs, mining the logs, perhaps replaying the logs and figuring out what went wrong. So how do you design a secure system? Well, essentially, it's kind of hard to do this because you don't necessarily know how powerful your attacker is. Your attacker may have access to data centers. Your attacker may have the capability to listen to all the messages that are in the underlying network. So when you design a security protocol, first you need to set down on paper what your attacker model is. What are your assumptions about what your attacker is able to do? For instance, you might assume that your attacker is able to read messages in the underlying network, but is not able to modify messages. A different attacker model might involve the attacker also being able to modify the messages. So what are exactly the assumptions that you assume from your attacker? This is very important to lay down on paper. Of course, this attacker model should be tied to reality, which means that you can't just make up an attacker model out of thin air. It needs to actually be an attacker model that is somewhat real, that corresponds to real attackers. So once you have the attacker model, then you have the problem statement, and you now need to design the security mechanisms that satisfy the policy that is specified as a part of the problem statement. Then you need to analyze and prove, perhaps formally prove, that the mechanisms that you have designed in fact satisfy the policy under the attacker model that you have assumed. And this is an important part of any secure system design. Finally, when you design a secure system, you need to analyze the behavior of your system when there are no attacks. This is the common case. Attacks do happen, but they're not the common case. They happen rarely. And when there are no attacks going on, you want your system to be as fast as when the system did not have any of your security mechanisms in place. Okay, so analyzing the effect of your security mechanisms on the overall performance is very important. Typically, when you add security mechanisms to an existing system, which was insecure to begin with, you're going to impact the performance of the system. Perhaps the throughput will go down by a few percentage points. If your throughput goes down by, say, 2 or 3%, then that's probably acceptable performance overhead. But if your throughput goes down by 100%, then you're in trouble, because now you're incurring a much higher cost for the security mechanisms, and that's probably not a good set of security mechanisms anyway. So in the next lecture, we're going to see some of the basic cryptography techniques, very basic cryptography techniques, and then after that we'll use cryptography to implement some of the mechanisms that we have seen in this lecture. In this lecture, we're going to see some basic cryptography concepts. These are applicable to not just distributed systems, but computer systems in general that want to use cryptography. So an important terminology that is used in a lot of security protocols, especially when discussing cryptography, is that of principals. And essentially, a principal is a process that carries out operations or actions on behalf of a user. If I say a principal is Alice, essentially that means that the process is acting on behalf of the user Alice. Similarly, Bob, Carol, and Dave are used as other principal names. And as you can notice, these are starting with the letters of the English alphabet. Eve is typically an evil attacker, Mallory is typically malicious, and Sarah sometimes is used as the server. So in cryptography, an important concept is a key. A key is essentially a sequence of bytes that is assigned to a user, and the key can be used to lock a given message, any given message. So you can take a message and you can take the key and you can lock the message so that only that key can then be used to unlock that particular locked message. Okay, so if you don't have the key, then you cannot unlock that message. Essentially, this is used to ensure that messages are sent over the network in a way that only authorized individuals who have access to the key can in fact unlock that locked message. Keys are used in many different ways, and there are different flavors of using keys, and there are many different flavors of key-based systems. The way in which you use a key is you take a message, you apply the key on it, and this process is known as encryption. This leads to an encoded message, which is again a sequence of bytes. But essentially the encoded message, the sequence of bytes, would not make sense to any attacker who is able to intercept the message on the network unless the attacker also has access to the key. So only those with access to the key can take the encoded message, the sequence of bytes, use the key on it, and then use decryption so that you can get back the original message, the original sequence of bytes. If you don't have access to the key and you use decryption on the encoded message, you're likely to get back some garbage gobbledygook, which is not the original message. So no one can decode an encoded message without having access to the key. So if you have two individuals that have access to a given key, only those two individuals can send messages to each other that are encoded and decoded, or encrypted and decrypted using that particular key. No other attacker or no other individual in the system, even if they are not an attacker, would be able to listen to messages that are being exchanged by this pair of individuals. So as I mentioned, there are different flavors of cryptography systems. There are two important flavors. They are symmetric and asymmetric. Let's discuss the symmetric first, and then we'll discuss the asymmetric later on. So in symmetric key systems, Alice may be given a key. We'll note that as K sub A or just KA. This key is secret to Alice. There might also be a key that is shared between Alice and Bob. That's denoted as KAB, sometimes as KA, B. This key is known to both Alice as well as Bob, and this can be used to encrypt and decrypt messages that are sent between Alice and Bob. You use the same key, KAB, to both encrypt and decrypt the message. For instance, the data encryption standard uses 56-bit keys, and when you're given a message, DES essentially splits up the message into 64-bit blocks, and then it applies the 56-bit key to encrypt each 64-bit block, and the output is then concatenated to the previous block's output, and that's the encoded message. The second flavor of systems is what is known as public-private key systems. Here, each user is given not just one key, but is given a pair of keys. So Alice has both a private key and a public key. Alice's private key, known as KA-priv, is known only to Alice, and no other principal in the system knows Alice's private key. That's why it's private, it's secret. KA-pub, Alice's public key, is known to everyone in the system. Okay, this is the exact opposite of the private key. Okay? But the private and public keys are paired with each other in a special way, in the sense that any message that is encrypted with the private key, Alice's private key, can be decrypted only by using Alice's public key. And the reverse. Any message that is encrypted using Alice's public key can only be decrypted using Alice's private key. So typically you generate public-private keys in pairs using some well-known algorithm. These pair of keys are related to each other, so that a message encrypted with one key can only be decrypted with the other key and cannot be decrypted with any other key in the system. One of the common ways of generating these public-private key pairs is the RSA, or Rivest-Shamir-Adleman algorithm, which typically uses prime numbers. So RSA is a well-known standard, for instance, of a public-private key system. PGP, which some of you might be using already, known as Pretty Good Privacy, is another example of a public-private key system. Keys need to be several hundreds, in some cases several thousands of not just bits, but several bytes long. And the longer they are, the more secure is the system, because the harder it is for attackers to guess what the key is or to break the key. If the key is very small, say the key is just 4 bytes, and essentially the attacker can cycle through all the 2 power 4 combinations or rather, say it's 4 bits, right? And so the attacker can cycle through all the 2 power 4 combinations of ones and zeros, and whichever one leads to a message that seems to make sense would be your key. So the larger your key is, the more computationally difficult it becomes for the attacker to guess what your key is. How does everyone know Alice is a public key? Well, typically a public key infrastructure, or known as a PKI, is maintained, which maintains the public keys of not just Alice but all the principals in the system, so anyone can access anyone else's public key. If Alice wants to send a secret message M that Alice only wants Bob to be able to read, essentially Alice encrypts that message with Bob's public key. So you take the message M and you apply Bob's public key kbpub on it, and the resulting encoded message is then sent to Bob. This can only be decrypted by using Bob's private key, because that's the only key that's paired up with Bob's public key. And so Bob is the only one who has access to that private key, his own private key, and so Bob is the only one who would be able to decrypt this encoded message. Okay, so when you apply Bob's private key, when you apply decryption using Bob's private key on the encoded message, you will get back the original message. This is symmetric too, so you can do the same thing by using the public key first and then the private key next. So if you encode a message with your private key, then it can be decrypted using the public key. And this mechanism, you'll see later on, is used for implementing signatures in the digital world. So when do you use the shared or symmetric key system versus the public-private key system? Each of these systems has their pros and cons. Let's discuss the cons. The shared key system reveals too much information, makes it harder to revoke permissions from individuals. For instance, suppose there is a group of, say, 10 or 15 individuals that are sharing the same group key so that they can send messages to each other only within the group, and no one else outside the group would be able to understand these messages. Now, if you want to remove one principal from the group, essentially you need to change the group key for everyone in the group, okay? And that's potentially harder. So revocation is a fairly expensive operation in the shared key system. In public-private key systems, the disadvantage is that the encryption or decryption operation could be very costly, meaning it consumes time. So if you have a very large message, then encrypting the message might be very expensive. There are some variants of the public-private key systems where encryption is a fast operation, but in those variants, decryption becomes a slow operation. So at least one of these two operations ends up being costly and time-consuming. As a result, some systems use a hybrid approach where they might use a public-private key system to generate shared keys, and then later on use this shared key on the messages themselves. In the next lecture, we're going to see how to use the cryptography techniques that we have seen in this lecture to implement the mechanisms that we discussed in the previous lecture. Finally, we are going to see how to use the cryptography techniques that we have already seen to implement the mechanisms that we have already seen. So we're going to use cryptography to implement authentication, digital signatures, digital certificates, and then I'll discuss a little bit of authorization too, just for completeness sake. So first, authentication. Authentication is a process where two principals verify each other's identities. So if Alice and Bob are communicating with each other, Alice needs to convince herself that Bob is in fact Bob. Bob needs to convince himself that Alice is in fact Alice. There are two flavors of authentication. They are known as direct authentication and indirect authentication. Direct authentication involves direct communication between Alice and Bob. Indirect authentication uses a trusted third-party server. Typically, this is called an authentication server. For instance, it might be a server run by a well-trusted company like VeriSign. We'll discuss indirect authentication second. Let's discuss direct authentication first. So we have two principals, Alice and Bob, who already share a shared key. We call that KAB. And Alice and Bob need to verify that each of them is in fact who they are pretending to be. So Alice needs to convince herself that Bob is Bob, and Bob needs to convince himself that Alice is Alice. So for this, we use a shared key, obviously. So Alice first sends a message to Bob saying, hey, I'm Alice over here. And Bob sends back a random number, which is known as a nonce. A nonce is an accepted terminology and a popular terminology in security protocols. Essentially, Bob generates a nonce for every single session that he has with any principal, and for any single authentication session, a new nonce is generated. Why is this generated? Well, Bob wants to see Alice using the shared key on the nonce. So Alice sends back the value of the nonce but encrypted with the shared key. And since Alice and Bob are the only two with the original shared key KAB, Bob can now verify by using KAB on the same nonce RB that in fact Alice is in fact Alice, because Alice is the only other principal that has access to the shared key KAB. So at this point, Bob is convinced that Alice is in fact Alice. How about the reverse? Well, we do the same thing. So Alice also sends a different nonce, obviously RA, to Bob. Bob encrypts it with the same shared key KAB. And then when Alice receives this, Alice can verify that in fact Bob is Bob. Okay, so this is wonderful, and this particular protocol involves 5 messages, and it involves 5 message transmission times. Now let's look at it. So why do you need 5 messages? Essentially, Alice and Bob are doing the same thing symmetrically, but in opposite directions. Why not send this second nonce RA earlier, say with the first message over here with Alice, and then when Bob sends back its reply, already you can send back the encrypted version of RA. Okay, so why don't we run the more optimized version of this protocol, where RA, Alice's nonce, is sent earlier, and Bob can also send back its reply earlier. This is essentially trying to achieve, this protocol here on the slide is trying to achieve the same thing as on the previous slide, except it's using 3 messages instead of 5, and it involves only 3 message transmission times. Well, not so fast. You have to be really careful about protocols like this. If you try to optimize them, they may be subject to replay attacks. They may be subject to replay attacks even if you don't try to optimize them. So this particular protocol here is vulnerable to the attack known as a replay attack. So Alice may in fact not be Alice. Alice may in fact be Eve, who is pretending to be Alice. And so Eve might start a session saying, hey, I'm Alice, pretending to be Alice, with a new nonce. And then Bob sends back a new nonce RB along with the encrypted version of RA. Okay. Notice that Eve does not have access to the shared key KAB at all. Okay. So Eve has no way to decrypt this message KAB of RA or anything like that, but Eve can use the sequence of bytes or bits. How does Eve do this? Well, Eve starts a second session where Eve says, hey, I'm Alice. And in the second session, she reuses the same nonce RB that was sent by Bob. Okay. So at this point, Bob would send back a new nonce RB2, but also the encrypted version of RB encrypted with KAB. And this sequence of bytes can now be reused by Eve to finish the first session. So Eve now goes back to the first session and replies back to Bob saying, hey, here is the encrypted version of RB. But in fact, Eve did this without ever knowing the shared key KAB. But by simply reusing the sequence of bytes KAB encrypted, used to encrypt RB from the second session, by replaying this message, Eve is able to convince Bob that in fact she is Alice. And at this point, you have a security violation in your system. Okay, so now you've seen what a replay attack looks like. There are a variety of replay attacks that could happen in secure systems, but essentially it means an attacker is able to replay messages from a different session over here. So the second flavor of authentication is known as indirect authentication. This uses an authentication server denoted as AS over here. Typically this is a trusted server, trusted by everyone. So essentially every principal in the system shares a key directly with the authentication server. You can think of this being either the public-private key or a shared key in between Alice and AS, and also between Bob and AS. So Alice would send a message to the AS saying, hey, I would like to start a session with Bob. The AS sends back a ticket which consists of, the AS actually generates a new shared key for this particular session. This shared key is KAB, but it does not send back the shared key as plain text. Why? Because any attacker would then be able to intercept this message which is sent in plain text. Instead, the AS uses the shared key with Alice to encrypt the shared key itself, KAB, so that Alice is then able to decrypt this first part of the message and get the shared key KAB. And AS also decrypts KAB using AS's shared key with Bob. So Bob is able to decrypt the second part of the shared key, and no one else is able to do that. Okay, so Alice retrieves KAB from the original ticket message, and Alice and Bob are the only ones who will be able to decrypt parts of the ticket message. So Alice is able to decrypt the KAB, but then sends out the rest of the ticket, the second half of the ticket, onto Bob, which can then at that point obtain KAB by decrypting that second part of the ticket. At this point, Alice and Bob both have KAB, and they are the only ones to have access to the shared key KAB because no one else can decrypt parts of this ticket message. And now Alice and Bob can start communicating with each other by using the key KAB. So in this way, Alice and Bob use this third indirect authentication server to share a shared key. Next, we move on to digital signatures. Digital signatures are just like real signatures. When you sign a document, people expect that the signature is authentic, that no one is able to forge your signature, so it's unforgeable. Anyone is able to verify your signature. And finally, it's non-repudiable. Once you have signed something, you cannot withdraw that signature. So to sign a message M, so to say that, hey, I am the one who has signed message M, Alice would encrypt the message with her own private key. Okay, so when we were sending secure messages, we were using public keys to encrypt. Here we use a private key to encrypt the message. So you send the message M along with the encrypted version of the message M encrypted with Alice's private key. Why do we use the private key? Well, this allows anyone in the world to be able to verify by using Alice's public key that in fact this second part of the message, the signature, is in fact Alice's signature. So if you use Alice's public key to decrypt the second part of the message, you should get back the original message M, and in this way you know that Alice is the only one who could have signed this message. If an attacker, for instance, modifies some bytes of the message M, then decrypting the second part will not give you M, and so immediately you'll know that the message has been tampered with. If a different attacker modifies some of the bytes of the encrypted, the second part of the message M, the encrypted version of message M, then decrypting it with Alice's public key will give you some gobbledygook, and that will be different from the message M, and at this point again you'll know that the message has been tampered with. Okay, so this ensures that messages, if they're tampered with, can be discovered quickly. However, as you know, encrypting and decrypting can be fairly costly operations. They might involve a lot of time, as you have already seen before, and if you're going to do this signing business very frequently, this might become a very inefficient operation. To make it more efficient, you can use a one-way hash function first, for instance, secure hash algorithm 1, message digest 5, and you first hash the message, which is typically a fast operation and results in a small output, typically just a few hundreds of bytes. And then you use the encryption with a private key on this hash. Okay? So this ensures that you're using the encryption on a very small sequence of bytes, and so it's very fast. So you don't need to encrypt the entire message. And on the receiving side, when someone is trying to verify the signature, they can also hash the message. Again, the hashing operation is very fast. And then verify that when you use the public key on the second part of the message, you get back the hash of the message. And that ensures that the signature is in fact verified. Finally, we discussed digital certificates. Again, these are just like real certificates. So someone who gives you a certificate saying, hey, you have taken this particular course, C3 course, should also be able to give you such certificates in the digital world. And to do this, again, digital certificates use the concept of digital signatures that you have just seen. Digital certificates typically have a standard format, and they have a transitivity property. So they have a standard format so that principals who receive a certificate are able to verify that the certificate is in fact correct. They have a transitivity property. So if someone is giving you a certificate, that particular someone should be authorized to actually give you the certificate in the first place. And so you can trace the chain backwards, the chain of certificates backwards, and it should end at a trusted authority, which is at the root. So let's see an example of this. So say Alice opens a bank account at Charlie's bank, and so Alice is given a certificate, a digital certificate that says, hey, this is the account number for user Alice. The account number is 12345, and the certifying authority is Charlie's bank. There's a signature with the certificate, which is essentially you take the name field, the second field over here, the account number field, you mash them together, maybe do an addition or concatenation, whatever, something that is consistent, and then you take a hash of that for compaction, so that it's compact, and then you apply Charlie's private key to derive the signature. This means that anyone receiving the certificate would be able to use Charlie's public key to decrypt the signature and then verify that in fact when you add the name and the account number and hash it using the well-known hash algorithm, you get back the same output. If someone tampers with either the name, the account number, or the signature fields in the certificate, then the certificate will become invalid and people will not be able to use it. So essentially no one can tamper with the certificate itself without affecting its correctness. So Eve, for instance, who might want to insert the name Eve over here would not be able to do that, because then the certificate would become invalid. So here we have shown Alice getting a certificate from Charlie's bank, but Charlie in turn should be given a certificate, for instance, for Charlie's public key. So a certificate that says Charlie's public key is in fact Charlie's public key might be given by the Bankers Federation. So this would be a certificate shown here given to Charlie. Once again, here the name field says Charlie's bank, the public key has the actual public key in there, and the certifying authority is the Bankers Federation. So the Bankers Federation would then sign this message by using the name and the public key over here, along with the Bankers Federation's private key. So anyone receiving this would be able to then verify that in fact the name, public key, and the signature are in fact matching with each other. The Bankers Federation would be given another certificate by VeriSign, a well-trusted authority. The VeriSign would now be at the root of the certificate tree in this particular case. And this particular certificate given by VeriSign to the Bankers Federation would say that the Bankers Federation is being given the public key KF-pub, and then it's signed by the VeriSign authority. Everyone trusts VeriSign, we are assuming here, and so everyone is able to verify this certificate. So you've seen that we have constructed a chain where Alice is given a certificate by Charlie, who is in turn given a certificate by the Bankers Federation, who is in turn given a certificate by VeriSign. And so you have essentially a root, a tree, or a DAG, or a directed acyclic graph of certificates that might be given across pairs of individuals. And all the certificates, if you follow them in reverse, if you follow the chains in reverse, should lead to a well-trusted root authority. Finally, for completeness, we discuss authorization. So when you have a pair of principal trying to access a particular object, say trying to write a particular object, how do you know whether that is in fact an authorized operation? So for every pair of principal comma object pairs in the system, you may want to maintain information about whether that principal is allowed to access that object, and if so, in what modes. So some principals may be allowed to only read a particular object. Other principals might be allowed to read as well as write to a given object. This is known as the access control matrix, where every row of the matrix corresponds to a principal and every column corresponds to an object. So the I, jth entry in this matrix is maintaining information about whether the ith principal is allowed to access the jth object, and if so, in what mode. However, this matrix may be very large. There might be thousands of principals and there might be millions of objects in the system. Also, a lot of the entries in the matrix might be empty. It might be a sparse matrix, because in most of the principal comma object pairs, the default entry might be no access, right? So this is a lot of wasted space. Instead, you have two other options, the access control lists and capability lists, which are far more compact. The access control list is a per object list of principals who are allowed to access that object, along with the mode of access allowed to each individual. The capability list is kind of the converse, where you maintain a per principal list of files or objects that this particular principal is allowed to access, and the type of access that is allowed for that particular principal. You could also split up the capability list into individual capabilities, where for each principal comma file pair or each principal comma object pair, you maintain information about whether that principal is allowed to access that file or that object. Okay. In this slide, the terms file and object are used interchangeably. Wrapping up our discussion of security, security challenges abound in today's distributed systems, especially because of the large scale of these systems. There are a lot of threats and attacks that are possible on these systems. The confidentiality, integrity, and availability properties are desirable policies or desirable properties, and you use mechanisms to then implement these policies, mechanisms such as encryption and decryption. Also mechanisms such as shared key infrastructures or public-private key infrastructures. And these can be used to implement authentication, signatures, digital certificates. We've also discussed authorization, which is important in secure systems. In this next series of lectures, we're going to be seeing a set of case studies that look at particular data center outages that happened over the last several years, and also the causes for these outages. So just to start with, here's a simple quiz question for you to think about. This is not an automated quiz, but something for you to think about. Here are some possibly common causes of data center outages. When I say data center outage, I mean something like Facebook goes offline for several hours, or Amazon Web Services goes offline for several days, or some website goes offline for a significant period of time. When such an outage happens, clearly something might be happening at a data center. Why do you think a data center might go out? One cause might be power outage. Maybe they forgot to pay their bills. Second cause might be overheating. Maybe some of the servers are working too hard and they caused too much of a temperature rise, and that caused the data center to shut down. The third cause may be human error. Maybe someone committed a mistake. Fire is, of course, something that always could take data center down. And finally, you can have denial of service attacks, which are explicit malicious attacks by humans or bots on data centers. Which of these do you think is the most frequent? So Take a pick, and now the answer is human error. In fact, it turns out that 70% of data center outages are caused, at least the initial cause, is because of human error. Human error is not the only factor that comes into play, though. Power outage, overheating, fire, and a host of other reasons also come into play. But typically, the outage is triggered by a human error, but there are always other factors that keep the outage going, as you will see as we go along. To give you an example of human error being responsible for outages, here are some examples that I've taken from a website called availabilitydigest.com. One example was that a system operator mistakenly deleted the $38 billion Alaska Permanent Fund database and then also deleted its backup. This resulted in the entire database being gone. Right? So this is clearly a human error. The second example was when a maintenance contractor's mistake shut down the Oakland Air Traffic Control Center. Third example was a state of Virginia technician pulled the wrong controller and crashed a redundant SAN, a storage area network, that had already suffered a controller failure. Okay, so this is an example of an outage that started with a human error, that was triggered by a human error, but there were other cascading effects such as an already existing controller failure that caused the outage to become worse. And finally, another example was a technician with the DBS Bank made an unauthorized repair on a redundant storage area network and took down both sides. There are many more examples on this website, and here are some more. I don't want to go through all of these. I just want to point out one of them. You can pause the video at this point and read the examples, but one of them that is really useful here is this one highlighted in orange font. Siren noise damaged several disks, including the virtual backup disks. It's somewhat less well known that noise affects the performance of disks. There are some videos on YouTube that you can find that show this, but essentially because hard disks involve very precise movements by the head of the hard disk over the platter, the magnetic platter, noise can affect these precise movements and can affect the performance and the bandwidth, the throughput of these hard disks as well. They can also cause hard disks to crash, or rather the heads to crash, and the entire hard disk may result in lost data. So there are many more examples such as this, and what we want to be doing is picking a few of these examples, major outages, and studying them in detail. Okay, so why do we want to study these outages at all? Well, the first reason is because they're sort of fun to study. Schadenfreude is an English word originally from German that says that we take pleasure in the misery of others. That's not really our goal here. Our main goal here is to learn lessons, to study these outages as evidence of what could go wrong, and to draw conclusions about how we can avoid such outages. Okay, in general, we want to be able to learn about the actual behavior of systems in the real world, in the wild. After this course, you might write code for many different cloud computing systems. Your code is going to run on servers and data centers, and it's better for you to know what might go wrong with these data center deployments so that you can prepare ahead of time in terms of how your service runs. Okay, so this will hopefully help us design better systems in the future. Once again, the goal of this series of lectures is not to say that some companies are worse than others. It is not to point fingers. Everyone suffers outages. As we know in this course, failures are the norm rather than the exception. In fact, it turns out that the examples that we'll see for the most part are companies that responded very well to outages. When the inevitable outages did happen, the companies were very transparent and very open and very honest with their customers and users. And in fact, after the outages were resolved, the companies wrote post-mortem reports that analyzed the outage. And in fact, all the information you see here is open information that is available on the web from these post-mortem reports. Okay, so this goes along with the adage, what doesn't kill you makes you stronger. Okay, so we'll see a few case studies of outages, and then we'll learn lessons from them. In this lecture, we're going to study a particular outage that happened at the Amazon Web Services, the AWS service. So this outage occurred April 21st, 2011. And all the data and all the information we are going to see in this lecture are from a post-mortem analysis that AWS published after this outage was resolved. Once again, our goal in discussing this outage is not to say that AWS is a bad infrastructure. In fact, it's quite the opposite. AWS was very open and honest and transparent with its customers and users, and they kept giving continuous updates during the outage. And after the outage, AWS improved its infrastructure to avoid outages like this. And as you know, AWS continues to be one of the market leaders in the cloud computing area. During this outage, several companies using AWS, especially the EC2 service, Elastic Compute Cloud, went down. This included companies like Reddit and Foursquare. AWS dashboard showed problems with the EC2 service and also other storage services. As you'll see, the EBS service was the one that was the root cause of this outage. The overall outage lasted at least 3.5 days. There was also a long tail of recovery and some permanent data loss for some of the customers. So a little bit of background before we discuss the actual outage itself. AWS is split into regions. You can think of these regions as being separate data centers. For instance, there is a US East 1 region, there's a separate region called US West 1, and so on and so forth. Typically, customers who are running a service for their users want to run their service in a region that is close to some of their customers. So if you have a service that is running on the East Coast, you might want to host it on the US East 1 region. Each region itself is divided into multiple availability zones. The best way to think about it, the availability zones, is like there are different racks within the same data center. Okay, so you can have automatic data replication across availability zones within a region, but this has to be explicitly done by the customers, and not all customers choose to do it. Okay, and the outage here that we'll see affected a lot of customers that did not choose to do it. The outage really affected the AWS Elastic Block Storage Service, or EBS, which essentially is mounted storage devices that are accessible from the EC2 instances. So think of these as large volumes of data that are being stored, that EC2 instances, VMs, virtual machines are accessing them as they're running the service. Now in AWS, a single EBS volume runs inside an availability zone, and it uses two networks. A primary network that is used for EC2 and EBS control plane traffic. When I say control plane traffic, I mean basic operations like create a volume, close a volume, open a volume. This is as opposed to data traffic, which actually transfers the real data that is stored in that volume. Control plane traffic is relatively less in volume compared to the data plane traffic, but it is very, very important. So anyway, a primary network is used for EC2 and EBS control plane traffic, and a secondary network is used for overflow. The secondary network used to be over-provisioned when this outage happened, used to be over-provisioned with a lower capacity, because the only goal of having it was to catch some of the overflow traffic. If the primary network was full, then you would overflow some of the traffic to a secondary network. The control information is replicated across zones. This is for availability of the control information. And this includes meta information about the volumes, where they're stored, how much data is stored in them, but not the actual data itself. That's what I mean by control information. The EBS volumes are replicated for durability, and each volume has a primary replica. Whenever one of the replicas is out of sync, or when there is a node failure detected, the replicas are programmed to do aggressive remirroring of data, at least before this outage happened, which means that if the primary discovers that one of the backups is gone or missing or is not responsive, it will try to aggressively create another backup because it doesn't want to lose data if another failure happens at the primary. So here is the outage timeline itself. At 12:47 a.m. there was a routine primary network capacity upgrade that was supposed to be done in the availability zone in the US East region. The traffic was shifted off several primary network routers to other primary network routers. So far, so good. This was as intended. However, the critical error was that one of the operators involved in this capacity upgrade shifted traffic for one such router to a secondary network router. Remember that the secondary network router has very limited bandwidth because it's only for overflow. But when you shift the entire traffic from a primary network router to a secondary network, then the secondary network is going to be overloaded and is going to be overwhelmed with traffic. As a result, a lot of these packets and messages are going to get dropped, and several EBS volumes will now not be able to communicate at all with their primary. They don't have any primary network, right? So this means that the primary network is disconnected. The secondary network has low capacity and overwhelmed, and many primary replicas have no backup. The team quickly discovered this critical error after it started happening, and you might think that at this point the outage will start to recover. But as you'll see with outage case studies, outages keep cascading because of other reasons that come into play as well. In this particular case, after the team rolled back the critical error, the outage had already been triggered. Many primary replicas thought that they had no backup. These automatically started remirroring aggressively because they thought, well, there's no backup, and if another Faria happens at me, then the data might be lost, so let me try to create another replica. And this was happening at all the affected EBS volumes that were on that particular primary network. So all at once, the free network capacity was quickly used, and replicas were creating more traffic where they were trying to remirror the data. This overwhelmed the network even more and made things even worse. So you can see how this cycle is a cascading loop of very, very bad things leading to even worse things. And this is what is known as a remirroring storm, which affected about 13% of the EBS volumes in AWS. When the network was unavailable for the control plane traffic, this meant that it was unable to serve create volume API requests for EBS, which meant that new volumes could not be created. And so a lot of these control plane operations like create volume requests started to back up. They started to have a long timeout, and they started to build up in queues. When the thread pool filled up, the control plane started to reject these create volume requests, and this is where the customers and the users really started to see the outage affecting the service that they were trying to access or run. At 2:40 a.m., this is again at morning, the AWS engineers are working hard to resolve this outage. The team disabled all new create volume API requests. And at 2:50 a.m., within a few minutes, all error rates and latencies for the EBS APIs start to recover. They start to go down. Again, you might think here that the outage is starting to end here, but once again, cascading causes come into play. Two issues made things worse. The first is that primary searching for potential replicas did not back off. When they tried to create new replicas, they overwhelmed the network with traffic. This meant that they could not create new replicas. But the way the primaries were programmed was that they would try equally hard or harder to create that backup replica when they failed the last time. They did not back off, which meant that they did not wait for a longer time to make their next attempt of creating the backup. Okay, so this made the system much worse because it overwhelmed the network with data. Also, a race condition had been known to exist in the EBS code that was only triggered by high request rates, and this was exactly one of the situations where you had very high request rates, and so this caused even more node failures. So at 5:30 a.m. that morning, error rates and latency started to rise again, and the engineers had to grapple with this again. So once again, a little bit of background here. The remirroring is essentially a negotiation between an EC2 node, an EBS node, and the EBS control plane. This renegotiation is required so that you ensure that there is exactly one primary for each volume. Due to the race condition, EBS nodes started to fail, and the rate of these negotiations increased, and this affected the EC2 nodes as well. This caused even more node failures, and therefore it again caused the rate of negotiations to increase, and you can see how this cycle is a cascading loop of things getting bad and worse and worser. This resulted in the brownout of EBS API functionalities. A brownout is essentially where you don't have a blackout. It's not that the outage completely takes EBS out, but the operations are pretty unreliable. The brownout term comes from electric power, where instead of having white light, which is normal light, you'd have brown light when the voltage goes below the recommended voltage. So something similar happened in the EBS because of this outage. So at 8:20 a.m. in the morning, the team started disabling all communication between EBS cluster in the affected availability zone and the EBS control plane. The availability zone was still down and unresponsive or very slow, but the control plane started recovering slowly. At 11:30 a.m., the team figured out how to prevent the EBS servers in the affected availability zone from doing this aggressive, futile remirroring where they were not able to create any backups. And the availability zone started to recover at this point of time. Customers still continue to face high error rates for new EBS-backed EC2 instances until noon. New instances that were created with new EBS volumes still suffered fairly high error rates. And one of the reasons for this was that another new EBS control plane API had recently been launched, That was for attaching new EC2 instances to volumes, and that had some error rates and some bugs which were being hidden earlier by the outage, but that the engineers were seeing now that the outage was starting to get resolved. So again, these are other causes that come into play that keep the outage going on and on. So by noon, however, the good news was that no more volumes were getting into the stuck state, but 13% of the volumes stayed in the stuck state, meaning that they were not really accessible and they were not able to create the backup copies. There was a pretty long tail of recovery for this particular outage, and you can read more details about this on the post-mortem report. By noon, April 24th, which is several days after the outage, all but about 1% of the volumes had been restored. So 99% of the volumes that were affected had been restored. Eventually, 0.07% of the affected volumes could never be recovered, and the data was lost permanently. Amazon Web Services did give credit to these affected customers, not just the ones who lost their data, but also the ones whose service was unavailable for a significant period of time. This outage affected not only EC2 and EBS, but also affected the relational database service, also known as RDS, especially the ones that were single availability zone. So what are the lessons we learned from this particular outage case study? First, outages or failures that are large often start with a human error. In the AWS case, the human error was the operator moving the entire traffic from a primary network to a secondary network. And the secondary network was never intended to take over for the primary network. It was only intended to be an overflow network. But that's not the only reason why the outages keep going on. They keep going on, or they balloon, because of cascading other failures that happen in the system, which may or may not have anything to do with human error. For the specific case of AWS, this outage could have been avoided in some ways. First, if the network reconfiguration processes had been audited well to create, for instance, a step-by-step protocol for upgrades, and if the operator had followed these steps one by one, then perhaps the mistake that triggered the outage of moving data, all the data from a primary to a secondary network, that mistake would never have happened, perhaps. They could have had the secondary network not just be an overflow network, but instead have enough capacity to take over for a primary network. That would also have prevented the outage. The remirroring storm really kept the outage going, and if primaries had backed off, meaning that if they tried to create a backup, and if they fail, then they wait for slightly longer than the last time around to make their next attempt at creating the backup. Okay? If the primaries had backed off, then the remirroring storm would not have happened. Everyone would have played nice with each other, and the outage would not have kept cascading. The race condition also kept the outage going, so fixing it ahead of time might have prevented the outage from going on as long as it did. Users who wrote code to take explicit advantage of multiple availability zones were not affected as much by this outage as users who just had data on one availability zone. Also, throughout this outage, AWS kept giving continuous updates to its customers and its users and their users. But in general, AWS used this as an incentive, as a catalyst to design better dashboard communication tools. And if you go to AWS, you will find such dashboard tools that give the health of each one of their services. The same is true for other cloud providers too, like Google and Microsoft Azure and so on and so forth. AWS also gets service credits for its customers that were affected by this particular outage. In this lecture, we're going to study the outage that happened at Facebook a few years ago. So this outage happened on 23rd September 2010, and during this outage, Facebook was unreachable for 2.5 hours. This was the worst outage in the past 4 years leading up to then at Facebook. Facebook published a postmortem after the outage was resolved, and all the information you're seeing on this particular lecture is from that postmortem. Once again, our goal in studying this outage is not to say that Facebook is a bad infrastructure. In fact, it is a very robust infrastructure. And during the outage, Facebook was very open and honest with its users about what was going on. And after the outage, Facebook improved their infrastructure and continues to improve its infrastructure to avoid such outages. And as you know, Facebook continues to be one of the market leaders in the area of social networks. So a little bit of background before we discuss the actual outage itself. In Facebook, data is stored in a persistent store as well as in a cache. Okay, so the persistent store has many servers that are essentially the back-end servers storing the data. And the data includes, things like Facebook profiles, the updates, the status updates that you post, the friend information, photographs, and so on and so forth. The cache is another set of servers that is closer to the clients, that is running a distributed cache system. So the cache servers sit in between the persistent store servers on the one end and the actual client machines, the user machines, your browser and your mobile device on the other end. This system that includes a persistent store and cache includes configuration data, and Facebook has an automated system for verifying the configuration values in the cache servers. Whenever a particular configuration value is invalid, the cache server replaces it with updated correct values that it fetches from the store, from the persistent store servers. So on September 23rd, Facebook made a change to the persistent copy of a particular configuration. Unfortunately, that particular change was invalid. Okay, so this is where the human operator mistake comes into play that triggers this particular outage. When this invalid change was made, all the clients, when I say clients here, I mean Facebook cache servers, not your mobile device and your browser. So throughout this, when I say clients, throughout this outage, when I say clients, I mean Facebook cache servers. When these clients, these Facebook cache servers saw this invalid value, all of them attempted to fix it all at once. All of them queried this cluster of databases, the persistent store, to fetch the updated value. And the databases were quickly overwhelmed by these hundreds of thousands of queries per second coming from these cache servers. Pretty quickly, the team discovered this and fixed the invalid configuration. And at this point, you might start to think, well, okay, so now the outage is starting to recover or should start to recover. But as we have seen before with outages, they keep cascading because of other factors that come into play as well. When a client, meaning the Facebook cache server, received an error from a database, it interpreted this as invalid and deleted the corresponding cache entry. So essentially, when a database failed to respond, the client created even more requests to send to the database layer, to the persistent stored layer. So you can see this bad cascading loop happening where the database has an error, the cache servers see this error, they try to fetch information from the database, but because the database network is overwhelmed by these hundreds of thousands of queries per second, the cache server times out and panics, and it tries to query the database even more aggressively, or at least as aggressively as before. And this keeps the network always in a bad state and stuck in this bad state. In other words, there is no backoff. The cache servers did not slow down sending their rate of queries when they saw congestion in the underlying from the database itself. Okay, so this rinse and repeat cycle led to the cascading failures, and the outage kept propagating and continuing in this particular case. Facebook's solution eventually was to realize that they had to turn off the entire Facebook website. This stopped all the traffic to the database cluster, and the database started to recover. They slowly allowed users back on. This also meant slowly allowing the cache servers to come online, and the cache servers slowly started to update their caches. This kept the traffic to the database, the persistent stored layer, pretty low. But allowing these cache servers on in stages took a while, and it took until later in the day for the entire site to be back up. So what lessons to be learned from this particular outage case study? Well, first of all, a new configuration system design is what Facebook built after this outage to avoid exactly outages of this kind. The second was that when you cannot access a resource, in this case the cache is unable to access the database copy of a configuration value, you should not try aggressively to try to access the resource again. Okay? Don't try as hard or harder to try to access the resource. Instead, back off, which means that wait longer than you waited the last time to try to access the resource. So each time a request fails, you wait twice as long as last time. That's a potential solution. This is often known as exponential backoff. Such an approach is used in networking protocols like 802.11, as well as in transport layer protocols like TCP to avoid congestion. A similar approach may be needed when it comes to the data center layer in terms of avoiding such outages. In this third and last outage case study, we're going to study an outage of this company known as the Planet. This outage occurred on 31st May 2008, and once again, the information that I'm discussing here is available from the postmortem, which is available at the URL shown on the slide, which is an availabilitydigest.com URL. The Planet at that time, at the time of this outage, was the fourth largest web hosting company, and it supported 22,000 websites. It had 6 data centers at that time, 2 in Houston, 4 in Dallas. This particular outage took down 9,000 servers and 7,500 businesses. The outage started at about 6 p.m. with an explosion in the H1 Houston data center. A short circuit in the transformer set the transformer on fire. Normally, when the transformer goes on fire, the backup power supply, the UPS, kicks in to keep the servers online. However, in this case, the fire in the transformer caused an explosion of battery acid fumes from the UPS backup. So this was a cascading series of failures, physical failures, that caused the power to go out to several of the servers in the data center. Also, because this was fire, real fire here, this blew out 3 walls of the first floor. So this is an example of an outage that actually did not involve human error at all. I mean, you could argue that there was potentially maintenance issues involved here that could have prevented the transformer from catching on fire, but there was no explicit human trigger here that triggered this particular outage. It was really fire in this particular case. So there was an explosion. This blew out 3 walls of the first floor. Thankfully, no servers were damaged, but 9,000 servers were brought down because essentially they did not have any power source at all to them. And the fire department quickly responded to this, and they evacuated the building for the safety of all the personnel. They also directed that the backup generators could not be turned on because there was a fire hazard. Also, because of the fire hazard, no staff were allowed back in until about 10 p.m. However, there were several services that went offline and several customers who were complaining about their services being offline. And the rumor is that the Planet staff had to physically ship some of the critical servers to some of their other data centers in Houston and in Dallas on their pickup trucks and so on and so forth. Again, this is a rumor; it's unsubstantiated. I do not know whether this is true or not. But of course, they could not transfer all the 9,000 servers that were affected to the other data center because the other data centers were almost running at the capacity of their power and cooling. So by 5 p.m. June 2nd, power was restored to the second floor, and on June 4th, a couple of days later, the first floor servers were being restored back 1 rack at a time. So this was a very slow, painstakingly slow process of bringing the data center, the affected data center, back online 1 rack at a time. All the while, during this entire outage, the company was very transparent and open with its customers. They provided frequent updates to all its customers at the frequency of 15 minutes to 1 hour per update. And this kept the customers reasonably well informed about what was going on and what was the expected time to recover from the outage. What lessons can we learn from this outage? Well, first, outages will happen. Even if it's not human error, they're going to happen. Fire happens, right? As a customer who's running a service, your service on a data center, you may want to back up not just your data, but also your service across multiple data centers so that there is fault tolerance. So one of the data centers goes down, then the other data center is up and it's able to service at least some of the requests. Entire data centers could go down, entire companies could go down, they could go bankrupt. So you may want to have backups not just across data centers of the same provider, but across data centers of different providers. So for instance, you may want to run one version of your service on Google, on the Google Cloud, another version on Amazon Web Services, and another version on the Microsoft Azure service. These are sometimes known as business continuity plans that ensure that in spite of disasters that happen at these different providers, your service is still up and running all the time. However, running your service on these 3 different providers, like the example that I mentioned with Google Cloud, AWS, and Azure, is easier said than done today. It's very hard because these different cloud providers have very different APIs and very different ways in which they store data. It's an open question about whose responsibility should it be to replicate data and services across different providers. Should it be done by the providers themselves? Perhaps the customers pay some extra insurance money and the providers ensure that the data and services are replicated no matter what. Or should it be done explicitly by the customer? This, of course, is far more painstaking because it involves extra work at the providers, and also because the different providers store data in very different formats. So there's data lock-in at each provider, and when you want to transfer data from one provider to another, you need to export the data into a common format and then re-import it back into the destination data center format itself. So the whole problem becomes very challenging because of the lack of standard APIs, and also because of the lack of standard data formats, which leads to data lock-in at individual providers. Okay, so if you go the provider route, this may cost customers more, but it's sort of similar to insurance premiums. Maybe that's the way to go forward, or maybe customers will start to build their own business continuity plans that cover multiple providers. The next few years will tell us which way the industry is going to go on this particular front. In this lecture, we are going to recap and summarize some of the lessons that we have learned over the 3 case studies that we have seen of data center outages. Outages are inevitable, whether they are triggered by human error or whether they're triggered by fire or some other natural cause. They are going to happen no matter which company you are and no matter how robust you claim your infrastructure is. We have seen how the leading cloud providers, AWS, Facebook, and the Planet, suffered from outages. But these are 3 examples of companies that also kept their affected customers and users updated throughout the entire outage with frequent updates about what was going on. And after the outage was resolved, they gave the affected folks coupons and discounts. They also analyzed and published postmortems of the outage, what led to the outage, what kept the outage going, and how they fixed it for the future. All of these bolster customer confidence. So if you're going to run a data center for customers, it's a good idea to make sure that you're honest and open and transparent with users all the way through. Many companies today run dashboards with real-time information, so you can check out Google Apps status dashboard if you just search on Google for it, or check out the AWS dashboard if you search on any search engine for it. These have up to the minute information about which services are suffering from a bad state or which services are healthy, and if it's a bad state, what is currently going wrong and what is, in some cases, the expected time to recover from these outages. However, not all companies are as open as the ones we have discussed. RIM, which is the maker of the BlackBerry, had a very long outage in April 2007, a day-long outage, but they never published a postmortem about it. Hostway in 2007 informed customers that it would move its data center from Miami to Tampa and that they had a planned outage that would be 12 hours long, but when they executed it, the actual outage was between 3 to 7 days. So planning is very important as well. Overall, we learned a few lessons. First, the data center fault tolerance is somewhat akin to human ailments or medicine today. Most common illnesses are addressable today. So in most parts of the world, at least the developed world, common cold and the flu, influenza, you can just go to the doctor and they will give you a medicine for it, or you just take rest and you'll recover from it. This is similar to how crash failures are, or crash stop failures or fail stop failures are handled in most distributed systems today. There is well-known protocols and well-known distributed algorithms that are fault tolerant. However, the uncommon cases can be very horrible when the end-of-life diseases hit you. There are no really known cures for most forms of cancer, at least as of today. Similarly, when outages happen, it's very hard to respond very quickly to the outage. It's very hard to know what's going to go wrong during an outage and to prepare for it. Testing is very important. Whenever you set up a service, whenever you set up a data center, you need to make sure that you have tested it enough, especially that you have tested it for disaster tolerance. So for instance, American Eagle, during a disaster, when the disaster was going on, they discovered that they had a backup data center, which they had set up so that they could fail over to it, but they never tested whether the failover actually worked. So during the disaster, they discovered to their chagrin that actually the failover didn't really work, so they could not use their backup data center. Had they tested it well, then they would have fixed this failover mechanism. Upgrades that are planned but that failed are also a common cause of outage. So someone, for instance, tried to upgrade all the OSs and all the machines in a data center, but for some reason that upgrade failed. This causes those machines to be in a hung state and causes the data center to be out. Okay, so whenever there's an upgrade, you need to have a fallback plan that you can rely on in order to, for instance, roll back the upgrade and restore the old state. Data availability and recovery is something that we've talked about during the case studies. Business continuity processes and disaster tolerance is an important requirement for many of the cloud services today. This can be provided by cross-data center replication, either provided by the provider or provided by a customer explicitly by writing code for it. Consistent documentation is very important too. There are well-known books and well-known treatises on the fact that making lists is a very good way to make sure that you're not making mistakes. One of the examples of this is that there was an outage with the Google App Engine several years ago, and the outage was prolonged because the actual operations personnel did not know which of the versions of docs, which had lists of things to do on them, was the current latest version. There were multiple conflicting versions, some of them old, some of them new, but they didn't really know which ones were new and which ones were old. In order to avoid this in the future, Google has adopted the fix of explicitly marking old documents as deprecated, so that when someone looks at it, they know that, okay, this is an old version, and perhaps the document also contains a link to a newer version of the document. This is a good practice for us to follow in principle, even if it's for any other documentation that we write. Outages in general, as you have seen, in general are a cascading series of failures. They start with a trigger, which may be a human trigger in some cases, but they keep going. Because of other causes that come into play. And usually, somewhere along the way, there is a loop, a cascading loop that happens. And perhaps there are new ways, new techniques that we can discover or invent to break this chain, to break this loop, and to prevent these outages from going on for as long as they do today. There are also other sources of outages that we have not discussed in our case studies. Denial of service attacks, distributed denial of service attacks are well-known causes of outages. Internet outages, where the entire network is blocked off and there is no communication possible between data centers, is a well-known cause of outages. For instance, the undersea cable might be cut by a trawler. There might be a failure in the DNS. A government that engages in censorship might block particular websites by blocking the DNS entries. These are all well-known sources of outages. In some of these countries where DNS is blocked, there are alternate DNS services, open DNS services as well, that are available and that users use whenever they want to access a website that is otherwise censored. Many failures are unexpected, as we have come to know in this course, but also there are planned outages, for instance, kernel upgrades or upgrades of particular parts of distributed services. And so when you have planned outages, these need to be planned well. They need to have steps that are well documented and that are followed and ticked off by the operators as they go along from one step to the next. Also, you need to have fallback plans in place. So if this particular planned upgrade goes wrong for whatever reason, then what is the fallback plan? How do I roll back this upgrade so that I can get back to an operational state and then perhaps try the upgrade later on in the future? Hopefully this set of case studies has been informative to you, and that the lessons learned here have been both informative to you as well as useful to you if you're planning to start up your own data center or planning to run services on some of the existing data centers. Hi everyone, we are here at the University of Illinois and we are talking with Professor Paul Kwiat, who is a professor here in the physics department, and this is us playing 10 questions or 20 questions about quantum computing. Thank you, Paul, for talking with us.
You're welcome.
Please introduce yourself for our audience.
So yes, I'm Paul Kwiat. I'm in the physics and also zero-time apportment and electrical engineering department here. I've been here since 2013, and my area of specialty is quantum information, experimental quantum information, mostly with optics, with photons, and a lot of things with quantum communication and a little bit with quantum computation. But I teach a quantum information course here, so I guess I'm hopefully qualified to at least tell you what other people know about this topic.
And you've been here since 2003, right?
2001.
2001, right. So you work in quantum computing, obviously, and I'm wondering if you can tell us what the differences are between quantum computing and the traditional computing that have been around for many decades.
Yeah, so I guess I'd say that there are two sort of main differences one could think about. So first of all, the classical computing is based on bits, things that can be zeros or ones. And I happen to have brought here an example of something that could be a nice bit, something that could be a 0 or a 1. Obviously, in a normal computer, it might be some voltage on some capacitor plate or something like that. And of course, all classical computers are equivalent in the sense that you can run any program on any classical computer. So quantum computing is quite different because in addition to having 0 and 1, this is just being an analogy, but in a quantum bit, a qubit, we can have something that's a 0 and a 1 at the same time, a superposition of 0 and 1. OK, we'll come back to that in a minute because that's a problem. So that's one very different thing. And so there's a lot more information in a quantum bit than in a classical bit. You can think of, sorry, I don't have too many of these props, but there, we can write a general quantum state as a combination of a 0 and a 1, and it can have arbitrary complex coefficients as long as the sum of the squares of these two coefficients is equal to 1. And so you can think of that as being represented on a, because I have two coefficients here, and because the sum of the squares is equal to 1, that corresponds to two parameters, basically. So you can think of a quantum bit as represented like a longitude and a latitude somewhere on a sphere. So if you're at the top of a sphere, for example, you could call that a 0, and if you're at the bottom, you could call that a 1, and you can have 0 plus 1, or 0 minus 1, or 0 plus I1, basically anywhere on the surface of the sphere. So that's a lot of information compared to classical. So that's the one sort of part difference. The next thing has to do with gates. So of course you have gates in classical computing, and you also have them in quantum computing. If you think about a classical computer, there's for a single bit, there's only one gate. Well, I guess there's two. There's the identity. You computer scientists probably call that a gate, but anyway, that's not a useful one. And then there's the NOT gate. So in a quantum computer, all gates on a qubit become rotations about some axis on this sphere. So for example, we might rotate about this axis, this horizontal one, and that would take 0 to 1 and 1 back to 0. And every state on the sphere would get moved, well, except for the two that at the axis. So basically, it's a much more complicated set of gates that you can have. And also, if you combine different gates together, qubits together, where we have 2 qubit gates or something like that, then you can generate much more interesting states, so-called entangled states. And so just as an example of that, if you had a classical computer that had 3 registers, there, we'll do 3 registers. With 3 registers in a classical computer, you would have one of 8 numbers, because you could have 0, 0, 0, or 0, 0, 1, or 0, 1, 0, or 0, 1, 1. OK, 2 times 2 times 2, one of 8 numbers. But in the quantum case, you actually get, if I can do this, you actually get all 8 numbers simultaneously in the computer at the same time. OK, again, ignore the fact that these are decohering, that these are dropping out of that for the moment. So with just 3 registers, that's not so impressive. But if instead you had 300 registers, which your iPad or something has millions of registers in it. But with just 300 quantum registers, you can encode up to simultaneously 2 to the 300 numbers. And 2 to the 300 is like 10 to the 100 or something like that. And that's more than the number of particles in the universe. So even if you were to count every electron, you run out of particles before you get the number of states you could simultaneously put into a quantum register. And so that's going to enable a tremendous speed up in solving certain types of problems. And in particular, I guess the funny way of putting it is that there's an exponential speed up on an exponentially small number of problems, because it's not good for everything, but for some things it definitely has a huge benefit.
So essentially, when we do parallel computing, say with 4 processors, it might get sped up 4 times. It might be 4 times faster. But essentially, what you're saying is that with a quantum computer, you could be as fast as you possibly can, because essentially you have an exponential speed up.
Yeah, it would be like 2 to the 4 times faster.
2 to the 4 times, right. So we hear this term called qubits in quantum computing. Can you say what it is?
So a qubit is just the term of a quantum bit. So any representation of this 2-level system, so bit, but that can be in superpositions of the 2 at once. And so maybe I'll just talk about how you might get that physically in a physical thing. Yeah. So the simplest example maybe is, I guess there are sort of 2 that are pretty easy. One is, from chemistry, you know that in atoms there are electrons, and electrons have these different orbitals. And so, for example, you could call, if the electron is in its lowest orbital, you could call that a 0. If it's in some excited orbital, you could call that a 1. And you can put the electron so that it's in a superposition of 0 and 1 at the same time. It's in a superposition of both these locations at the same time. If that seems really impossible or weird to you, I would say, yes, true. But already the fact that when it was in the 0 state, the electron was already in all these different locations around the nucleus at once anyway. So in some sense, it's not really any, we've already had the weirdness put in. And now the question is, can we use that to do something? That's one possible way of getting of encoding a qubit. Other things that people have looked at is in superconducting coils, you can have the current going clockwise being a 0 and counterclockwise being a 1, and then you can get the current of electrons to be both going clockwise and counterclockwise simultaneously. I deal with optics a lot, and so we can use properties of photons. The one that we often use is the polarization of the photon, whether that's horizontally or vertically polarized, just like you would get with 3D glasses in a movie theater. And you can make superpositions of, say, horizontal and vertical, and that would give, say, something that was diagonal. And so it's real easy to see how you get those superpositions. Or if there are superpositions with a 90-degree phase shift, then you get circularly polarized light. And that's how the, not the IMAX 3D glasses, but the other one, the real 3D or whatever, they use circular polarization. So it's basically, the qubit is basically any quantum system that can be mapped onto a two-dimensional space where you can make these superpositions of the properties in that space.
And what kind of problems is quantum computing used to solve nowadays?
They were originally proposed by Richard Feynman as a way of basically solving physics problems, of doing simulation. So just like any classical computer can run any classical architecture program, any quantum computer in principle can solve any quantum mechanics problem, but in a way that's maybe a lot more controlled than you would normally have with the actual system that you're trying to study. So certainly quantum simulation is something that people look at a lot as a possible application, and I'll come back to that in a little bit. The main one that really started the whole field, though, is so-called Shor's algorithm. So Peter Shor, the theorist, I think at IBM at the time, who figured out that you could factor large numbers into their prime constituents using a quantum computer, and it wouldn't require the exponential speed up that we currently have. So currently with classical algorithms, it's an exponentially, as you increase the number of digits, then the time to do the factoring increases exponentially. And with a quantum computer, it doesn't, it decreases, it's only polynomially. And so there's a huge interest in that because, of course, that difficulty of that problem, or the perceived difficulty, is what a lot of our current classical encryption is based on. Like RSA encryption is based on the fact that that should be a hard problem to solve. It's not mathematically proven that it's hard that's a so-called NP-complete problem, or that it's a difficult problem, but it's strongly believed to be. So at the moment, what's driving this is this factoring sort of thing in terms of quantum computing, and then this possibility of doing quantum simulation.
You mentioned quantum computing being used to potentially break RSA cryptography. Is it possible to use quantum computing to come up with new ways of encrypting and decrypting data?
There are two answers to that. The answer is yes in both cases. So first of all, people try to find algorithms, classical algorithms, that are not susceptible to this exponential speed up. And so if you use, I think it's elliptic curve cryptography, I think, is that, I don't know, you're the computer science person, and maybe also Diffie-Hellman encoding. Those you only get a square root of n speed up because it's like this search algorithm basically, so that's not such a big speed up. So one thing is to try and redo your classical cryptography in ways that are not so susceptible to quantum computers. The other thing that you can do is quantum cryptography, which is actually mostly what my group is involved with, not so much quantum computing, and that's basically using single photons to generate a random key that you can then use to encrypt information. And because you have a single quantum system, and it's very fragile if you make measurements on it, so it's very fragile in the sense that this thing doesn't like to stay spinning in that sense. You can encode information in a way that you can detect if there's an eavesdropper who's been trying to monitor that information. And then you simply never have any transmissions that are encrypted using a key that an eavesdropper could have looked at without you knowing that an eavesdropper looked. So either you know that no eavesdropper looked at it, in which case it's secure and you can use it, or maybe you know that an eavesdropper did use it, did look at it, and then you just never use that key to encrypt anything. So in that sense, it gives you perfectly secure encryption. That is not breakable by a quantum computer, because basically it's just using so-called one-time pad encryption, where you just have your message and you add to each bit of the message, you have your key, which is a random string of zeros and ones, and to each bit of the message you just add a bit of the key, modulo 2. This is a string of zeros and ones that you want to send. This is a random string of zeros and ones. When you add these random string to this string, you get a completely random string. You just post that on the internet, or you call up the person, or you put it on Facebook or whatever. And if the recipient knows the same key, then they can undo the process and they get the original thing. Because what's being transmitted over the internet is just a random string of numbers, there's nothing to be broken. There's no code. There's no structure in it at all. It's just a random string of numbers. So it's never going to be possible to do some sort of processing on that to figure out what the original thing was. Now, if you don't do the implementation, so the whole quantum cryptography is all about distributing this key between the two players. And if you don't do that right, if there are what will I say, loopholes in your experimental setup, then you can hack that kind of a system. And that's also been done in the last couple of years, where people have started hacking quantum cryptography systems and finding out, okay, there's a big difference between theoretically drawing the protocol and then how you actually implement it. And are you leaking extra information when you're implementing it?
So in all of this, it seems like there's a lot of ideas in quantum computing and quantum cryptography. How far are we from seeing a truly powerful quantum computer, one that is, say, similar to one of our data centers, or maybe even weaker than that?
In terms of that, how long is it till we have like a universal quantum computer or something like that, or one that could factor some very large number? Yeah, there's a physicist, Bill Phillips, who got the Nobel Prize a number of years ago, used to say that it's a 50-50 proposition with quantum computers. There's a 50% chance that in 50 years we'll have one. So let me just put that in perspective. We now have 14 or 15 qubits. That's the world record. And I might say a little bit about this other company, D-Wave, that's been in the news a lot. For universally accepted and recognized quantum computing efforts, the record is about 15, with maybe hundreds of gate operations, something like that. If you want to do quantum simulation, you need to have of order 30 or 40. And so 30 or 40, we're going to have that in 5 years or 10 years. I don't have any doubt about that. Whether or not we can get to this large number of gates that we need to do a useful simulation, that's a different question. And in order to do quantum factoring, then as I say, you need 50,000 or something like that. So there are people working on a lot of different efforts, a lot of different systems using ions or superconducting qubits or photons or something like that. The main difficulty, if I can just go back to my example here, the main difficulty, assuming this doesn't fall off the table, is that doesn't like to stay in a quantum superposition. It interacts with the environment. In this case, it's interacting with the air in the room and also with friction on the table, and that's causing it to collapse into being into either a 0 or a 1, not the superposition of 0 and 1. This is obviously just an analogy, but this happens with every quantum system, that it doesn't like to stay in this quantum superposition because it's interacting with the environment. And so you might say, well, okay, that's fine. I could put this in some evacuated chamber so it's not interacting with the environment and somehow magnetically levitate it or something like that. That's true, you could, but there's another thing you need for qubits to do. They have to be able to talk to each other. You need to do these gates. So in this analogy, it would be that the spinning of this one impacts how this one spins, which actually it does a little bit, but we need to interact on a really strong level. So they have to interact really strongly with each other. And not with the environment. So then you say, okay, well, that's fine. I just take these, I put them up in space somewhere, they're completely isolated, and they just interact with each other, and that's fine, except for the fact that there's two more things you need for any computer at all, and that's you have to have input and output. So you've got to be able to input into your computer what's the number you're trying to factor, for example, or what's the molecule you're somehow trying to simulate. And then at the end of the day, you need to make this readout of a single quantum system out. And here, it's really easy because I just slap my hand down and I see this. But if you're actually trying to read out what the state of a single electron is, a single photon is, something like that, that tends to be a lot more. You need to have strong interactions to do that. So basically, we need to have very strong interactions with the qubits to put the information in. We need to have no interactions with them while they're doing their dance and running the algorithm. And then at the end, we need to have very strong interactions again. And those are just hard It's hard to do that. This interaction with the environment, that's known as decoherence. That's the technical term for that. And it happens with any physical system that we know about. So that factor of decoherence is a problem. So you need to do some sort of error correction in order to do any kind of a long algorithm. Just like in classical computing, of course you do error correction. The thing is that in classical computing, you can do things like best 2 out of 3 in coding. So you could just run this every step, say 3 times, and then you would just take, assuming that if they all 3 agree, you say that's the right answer. If 2 of them agree, you take the 2 and you say the 1 was an error. And then by doing that sort of concatenation of that, you can really get the errors small. The problem is that in a quantum computer, you're not allowed to measure what the results are in the middle because that stops the whole computation. So you have to do more complicated schemes of encoding. And it turns out you need to have of order, let's say 7. If you can have 7 physical qubits, then you can correct any single logical qubit error. So whether an error could be a flip error, so something a 0 becomes a 1, or it could be a what we call a phase error, which would be that this sort of gets rotated around. Or if you think about this longitude and latitude, a flip error would be doing this, and a phase error would be doing a rotation, an unwanted rotation like that. So if you can encode in 7 physical qubits, 1 logical qubit, then you can, it turns out there are ways of then measuring them in a way that doesn't kill the quantum computation, and you can correct those errors, and then you can continue.
It's pretty fascinating. If one of our audience members is interested in knowing more about quantum computing, is there a good book or a reference that you might suggest?
If you just Google quantum computing, I mean, there's lots of Wikipedia articles, lots of tutorials on it. I mean, quantum computing tutorial, and there's tons and tons of web pages on it, about it. I actually wanted to say one more thing about an algorithm thing that is relatively new that might be of interest. So there's a problem called the boson sampling problem, which is equivalent to finding the permanent of a matrix. Computer scientists supposedly know what this is. I didn't know what it was, but the permanent is like the determinant of a matrix, but you make all the minus signs plus signs. And it turns out that finding the determinant of an n by n matrix is something that's exponentially hard. And it's now known, it's now believed anyway, that if you take that you can map that problem onto a very physical problem, and the physical problem is you've got a bunch of photons, which are particles of light, and they come into a network that has a bunch of beam splitters that connects things. So the beam splitters are just like this piece of plastic that I had, where the light sometimes goes through and sometimes is reflected, and you make this complicated web, and it's got maybe n inputs and n outputs. And the question is, for given inputs in here, and for given basically, depending on what the reflectivities and transmissivities of each of the elements in this network are, what's the distribution of where the things are going to show up? So what's the probability distribution? And that is mappable onto this permanent problem, which is known to be exponentially hard. And yet the quantum case seems to just solve it. You just send the things in, and you see where the photons show up, and it solves it. And the reason that's relevant is supposedly then that would violate the extended Church-Turing thesis, because you'd be able, with this system, you would have a system that would be able to solve an exponentially hard problem. And so that is something that's of great interest at the moment, both from a theoretical point of view, and also that requires of order maybe 30 photons or something like that, or 40 photons. And so I guess in the next 5 or 10 years, that will also be done. And I don't know, either the quantum mechanics will somehow break down, which would be impossible, or the Church-Turing thesis would break down, which I think the computer scientists would also say is impossible. So something's going to fall, and that's kind of interesting.
So I wanted to wrap up with a question that's changing gears a little bit, not related to your technical work, but you've worked in the university for over a decade now. Before that, you were in a national lab.
Los Alamos National Laboratory.
Right. So I wanted to ask about, how do you think, what is the difference between working in these two different environments?
So one thing is there's more bureaucracy at a national lab. There's no question about that. And we have colleagues who come to us from NIST, National Institute of Standards and Technology, and they have extra travel restrictions and computer restrictions, and they have to change their passwords every 2 months. I was at a talk once where someone couldn't remember the password to his computer, and that was really kind of annoying. So that's one thing. There's quite a bit more bureaucracy. Of course, you're not teaching at a national lab, and that can be a positive or a benefit, of course, depending on how much you like teaching. I happen to like teaching, so for me, it's much better being here. The scale of resources at a national lab tends to be bigger in the sense that if you're at Sandia National Lab, they have fabrication facilities that make our facilities look not good. And we have some of the best facilities that you can find at any university anywhere, and yet the Sandia ones completely blow us out of the water. And so if you need to make, you need a class 10 clean room or something like that, they have such things and they can do all kind of fabrication. On the other hand, things are a lot more expensive at a national lab, and a lot of times you have to get funding to work on whatever project you're doing. Same thing here, but also as professors, we're paid to teach during the semester, during the years, I should say, and that covers a lot of our salary, whereas if you're really working at a national lab, you have to find some sponsor who's, unless you're working on whatever, it kind of depends what kind of project you're working on at the national lab. But certainly places like NIST, really fabulous. I would love to work at a place like NIST. I wouldn't really love it more than working here, but I certainly wouldn't mind recommending people to go to some place like that or Sandia National Lab. It's really a good experience. The one thing I miss is that here you get a lot of unanticipated questions because you have students who don't know whatever. They don't know anything, and they come and ask questions, and by and large, almost none of the questions are ever stupid. But some of them are really incredibly insightful and cause you to think about things that you'd never think about on your own because we have a certain perspective and we sort of have this certain set of knowledge, and all of our questions are somehow related to that sphere of knowledge. And then the kid who doesn't know any of this comes in, and he has a question that's out here, and that really forces you to sort of think outside that. And I find that very, it certainly can certainly be refreshing, and also I love working with students. I mean, they're very bright, and that's a great thing. Sometimes national labs have them, sometimes they don't. It really depends. But it's certainly an opportunity that's worth looking into.
So your advice to students would be don't stop asking questions, even if you think they're stupid questions.
I've very rarely seen stupid questions, unless there's procedural things about, is the homework really due, blah, 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 or something like that. But in terms of science things, people, I mean, the questions might just reveal that we haven't really quite given enough information in lecture, and so, people are trying to make some logic jump and they don't quite have all the pieces, or they misunderstood something. I mean, all of these topics, whether it's quantum physics or high-end, computer science, they're not easy topics. And so everyone's trying to put this scaffold of knowledge together in their head, and sometimes it doesn't, it doesn't quite fit. And a question can really cause it to fit, or it can reveal that, oh, there's this whole other avenue that can be looked at. So,
okay, thank you for talking with us, Paul.
You're welcome. My
Thanks,
pleasure.
Professor Paul Kwiat. And that brings us to the conclusion of Cloud Computing Concepts Part 2, as well as the two-part Cloud Computing Concepts course series. You have seen a variety of cloud computing concepts so far, including basic cloud computing concepts like MapReduce and key-value stores. Then we started to look at classical precursors, widely used algorithms, and classical algorithms that underlie pretty much all the cloud computing systems that are out there in deployment today. In the C3 Part 1, you also saw interviews with leading managers and researchers in industry as well as academia. We continued that in Part 2, along with the discussion continued of classical algorithms that underlie today's cloud computing systems, a discussion of scalability, new and trending areas, as well as miscellaneous topics that are related to cloud computing. In this course, both Part 1 and Part 2 combined, you have done several homeworks that have hopefully allowed you to absorb the topics and exercise the topics as well. If you've done the programming assignments, you have built a membership protocol in C3 Part 1 and a key value store inside C3 Part 2. Now, both the programming assignments were structured inside an emulator, which made it easy for you to test your code using the test cases we provided. But the code is also structured in a way that you can easily port your code to run over a real network, essentially using a sockets interface. I highly encourage you to try this out if you can. Of course, you may want to think about how to multi-thread your code, for instance, to make it more efficient. And finally, of course, you have taken 2 final exams, one for each of the parts. You have now learned a lot of the distributed systems concepts that underlie today's cloud computing technologies. You have learned concepts, techniques, and applications of these to industry systems, including open source systems, where we look at applications from the inside rather than from the outside. You've seen distributed systems, distributed algorithms as applied to cloud computing. You now do have the background to go exploring through the cloud computing ecosystem out there, both open source as well as closed source systems. And for the open source systems, you should feel free to and brave to go out there and make changes to them. Try to contribute patches to Hadoop, for instance, or to the key value stores, or many of the other cloud computing systems that are out there. If you're interested in learning more about cloud computing, we do have a cloud specialization. The Cloud Computing Concepts course, Part 1 and Part 2, are part of a 4-course cloud specialization series. The other courses that are coming up in the specialization include a cloud applications course, a cloud networking course, and also a capstone that will be part of the cloud specialization series. Thank you for joining me on this journey, and I hope you have enjoyed this journey and continue to be interested in exploring more about cloud computing out there in the world.